Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing good, having a great time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Quickly in the chats, people. Everyone. Good evening, good evening, good evening, and welcome back. Good evening and welcome back. Good evening and welcome back, people. So, my dear students, as you all must be familiar with the fact, today we are going to cover one more important chapter of your chemistry, right? And it's going to be chemical equilibrium. We shall be starting the chapter exactly from the basics, from the scratch, right? All the theory, all the problem patterns, whatever can be asked from the chapter chemical equilibrium will be covered in detail in the today's session. Well, it does not matter whether you have studied the chapter before or not, because I'll be starting each and every concept from the basics, from the scratch, considering the fact that you guys have not studied the chapter before. Yeah? So let me know quickly in the chats if all of you are ready for this chapter. Let me know quickly in the chats, people, if all of you are ready for this particular chapter to be done and dusted. Someone is asking about the duration of the session. I think this chapter will take 7-8 hours to complete, right? It's not a big chapter, it's a small chapter only, so it will not take more than like 7-8 hours to complete. Okay, that too in the detailed manner. That too in the detailed manner. Yeah. So are you guys ready to be with me till the end? Are you guys ready to be with me till the end? Yes? I would want your answers in the chats. Devyansh, I'll do that after the session. And by the way, one more thing. At the end of this particular session, I'll be sharing the handwritten PDF, the session PDF of this particular chapter in my Telegram. And I hope you are already the part of the Telegram, which is Wassim Bhat Chemistry Official, right? If you are not the part of the Telegram channel yet, be the part of it right now, because right after the session, I'll be sharing the session PDF of this particular chapter. And at the same time, I'll be sharing the DPP of this particular chapter as well, which you guys are going to try out tomorrow, once we are done with this particular chapter. Okay? Perfect, people? All ready? I want the chats to flood continuously. I do not want the chats to stop at all. Yeah? Perfect. So first of all, let me give you the glimpse of the things which we are going to discuss in this particular chapter, right? Well, these are the topics which are in the chapter chemical equilibrium, my dear students. These are the topics which are in the chapter chemical equilibrium. So, starting with introduction to chemical equilibrium, reversible, irreversible reactions, characteristics of equilibrium constant, characteristics of chemical equilibrium, your law of mass action, equilibrium constant, relation between Kp, Kc, calculation of Kp, Kc with the help of mole method, degree of dissociation method, vapor density measurement, reaction quotient, Le-Chatelier's principle, and simultaneous equilibrium. So, this is going to be the session flow which we are going to follow in the today's session, people. Yeah? Now, this chapter is just the chemical part. Ionic equilibrium will be done afterwards, right? This is the chemical equilibrium. Okay? So, this is going to be our last topic. That's going to be the simultaneous equilibrium. We shall be stopping here exactly. And with this, your whole chemical equilibrium chapter will be done and dusted. Already then, should we start? Should we start, people? Let me know in the chats. Should we start? Let me know in the chats. Let me know in the chats, people, quickly. Okay. Telegram channel name is Wassim Bhat Chemistry Official. You can check it out. Of course, this chapter is super important when it comes to your NEET examination. Yeah, of course. Of course, people. All right then. So let's get going. Let's get started with the chapter Chemical Equilibrium. My dear students, first of all, how do we define the term equilibrium? How do we exactly define the term equilibrium? What is equilibrium exactly all about? Let me give you the idea of what this equilibrium exactly is all about. Let me write a statement over here. My dear students, equilibrium is defined as, I would say equilibrium is the state of the system. I would say equilibrium, it is that state of the system at which entropy becomes maximum and free energy of the system becomes minimum. As per thermodynamics point of view, equilibrium, it is that state of the system. It is that state of the system at which entropy attains its maximum value, free energy attains its minimum value, and as per thermodynamics is concerned, that state of the system at which entropy attains its maximum value, free energy attains its minimum value, that is considered to be the most stable state of the system. So what is equilibrium basically? Equilibrium, I would say, it is the most stable state of the system. It is the most stable state of the system as per thermodynamics point of view is concerned. Why is that? Because as per thermodynamics, that state of the system at which entropy is maximum, free energy is minimum, right? As per thermodynamics, we call that particular state of the system as the most stable state. So equilibrium is nothing but it is the most stable state of the system at which entropy of the system is maximum, free energy of the system is minimum, right? And at the same time, equilibrium is the state at which entropy of the system is maximum. It is maximum. If entropy of the system is maximum, that means at equilibrium, your delta S, change in entropy, it becomes zero. Why is that? Because at equilibrium, entropy of the system is maximum. It does not change after that. It is maximum, right? If entropy of the system is maximum, therefore change in entropy at equilibrium, it has to be zero. Because entropy has attained its maximum value at equilibrium, right? Similarly, Gibbs free energy of the system is minimum. At equilibrium, your Gibbs free energy of the system is minimum. It does not change after that. Okay, so I would say your delta G for the system at constant pressure and temperature, I would say it has to be zero, but where? At equilibrium. These are the first few points which I would want you guys to remember, right? And these are the points directly from equilibrium, basically. I mean, these are the points which are directly from thermodynamics, basically. Okay. So one thing which I would want you guys to remember, first of all, equilibrium is nothing. It is just that state of the system at which entropy of the system is maximum and free energy of the system is minimum, right? And as per thermodynamics point of view, that state of the system at which entropy attains its maximum value, free energy attains its minimum value, that is considered to be the most stable state of the system, right? So equilibrium, it is the most stable state of the system. Point number one. Now, my dear students, few more points, okay? Before going into the details of the equilibrium, there are few more points which I would want you guys to know first of all, right? Let's try to understand all those points in detail. See guys, the first point which I'm mentioning over here, I'm writing a simple statement. The statement is like this. As the reaction starts, as the reaction starts, as the chemical reaction starts, I would say moles of reactant, comma, concentration of reactant, and the partial pressure of reactant. It decreases with time. It decreases with time. It decreases with time. What does it mean? You'll get the idea in some time. Number two, I would say as the reaction starts, number of moles of products, concentration of product, and partial pressure of products, that increases with time. That increases with time. Let's try to understand these two statements, right, in detail, because this is important to understand the basics before getting to know the actual significance of the term equilibrium. Okay? Try to understand, guys, what exactly I'm going to do. For example, let's say I've got the reaction like this. Let's say I've got a general reaction like this. Reactants getting converted into products. R gives P. This is one general reaction, for example. Okay? This is one general reaction. Let's say this reactant over here, it is in gaseous state, as well as product is also in gaseous state. Now, my dear students, first of all, this reaction would be definitely taking place in some container. Let's say this is the container in which the reaction takes place. Let's say this is the container in which the reaction takes place. First of all, if I write a term like this, if I write T is equal to 0, if I write T is equal to 0, what does that mean? T is equal to 0 means that the reaction has not started yet. Reaction has not started yet. What does that mean? That means the reactants have not got converted into products yet. Okay? Perfect. So I would say at time T is equal to 0, there will be only reactant present in the container. There will be no product present in the container. There will be only reactant present in the container. At time T is equal to 0. At time T is equal to 0, there will be only reactant present in the container. And the number of moles of reactant present in the container at time T is equal to 0, I'm representing with NR. Okay? Number of moles of product at time T is equal to 0. That is 0 because the reaction has not started yet. Reactants have not got converted into products yet. Now, my dear students, when this reaction starts, when the reactants start getting converted into products, what will happen to the moles of reactants? I'll say moles of reactants are going to decrease with time because the reactants have now started getting converted into products. So moles of reactants will be decreasing with time. Similarly, with the time, I would say number of moles of products will increase in the container. As the reaction starts, moles of reactants are going to decrease with time and moles of products are going to increase with time. Perfect. As the reaction starts. This is complete basic stuff which I'm teaching you right now. Since at time T is equal to 0, there was only reactant in the container. There was no product. When reaction starts, what does that mean? That means when reactants started getting converted into products, I would say moles of reactants are going to decrease with time. Moles of product are going to increase with time. Perfect. Similarly, guys, one more thing. I'm defining a term which I represent with square brackets, or you can represent it with C, or you can represent this with M. What is this particular term? It represents concentration. Concentration means nothing but molarity. And how do we define concentration? Concentration is moles divided by volume of the system in liters. Moles divided by volume of the system in liters. This is what you call as concentration. Moles divided by volume of the system in liters. For example, if I write concentration of reactant, what does that mean? That means I'm talking about moles of reactant divided by volume of system in liters. If I write concentration of products, that means I'm talking about moles of products divided by volume of system in liters. Now, my dear students, few minutes back I told you, as the reaction starts, moles of reactants, they decrease with time. Therefore, concentration of reactant will also decrease with time. Similarly, moles of product increase with time. Therefore, concentration of product also increase with time, right? So as the reaction starts, moles of reactant decreases as well as concentration of reactant decreases, right? Moles of product increases as well as concentration of product increases. Perfect? Right? I believe this is clear till here. Now, my dear students, one more thing. One more thing. Since this is in gaseous state, this is in gaseous state. Tell me just one thing. Can I say at time t is equal to 0, in the container there will be only one gas, that is the reactant. At time t is equal to 0, in the container there will be only one gas. So initially at time t is equal to 0, pressure of the system is only due to the reactant, because there is only reactant present in the container at time t is equal to 0. So whatever is the pressure of the system, at time t is equal to 0, that is due to the reactant. As the reaction starts, moles of reactants, they are decreasing with time. Moles of products are increasing with time. If moles of reactants are decreasing with time, I would say pressure due to reactant, that is also going to decrease with time. If moles of reactants are decreasing with time, I would say pressure due to reactant, that's also going to decrease with time. Moles of products increase with time, so I would say pressure due to product, that is also going to increase with time. Yeah, I believe this is clear. So my dear students, as the reaction starts, moles of reactant, concentration of reactant, as well as pressure of reactant, all these three parameters, they decrease with time. Moles of product, concentration of product, and similarly pressure of products, that increases with time. Yeah, if you want to have a look on these two statements graphically, you can do that too. Let's have a look. See guys, for example, I'm plotting a graph either between moles versus time, or you can plot a graph between concentration versus time, or you can plot a graph between pressure versus time. So along y-axis, I'm either plotting moles, concentration, or pressure. Along x-axis, I'm plotting time, right? So is this just one graph or three graphs? I would say these are three graphs basically. These are three graphs: moles versus time, concentration versus time, pressure versus time. Now, my dear students, tell me just one thing. If I talk about this particular point represents time t is equal to 0. And at time t is equal to 0, reaction has not started yet. In the container, there will be only moles of reactant present. With time, moles of reactant, concentration of reactant, partial pressure of reactant, all the three terms, they are going to decrease with time. So I would say the graph is going to be like this. And this is the graph which is basically valid for what? This is the graph which is valid for the reactants. Okay? With the time, moles, concentration, pressure, all the three terms for the reactants, what happens to them? They decrease with time, right? Similarly, if you want to draw the same graph for the products, you can do that too. So let's say I'm plotting moles versus time, or concentration versus time, or pressure versus time. For what? For products. For products. My dear students, understand one simple thing. At time t is equal to 0, moles of product will be 0. With time, moles of product, concentration of product, as well as pressure of product, all the three parameters are going to increase with time. So with time, the graph is going to go upwards like this, and this is basically valid for the products. I hope whatever I've discussed till now, I hope every single thing is clear. If yes, let me know once in the chats quickly. Let me know once in the chats quickly if all these three things are super clear to every one of you. Quickly, people. Let me know in the chats quickly, everybody, if all this stuff is clear. I want you guys to be active in the chats as well, by the way, right? I want you guys to be active in the chats as well. So let me know in the chats quickly if all this stuff is clear. I want the chats to run. Sundar Ganesh is asking about thermodynamics. Thermodynamics will happen on coming Monday. Next Monday will be thermodynamics. Jeevan, you can solve those for 5 years. Last 5-year PYQs are enough. Perfect. All right. Now, guys, let's try to understand few more important things. My dear students, if I ask you, what are reversible reactions? You're going to note down all the points like me, right? Point by point, we'll be discussing things and making things clear. My dear students, understand. See, if I ask you what are reversible reactions, I would say that reaction which proceeds in both the directions. That reaction which proceeds in both the directions, that is forward as well as backward. That particular reaction which can proceed in both the directions, forward as well as backward. What do you call that particular reaction as? You call that as a reversible reaction, which is represented like this. A double-sided arrow like this. This double-sided arrow, it means that this reaction has got the tendency for the forward as well as backward reaction. Okay? So A has got tendency to get converted into B, as well as B has got the tendency to get converted into A. Perfect? So this arrow, it represents forward. This arrow represents a backward reaction. And any such reaction which can proceed in forward as well as backward direction, you'll be calling that particular reaction as the reversible reaction. Okay. Now, my dear students, I would say equilibrium. Is established. In reversible reactions. Equilibrium is established in reversible reactions. Can you think about it? Equilibrium is established in reversible reactions. What is equilibrium? It is that state of the system at which entropy is maximum, free energy is minimum. So equilibrium is the most stable state of the system. So all the reversible reactions, sooner or later, equilibrium is established in them, because every system wants to be present at the stable state. Right? And in case of the reversible reactions, which is the stable state, that is the equilibrium state, which is the stable state in case of reversible reactions. That is the reason why in every reversible reactions, equilibrium is established sooner or later. Right? Perfect. I believe this particular point is clear to everyone. So equilibrium, it is established in reversible reactions. Why? Because the system wants to be present at the stable state, and stable state in case of reversible reaction is basically the equilibrium state. That is the reason why in case of every reversible reactions, equilibrium is established sooner or later. Okay. Now guys, one more thing. My dear students, when equilibrium is established in the reactions, what happens? Remember, rate of forward and rate of backward reaction, it becomes equal. When equilibrium is established in the reactions, in the chemical reactions, right? Rate of forward and backward reaction becomes equal. How can we understand this particular statement? This particular statement we are going to understand in this way. See guys, there is one topic which we have to discuss in this chapter after some time. You call that as the law of mass action. And this is something which is to be discussed in detail after some time. But right now, I want its one point. That's it. Law of mass action. Law of mass action says that, in short, I'll be writing. Law of mass action says that rate of reaction is directly proportional to the concentration of reactants. Law of mass action says that rate of reaction is directly proportional to what? It is directly proportional to the concentration of reactants. It is directly proportional to the concentration of reactants. Now, how can we relate law of mass action with the equilibrium state? Try to understand, people, what exactly I'm going to say. Imagine that I've got the reaction A gives B. A gives B, right? This A is the reactant here, B is the product here. Okay. My dear students, just understand few things. We know at time t is equal to 0. We know at time t is equal to 0. Can I say at time t is equal to 0, concentration of A will be maximum? Right? At time t is equal to 0, concentration of A will be maximum because moles of A will be maximum. And when the reaction starts, moles of A are going to decrease. Therefore, concentration of A is also going to decrease. So one simple thing, at time t is equal to 0, concentration of A is maximum. Similarly, what do you think about the concentration of B? I would say concentration of B is 0 initially. Because at time t is equal to 0, number of moles of B in the container are 0. Therefore, concentration of B initially is equal to 0. Okay? Right? Now, as the reaction starts, concentration of A decreases with time and concentration of B, this increases with time. Concentration of A decreases with time and concentration of B increases with time. Correct? Now, people, if you understand properly, this is a reversible reaction, right? So I would say these are actually two reactions. One is your forward, A gives B. One is your backward, B gives A. This is your forward reaction and this is your backward reaction. Can I say this A is basically the reactant of forward reaction? Yes. This B is the reactant of backward reaction. This A is the reactant of forward reaction. This B is the reactant of backward reaction. What law of mass action says? Law of mass action says rate of the reaction is directly proportional to concentration of reactant. Okay? Rate of reaction is directly proportional to concentration of reactant. So if I ask you, what about rate of forward reaction? Rate of forward reaction, I would say that will be directly proportional to concentration of reactant, and reactant here is A. So rate of forward reaction is directly proportional to concentration of A. Okay? Similarly, rate of backward reaction will be directly proportional to what? Rate of backward reaction will be directly proportional to concentration of reactant, and reactant here is B. So I'm writing it is directly proportional to the concentration of B. Okay? Rate of forward reaction is directly proportional to concentration of A. Rate of backward reaction is directly proportional to concentration of B. Okay? Now, my dear students, we know something. Initially, at time t is equal to 0, concentration of A is maximum. So rate of forward reaction will be maximum. So I would say at time t is equal to 0. At t is equal to 0. Since concentration of A is maximum, therefore rate of forward reaction will be maximum. Rate of forward reaction will be maximum, right? At time t is equal to 0. Since at time t is equal to 0, concentration of B is 0. If concentration of B is 0, I would say initially at time t is equal to 0, I would say rate of backward reaction will be minimum. Rate of backward reaction will be 0. Now, my dear students, you know, as the reaction starts, concentration of A decreases. If concentration of A decreases with time, I would say rate of forward reaction decreases with time. Since concentration of B increases with time, therefore rate of backward reaction increases with time. Initially, rate of forward reaction is maximum. Rate of backward reaction is 0. Now with time, rate of forward reaction decreases, rate of backward reaction increases. Rate of forward decreases, rate of backward increases. Can I say there will be a time when rate of forward and backward becomes equal? Yes. And what do we call that stage? We call that particular stage as equilibrium. So I would say at equilibrium, your rate of forward and your rate of backward reaction, it becomes equal. Your rate of forward and backward reaction becomes equal. Perfect. At equilibrium. When equilibrium is established in the reaction. Okay. Okay, guys, is this clear? Is this clear? Is this clear? So initially your rate of forward reaction was maximum, backward reaction was zero. Now with time, rate of forward reaction decreases, rate of backward reaction increases. There will be a time when rate of forward and backward becomes equal. And at that point of time, we say equilibrium has been established in the reaction. So at equilibrium, I would say rate of forward and your rate of backward reaction, they become equal. Okay. Who is this RAJRMU? Just focus on this topic. Do not, avoid the spamming and stuff. Okay. Just focus on the topic right now. Avoid the rest of the things. Okay, guys. All right. If I represent this scenario in the form of a graph, we can do that too. For example, here I'm plotting rate of the reaction. Here I'm plotting time. So rate versus time. Understand, rate versus time. My dear students, this point represents time t is equal to 0. This point represents time t is equal to 0. And at time t is equal to 0, at time t is equal to 0, rate of forward reaction is maximum. With time, rate of forward reaction decreases. With time, rate of forward reaction decreases. This is the rate of forward reaction, which is decreasing with time. Similarly, I would say with time, rate of backward reaction increases. With time, rate of backward reaction increases. So this is the rate of backward reaction. And there will be a scenario after which rate of forward and backward reaction becomes equal. There'll be a scenario after which rate of forward and backward reaction is becoming equal. At that point of time, we say in the reaction, equilibrium has established. Okay? Right? Right, people? So when the reaction starts, rate of forward reaction decreases, rate of backward reaction increases. There will be a time after which rate of forward and backward has become equal. So I would say in the reaction, equilibrium has been established. So this is the graph which is correctly representing what? Which is correctly representing equilibrium. I believe this particular point is also clear to every one of you. Yeah? Now, my dear students, there are few more important points which you need to know. And what are those important points? Let's have a look. I would say when equilibrium is established in the reaction, at equilibrium, I would say at equilibrium, all the measurable properties, I would say at equilibrium, all the measurable properties of the system, like what are our measurable properties? Moles. Mole is a measurable property. Concentration is a measurable property. Pressure is the measurable property. Temperature, etc. I would say at equilibrium, all the measurable properties attain a fixed value. All the measurable properties, they attain a fixed value. What does that mean? That is, becomes constant. Becomes constant. Let's try to understand this particular statement because this is super important when it comes to equilibrium. When equilibrium is established in the reaction, all the measurable properties of the system, like pressure, like temperature, like concentration, like moles, right? They become fixed. They do not change after that, right? So my dear students, remember this particular stuff. Again, I'm repeating the same thing. When you talk about equilibrium, when equilibrium is established in the reaction, moles of reactants products, they become fixed, they become constant, they do not change after that. Concentration of reactants products, they become constant, they do not change after that. Okay? All the measurable properties of the system, they attain a fixed value, they become constant. Let's try to understand this particular statement in detailed manner because this is something which I feel is important. See guys. For example, I'm going to show you case 1 over here, which is going to represent equilibrium, which is going to show us equilibrium. See guys, let's say you've got the reaction like this, A gives B. Let's say this is the reaction, and this particular reaction will be definitely taking place in some container. Okay? Now people, understand few things what I'm going to say. Let's assume that at time t is equal to 0, we had 10 moles of this reactant. So this would be 0 in the beginning. Let's assume that in the beginning we had 10 moles of reactant and this B would be 0. Perfect. Because the reaction has not started yet. Now, as the reaction starts, moles of reactants are going to decrease, moles of products are going to increase. Okay. Concentration of reactant is going to decrease, concentration of product is going to increase. Partial pressure of reactant is going to decrease, partial pressure of product is going to increase as the reaction starts. Perfect. I'm assuming when 20% of the reaction gets completed. I'm assuming when 20% of the reaction gets completed. Let's assume at that point of time, equilibrium is established in the reaction. So I'm assuming when 20% of this reaction gets completed, equilibrium is established in the reaction. When 20%, I told you already, equilibrium in the reversible reaction can be achieved anytime, sooner or later. I'm assuming when 20% of the reaction is getting completed, at that point of time, in the reaction, equilibrium is being established. Right? Equilibrium is being established. Now guys, tell me one thing. What is meant by 20% completion? What is meant by 20% completion? It means that at equilibrium, 20% of the reactant has got converted into product. I would say at equilibrium, 20% of reactant has got converted into product. My dear students, I started with 10 moles of reactant, right? What is 20% of 10? 20% of 10 means 20 divided by 100 multiplied by 10, right? Which comes out to be how much? It comes out to be 2. Perfect. So I would say, if I'm saying 20% of reaction is being completed, that means 20% of reactant has got converted into product. What does that mean? If I've taken 10 moles of A, that means out of 10 moles of A, 2 moles have got converted into products. Okay? If out of 10 moles of A, 2 moles have got converted into products, I'll be left with 8 moles of A here. And I would say 2 moles of product have got formed. 2 moles of product have got formed at equilibrium. Perfect. My dear students, imagine that this particular reaction is taking place in a container whose volume is 1 liter. Whose volume is 1 liter. Okay, let's assume this also. Now see, if I'm telling you that equilibrium is established in the reaction when 20% reaction is completed, that means now when 20% reaction is completed, if equilibrium is established, it means now the rate of forward and backward reaction, it has got equal. Rate of forward and backward have got equal. That means if now 1 mole of A is getting converted into B, I would say at the same time 1 mole of B will start getting converted into A. I'm saying when 20% of the reaction is completed, equilibrium is established. At equilibrium, rate of forward and backward becomes equal. So I would say now if 1 mole of A is getting converted into B, at the same time 1 mole of B will be getting converted into A. Due to which these moles of reactants and products, now they are not going to change. They have attained a fixed value, constant value. Now moles of reactant are going to remain 8, moles of product are going to remain 2 over here in this particular case, because now the rate of forward and backward are becoming equal. If 1 mole of A is getting converted into B, at the same time 1 mole of B is getting converted into A. Perfect. Is getting converted into A. Right? Now we will one more thing. So we got to know one thing. At equilibrium, moles of reactant product, they attain the fixed value. They become constant. They do not change after that. Now, since the volume of container is 1 liter, if I divide these moles with the volume, what do I get? Moles by volume. That gives me concentration. So I would say concentration of reactant and product at equilibrium will be 8 divided by 1. That means 8 molar. This is 2 molar. Perfect. Right, people? I would say when equilibrium is established, since the moles of reactants products, they are not going to change now. Therefore, if you talk about concentration is moles divided by volume. If moles are not changing, that means concentration of reactants products, it won't change also. It will also attain a fixed value. Right? Perfect. So, I would say when equilibrium is established, the concentration of reactants products, they'll be fixed, they'll be constant. They are not going to change after this. Right, people? And if you observe one thing, look at these terms. This is the concentration of reactant at equilibrium. This is the concentration of product at equilibrium. Do you see one thing? Concentration of reactant at equilibrium over here in this case is greater than the concentration of product at equilibrium, right? Anything is possible. Concentration of reactant at equilibrium can be greater than concentration of product at equilibrium. It can be less. It can be equal as well. The point is, the concentration of reactant products, they have to attain a fixed value. They should be constant. They should be constant. Okay? They should be constant. Now see guys, if you want to have a graphical look on what I said till now, so have a look. So I'm plotting a graph between, let's say, moles versus time. I'm plotting a graph between moles versus time. Okay. So my dear students, this is time t is equal to 0. Time t is equal to 0. At time t is equal to 0, moles of A were 10. Let's say this pointer represents 10 over here. Okay. When the reaction started, moles of reactants decreased from 10 to 8. Let's say this pointer represents 8. When reaction started, moles of reactants decreased from 10 to 8. And then after that, became constant. Did not change. Perfect. Talk about the product. At time t is equal to 0, moles of product were 0. Right? Now with time, moles of product increased from 0 to 2. With time, moles of product increased from 0 to 2. And when moles of product increased from 0 to 2, after that, the moles of product did not change. Okay, after that, moles of product did not change. This is the graph which is valid for reactant. This is the graph which is valid for product. Can I say this is the time? Can I say this is the time after which? This is the time after which moles of reactant as well as moles of product, they are not changing now. They have attained a fixed value. They have become constant. So I would say this particular point is telling us that equilibrium has been established in the reaction. Right? Once equilibrium is established, moles of reactants products, they are not going to change after that. Similarly, same will be the graph for concentration versus time. Perfect. Concentration of reactant decreases first, becomes constant. Concentration of product increases first, becomes constant. And after equilibrium, concentration of reactant products does not change after equilibrium. It is fixed. Same is the case for pressure versus time as well. I would say pressure of reactant decreases first, then becomes constant. Pressure of product increases first, then becomes constant. After equilibrium, pressure of reactant product, it does not change. It becomes constant, fixed. Right? So, this particular graph, it correctly represents equilibrium. And this particular graph is telling you that at equilibrium, concentration of reactant can be more than that of concentration of product. So, this graph is telling us that concentration of reactant at equilibrium is more than that of concentration of product at equilibrium. Perfect. I'm again repeating the same thing, guys. At equilibrium, concentration of reactants products are supposed to be constant. They do not change after that. They do not change after that. Okay. Now, this was the first case to explain you equilibrium. Let me show you the second case. For example, I'm taking the reaction A gives B. And here, for example, I'm starting with 10 moles of reactant. This is 0. Let's say the container in which this reaction takes place, let's say its volume is 1 liter. Let's assume when 50% of the reaction gets completed, equilibrium is established in the reaction. And what is meant by 50% completion? 50% completion means that 50% of reactant getting converted into what? 50% of reactant getting converted into product. So I would say at equilibrium, out of 10 moles of A, 5 moles would have got converted. So I'll be left with 5 moles of A, and I would say 5 moles of B also have got formed. Okay. So at equilibrium, when equilibrium is established, we are left with 5 moles of A and 5 moles of B also have got formed. Because I'm assuming when 50% reaction is getting completed, equilibrium is being established. So I would say at this particular point, rate of forward and rate of backward now would have become equal. If rate of forward and backward now have become equal, that means if 1 mole of A is getting converted into B, at the same time 1 mole of B will be getting converted into A. Due to which moles of reactants products, they'll be fixed, they'll be constant. They are not going to change after that. They are not going to change after that. Right? So people, if I talk about, since these were the moles, if I talk about concentration, since volume is 1 liter, so I would say concentration of reactant at equilibrium is 5 molar, concentration of product at equilibrium here is 5 molar. Perfect. These concentrations are also not going to change. because equilibrium has been established in the reaction. And this is the scenario which is telling us that concentration of reactant and concentration of product at equilibrium can be equal as well, right? Can be equal as well. Concentration of reactant product at equilibrium can be equal as well. Perfect. So if you want to show this graphically, you can do that. See guys, for example, I'm plotting a graph between moles versus time, or concentration versus time, or pressure versus time. Okay. See, initially at time t is equal to 0, moles of A were 10. Moles of A at time t is equal to 0 were 10, right? And as the reaction proceeded, as the reaction started, moles of reactant decreased from 10 to 5. Let's say this represents 10. Over here, this pointer represents 5. So as the reaction started, moles of reactant decreased with time, and from 10 to 5. And after this, moles of reactant are not going to change. They are going to remain constant, 5 only. Similarly, moles of product from 0 to 5, and after that, they are not going to change. And this is the point which is telling us, that equilibrium has been established in the reaction. Because after this particular point, as you can see, after this particular point, the moles of reactants products are not changing. They have attained a fixed value. And this is the scenario which is telling you that the concentration of reactant and product at equilibrium can be equal as well. This was the case which was telling us concentration of reactant at equilibrium can be greater than that of concentration of product. Perfect. Right, people? Yes. Similarly, there can be one more case which I believe you can easily understand now. Let's say you have got the reaction A gives B. This is the reaction. Let's say at time t is equal to 0, we have got 10 moles of A. This is 0. Let's say when 80% of the reaction gets completed, equilibrium is established. So 80% of reaction completion means 80% of reactant getting converted into product. So I would say, people, 80% of 10 means 8. I would say out of 10 moles of reactant, 8 moles have got converted into product. So I'll be left with 2 moles of reactant. And I would say 8 moles of product would have got formed. Now I'm assuming equilibrium has been established. That means now the rate of forward and backward has become equal. So if 1 mole of A is getting converted into B, at the same time 1 mole of B is getting converted into A. Right? So I would say now the moles of reactants and products, they are not going to change. They have attained a fixed value, constant value. Right? Attained a fixed value, constant value. Perfect. If I talk about the concentrations, I would say since the volume of container is 1 liter, I would say concentration of reactant at equilibrium is 2 molar, concentration of product at equilibrium is 8 molar. And my dear students, this is the scenario which is telling you that concentration of product at equilibrium can be greater than that of concentration of reactant at equilibrium. Okay? Perfect. So people, if you want to represent this particular scenario graphically, I believe you can do that. Let's say I'm plotting a graph between moles versus time, or you can plot it for concentration versus time or pressure versus time. So what is happening? At time t is equal to 0, moles of reactants are 10. Let's say this particular point represents 10. With the time, moles of reactant are reaching from 10 to 2. Let's say this particular point represents 2. As the reaction starts, moles of reactants decreases from 10 to 2, then attains a fixed value. Does not change after that. Similarly, moles of product from 0 to 8. Moles of product from 0 to 8. Let's say this point represents 8 here. So 0 to 8. Moles of products are increasing from 0 to 8 and then becoming fixed, constant. Okay. So I would say, people, this is the time after which moles of reactant as well as moles of product are becoming constant. They are not changing. So I would say at this particular point, equilibrium is established in the reaction. And this is the equilibrium which is telling you that concentration of product at equilibrium can be greater than that of concentration of reactant at equilibrium. I believe all these 3 cases are perfectly clear to every one of you. So my dear students, the point is, see what my final point is here. My final point is pretty much simple. At equilibrium, rate of forward and backward becomes equal. The term I'm using is equal. At equilibrium, rate of forward and backward becomes equal. But at equilibrium, concentration of reactants and products becomes constant. becomes constant, becomes fixed, does not change after that. Okay? It can be equal, it cannot be equal as well. As in this particular case, concentration of reactant products have become fixed but are not equal at equilibrium. Here, concentration of reactant products have become fixed, and at the same time here it's equal as well, right? Similarly, concentration of reactant products has become fixed after equilibrium but are not equal. So remember this particular thing, because this is super important, guys. Remember this particular thing. At equilibrium, concentration of reactant products, it attains a fixed value, does not change after that. It can be, concentration of reactant product at equilibrium can or cannot be equal. But in terms of rate, at equilibrium, rate of forward and backward is always equal. Okay? For example, if I give you a question and let me see whether you can solve that question or not. The question is pretty much simple. I'm going to give you some graphs and you are going to let me know which all graphs are correctly going to represent equilibrium. Okay, I'm going to give you some graphs. Tell me which all graphs are correctly going to represent equilibrium. Rate versus time. This one of the graph. This is it. Second is rate versus time. Okay. The third graph is concentration or weight. Let me call it rate only. This is rate versus time again. The fourth graph is concentration versus time. Next is also concentration versus time. Next is also concentration versus time. Tell me, which all graphs are going to represent equilibrium, people? Is the first graph going to represent equilibrium? Rate versus time. We know at equilibrium, rate of forward, backward becomes equal. This does not represent equilibrium. Okay? Because if you think this is the point where equilibrium is established, that means this has to be the rate of forward reaction at this point. And this has to be rate of backward reaction at this point. If you see rate of forward and backward, they are not equal. This is rate of forward, backward. No, not. This represents equilibrium. Rate of forward, backward is equal. If you look here, this point, at this particular point, this is the rate of backward. This is the rate of forward. Rate of forward, backward is not equal, does not represent equilibrium. Now, concentration versus time. Concentration versus time. So, at equilibrium, concentration of reactant product should become constant. Can be equal, cannot be equal, right? It should become constant basically. So if you see concentration of reactant after this point is becoming constant, concentration of product after this point is becoming constant, so it correctly represents equilibrium. This also represents equilibrium. This also represents equilibrium. Am I clear with all this stuff? Say yes or no in the chats if all these things are absolutely super clear to every one of you. Everyone, people in the chats. Everyone in the chats, people. Everyone, people. Perfect. Perfect, perfect, perfect. Now, there are a few more points which you need to understand and remember about equilibrium. And then we'll move ahead and talk about our next topic, that is law of mass section. See, guys, one more point. Let me tell you equilibrium. If I talk about equilibrium, I would say it is attained equilibrium is attained in closed vessels? I would say equilibrium is attained in closed vessels. Why is that? Why is that? Have a look. For example, let's say you have taken a container which is, for example, open on one side. Let's say the container is open on one side. Okay, this is something which I'm assuming. The container is open on one side. Now, people, in this container, for example, you're keeping calcium carbonate solid. In this container, you have got calcium carbonate solid. For example, I'm heating this container up. If I'll be heating this container up, what is going to happen? I would say this calcium carbonate, it will get converted into calcium oxide. And with that, you will be getting carbon dioxide gas as well, right? Since I've taken calcium carbonate in the container, I'm heating this calcium carbonate. This calcium carbonate gets converted into calcium oxide. With that, you get carbon dioxide, right? This is something which is going to happen right now, okay? If you look carefully, since you took calcium carbonate solid in the beginning, you heated it up, it got converted into calcium oxide solid, and it gave a gas as well. Since the container is open on this side, so the gas which is being evolved here, can I say this gas can leave the container easily because the container is open on one side, right? Because the container is open on one side. If the gas is leaving the container, can I say there will be a time when there will be no gas present in the container, when there will be no carbon dioxide left in the container? If there is no carbon dioxide left in the container, is the backward reaction possible? I would say backward reaction is not possible. And if the backward reaction is not possible, will equilibrium be established here? No way. For equilibrium, forward reaction should happen, backward reaction should happen, then rate of forward and backward should become equal, right? At that point of time, we say equilibrium is established. But if the container is open on one side, the gas which is being generated through forward reaction, all that gas in the container, that's going to leave the container. And if this gas leaves the container, there'll be no gas available for the backward reaction. So remember, equilibrium is attained in the closed vessel. Okay, next point. Remember, my dear students, if I particularly talk about equilibrium, equilibrium is dynamic in nature. Equilibrium is dynamic in nature. What does that mean? For example, you have got the reaction like this. A gives B. Let's say equilibrium is established in this particular reaction. My dear students, once equilibrium is established in the reaction, it never stops. It never stops after that. Because the rate with which forward will be happening, with the same rate, backward will be also happening. So this cycle continuously keeps on running, right? In the same time duration, A gets converted into B, B gets converted into A, right? The cycle continuously keeps on working, okay? So when equilibrium is established in the reaction, I would say the reaction never stops. That's why we say equilibrium, it is dynamic in nature. Reaction is not going to stop because the rate with which forward will be happening, with the same rate backward will be also happening. So reaction never stops. The cycle continuously goes on, forward to backward, forward, backward, forward, backward, and continues, right? So do remember this particular point as well. So these were some of the characteristic features, my dear students, which I want to discuss with you about the term equilibrium. I hope all this stuff is clear to you. Now, let's move on to one more topic. What is that? That is your law of mass action. Law of mass action. My dear students, if you talk about this law of mass action, let me tell you, it is completely theoretical stuff. It is all theoretical. Law of mass action, it is theoretical. Point number one. Point number two, it was given by two scientists. One was your Goldberg and another one was P. Vage. These were the two scientists who gave this particular concept of law of mass action. Okay, what this law of mass action is all about, what it states. My dear students, as per law of mass action is concerned, let me write it here. As per law of mass action is concerned, rate of the reaction is directly proportional rate of the reaction is directly proportional to the product of to the product of active masses of reactants, raised to the powers of their respective stoichiometric coefficients. Raised to the powers of their respective stoichiometric coefficients. Let's understand what it means. First of all, just remember one thing. Here, guys. I used a term active mass here. Remember just 3 points when it comes to active mass. That's all. You're sorted. See, whenever you see any reactant or product in aqueous phase, in the bracket, if there is AQ mentioned, any reactant or product which will be in aqueous phase, in the bracket, if there is AQ mentioned, its active mass is taken as its concentration. Its active mass will be its concentration. Whenever you will be having a reactant or product in gaseous phase, its active mass can be its concentration, it can be its pressure as well. Because for gases, concentration as well as pressure, both the things are defined for gases. Concentration is also defined for a gas, pressure is also defined for a gas. So for gases, active mass can be concentration, it can be taken as pressure as well. When you'll be having a pure solid or a pure liquid, for pure solids or pure liquids, active mass is taken as unity. These are the four things which I would want every one of you to remember from now onwards. Whenever you see any reactant or product in the aqueous phase, its active mass will be taken as its concentration. If it is in gaseous phase, its active mass will be either concentration or pressure. If it is a pure solid or pure liquid phase, its active mass is taken as one unity. Yeah. Now, try to understand what this law of mass action exactly is all about. See, guys. Imagine that we have got the reaction like this. N1A plus N2B. It gives N3C plus N4D. This is your reaction. Yeah? This is your reaction. Now, my dear students, here, if you look carefully, if I ask you whether this is one reaction or these are actually two reactions, I would say these are actually two reactions. The first reaction is your forward, second reaction is your backward. Let me write them separately. N1A plus N2B. It gives N3C plus N4D. This is your forward reaction. What about the backward reaction? I would say N3C plus N4D. It gives what? It gives N1A plus N2B. This is the backward reaction. Okay, this is forward and this is backward. My dear students, if you look carefully, I would say this A and B, these are the reactants of forward reaction. This C and D, these are the reactants of backward reaction. Okay, these are the reactants of forward, these are the reactants of backward. Now, as per law of mass action is concerned, rate of the reaction is directly proportional to the product of active masses of reactants raised to the power their stoichiometric coefficients. What does that mean? For example, as per law of mass action, I can say rate of reaction. Which reaction I'm considering? This particular forward reaction I'm considering. So I'll be writing rate of forward reaction. See, as per law of mass action, what is there? As per law of mass action, rate of reaction is directly proportional to product of active masses of reactants. Active mass of reactant 1 multiplied by active mass of, for example, reactant 2 raised by their stoichiometric coefficients. Let's say stoichiometric coefficient of reactant 1 was N1, stoichiometric coefficient of reactant 2 was N2. This is the simplest statement of the law of mass action. Now I'm using this law of mass action here. I'm saying rate of forward reaction is directly proportional to the product of active masses of reactants. Reactant here is A and B. So it's active mass of A raised by its stoichiometric coefficient N1 multiplied by active mass of B raised by its stoichiometric coefficient N2. Okay. Similarly, if I use the law of mass action for the backward reaction, I will say rate of backward reaction is directly proportional to the product of active masses of reactants. Reactants here are C and D. So I'll write active mass of C raised by N3, active mass of D raised by N4. Okay. Perfect. Now, remove the proportionality sign. You'll be getting a constant here, which I'm representing as Kf. Active mass of A raised by N1, active mass of B raised by N2. Similarly, if you remove the proportionality sign here, it's going to be Kb active mass of C raised power n3, active mass of D raised power n4. Right, people? Now, first thing, this RF, what does it represent? It represents a rate of forward reaction. KF is the rate constant of forward reaction. Rate of backward reaction. Rate constant of backward reaction. Okay? You know, people, at equilibrium, something which we already discussed, at equilibrium, rate of forward and rate of backward reaction becomes equal. If at equilibrium, rate of forward and backward becomes equal, rate of forward and rate of backward becomes equal, I would say this particular term, which is Kf multiplied by active mass of A raised power n1, active mass of B raised power n2. It has to be equal to RB. RB is nothing but, it is Kb, active mass of C raised power n3, active mass of D raised power n4. Now, my dear students, just do one thing. Just separate the active masses and separate the constants. So, I'm writing Kf divided by Kb. Kf divided by Kb is equal to, it is nothing but active mass of C raised power n3, active mass of D raised power n4 divided by active mass of A raised power n1, active mass of B raised power n2. Perfect? Right? Now, Kf is what we call as the rate constant of forward reaction. Kb is what we call as the rate constant of backward reaction. And my dear students, since these two are constants, I would say division of these two constants. Division of these two constants will give us one more constant, which is what you call as equilibrium constant. Right? So, if I ask you to define the equilibrium constant, how do you define the equilibrium constant, guys? Equilibrium constant is defined as the ratio of rate constant of forward to that of rate constant of backward reaction. Equilibrium constant is defined as the ratio of rate constant of forward to that of rate constant of backward reaction. How do we write its expression? Expression is written like this. Active mass of C raised power n3, active mass of D raised power n4 divided by active mass of A raised power n1, active mass of B raised power n2. So basically, in order to write the expression of equilibrium constant in the numerator, if this is your general reaction, if this is your actual reaction, in this actual reaction, these are your reactants A and B, and these are your products. And if you want to write the expression for equilibrium constant, in the numerator, you will be taking the active masses of products. Active mass of C, active mass of D, raised by their stoichiometric quotients. In the denominator, you will be writing active masses of reactants. Active masses of reactants. Active mass of A raised by N1, active mass of B raised by N2. Right? I believe this is clear till here. Okay? I believe this is clear till here. Okay, guys. So, how do we define the equilibrium constant? If this is the question asked, equilibrium constant is defined as, I would say it is defined as the ratio of rate constant of forward to that of rate constant of backward reaction. Okay, so you can say KEQ is nothing but, it is equal to KF divided by KB. KF is rate constant of forward, KB is rate constant of backward. Now, my dear students, how do we write the expression for equilibrium constant? I showed you how to write the expression for equilibrium constant. You know it already now. In the numerator, you will have to write the active mass of products. In the denominator, you will have to write the active mass of reactants. Yeah? So, if I talk about the equilibrium constant KEQ. Equilibrium constant KEQ. How do I write its expression in general? It is active mass of C raised by N3, active mass of one more product D raised by N4 divided by active mass of A raised by N1, active mass of B raised by N2. Right? Okay. Now, my dear students, remember, when you talk about equilibrium constant, we have got two types of equilibrium constants in our syllabus, right? But I'll be teaching you three over here. One is going to be your, because the third one will be useful when we do the Le-Chatelier principle. The first equilibrium constant is your Kp. Another equilibrium constant is your Kc. One more I'll be teaching you here, that is Kx. Now, what is this Kp? What is Kc? What is Kx? All these three, they are the equilibrium constants, right? They are the equilibrium constants only. But, what is the difference? My dear students, in this particular expression, instead of active mass, I mean, if I replace active mass by the term pressures, if I replace active mass in this particular expression by the term pressures, I'll be replacing Keq with Kp at that point of time. And the Kp expression becomes, I will write partial pressure of C at equilibrium raised power n3, partial pressure of D at equilibrium raised power n4 divided by partial pressure of A at equilibrium raised power n1, partial pressure of B at equilibrium raised power n2, right? This is the expression of my Kp. Similarly, people, if I talk about Kc, if in this particular expression, your active masses are your concentrations, at that point of time, your Keq will be called as Kc. And how do you write its expression? I'll be writing concentration of C in the container at equilibrium raised power n3, concentration of D in the container at equilibrium raised power n4 divided by, instead of active mass of A, it's concentration of A at equilibrium raised power n1, concentration of B at equilibrium raised power n2. Similarly, my dear students, if I replace active masses by the term mole fractions, then at that point of time, I'll be calling equilibrium constant as Kx. And how do you write the expression of Kx? It is going to be mole fraction of C at equilibrium raised power n3, mole fraction of D at equilibrium raised power n4 divided by mole fraction of A at equilibrium raised power n1, mole fraction of B at equilibrium raised power n2. So my dear students, this is the way by means of which you write the expression for Kp, you write the expression for Kc, and you write the expression for Kx as well. Okay? Yeah? Hema Madhuri, why are you spamming? Yes, this is more than sufficient. Do not spam. Just follow this and follow the DPP which I'll be providing on my Telegram tomorrow. Right? That's more than sufficient. Do not spam. Is this stuff clear till here, people? Is it clear till here? Quickly. Everyone in the chats. Is all the stuff clear? Whatever things we have discussed till now, is every single thing clear? I'm asking you a question. Say yes or no in the chats quick. Say yes or no in the chats quick, people. Everybody. Sir, what is your DPP source? I am the DPP source. Perfect, guys. Let's move ahead and let's talk about some other important things. See, guys. So till now, we got to know how to write the expression for your equilibrium constant. And this is the general expression for equilibrium constant. And further, I classified it in Kp, Kc, and Kx, right? Kp, Kc, and Kx. Now, my dear students, let's exactly see how do we write equilibrium constants for different types of reactions. How do we write equilibrium constants for different types of reactions? If you look at this particular reaction, people, right? Gas, gas, gas. So I would say the phase of every reactant product is same. The phase of every reactant product is same. So first of all, if the phase is same, I'll be calling this particular reaction as the homogeneous reaction. It is the homogeneous reaction. And since every reactant product is in gaseous phase, so it is homogeneous gaseous phase reaction. It is basically homogeneous gaseous phase reaction. So, since all the reactants products, they are in gaseous phase, right? For gases, active mass can be concentration as well as pressure. Active mass, you take either concentration or pressure. So, that means I can write the expression for Kc as well as Kp, right? Because for gases, active mass is concentration as well as pressure. So, If you want to write the expression for Kc, you'll be starting with the product. Now you'll be writing concentration of H2 at equilibrium raised power stoichiometric coefficient, concentration of I2 at equilibrium raised power stoichiometric coefficient divided by concentration of Hi at equilibrium raised power stoichiometric coefficient. This is the expression for your Kc. Similarly, people, if you want to write the expression for Kp, so now you'll be using the term pressures instead of concentrations. I'll be writing partial pressure of H2 at equilibrium raised power stoichiometric coefficient, partial pressure of I2 at equilibrium raised power stoichiometric coefficient, partial pressure of Hi at equilibrium raised power stoichiometric coefficient. That is 2. Okay. If you look at this particular reaction, here every reactant product is in aqueous state. For aqueous species, active mass is concentration, active mass is not pressure, right? So you'll be only able to write the expression for Kc here. You won't be able to write the expression for Kp. For Kp, there should be minimum one reactant or product in gaseous state. But here, everyone is in aqueous state. So Kc is equal. Start with the product. It's concentration of NH4 positive at equilibrium raised power 1, concentration of OH negative at equilibrium raised power 1 divided by concentration of NH4OH at equilibrium raised power 1. This is how you are going to make the expression for Kc for this particular reaction. Look at these two reactions, people. If you look carefully, this is solid, this is gas. So I would say the phase of not every reactant product is same. The phase of every reactant product is not same. So I'll be calling this as heterogeneous reaction. And at the same time, people, at the same time, if one of the reactant or product minimum is in gaseous state, then you'll be calling this as heterogeneous gaseous phase reaction. Now, since this is solid, its active mass is 1, nothing to do with it. This is solid, its active mass is 1, nothing to do with it. This is gas, its active mass is concentration as well as pressure. So you will be in a position to write the expression for Kp as well as Kc. So what will be the expression for Kp and Kc here? My dear students, Kp is going to be simple. Partial pressure of carbon dioxide at equilibrium raised power 1, and Kc is going to be concentration of carbon dioxide at equilibrium raised power 1. Okay, right? Similarly, look at this particular scenario. Solid, gas, gas. So heterogeneous reaction and heterogeneous gaseous phase reaction. So since this is solid, its active mass is unity, nothing to do with this. This is gas, gas. For gases, active mass is concentration as well as pressure. So you can write the expression. You can make the expression for Kc as well as you can make the expression for Kp, right? What will be Kc expression? Kc expression start with the product. It's going to be concentration of SO3 at equilibrium raised power 1 divided by, it's going to be concentration of O2 at equilibrium raised power 3 by 2. If I talk about Kp, it's going to be pressure of SO3 at equilibrium raised power 1 divided by pressure of O2 at equilibrium raised power stoichiometric coefficient, that is 3 by 2. Perfect. Right, people? I believe this is clear. Few more reactions. This is gas, right? For gases, active mass is concentration as well as pressure. So I can write the expression for Kc as well as Kp. So Kc expression will be concentration of NO2 at equilibrium raised power stoichiometric coefficient 2 divided by concentration of N2O4 at equilibrium raised power stoichiometric coefficient 1. Kp expression will be equal to pressure of NO2 at equilibrium raised power stoichiometric coefficient 2, pressure of N2O4 at equilibrium raised power stoichiometric coefficient 1. Right? Similarly, people, this is solid, this is gas, heterogeneous gaseous phase reaction. So I'll be able to write Kp as well as Kc expression here. So if I write the Kc expression here, Kc expression is going to be concentration of H2S at equilibrium raised power stoichiometric coefficient multiplied by concentration of NH3 at equilibrium raised power stoichiometric coefficient 1. This is solid, so its active mass is 1, nothing to do with that. If you talk about Kp, Kp expression is going to be partial pressure of NH3 at equilibrium raised power 1 multiplied by partial pressure of H2S at equilibrium raised power 1. This is solid, its active mass is unity. So you wrote the expression for Kp as well as Kc for this particular reaction. Okay? All clear, people? All clear? All clear? All clear? Here I'm teaching you one more stuff, that is calculation of delta Ng for a reaction. This is something which we'll be using in the next chapter too, which is your thermodynamics. What is delta Ng first of all? What is delta Ng? Delta Ng represents the number of moles of gaseous products, number of moles of gaseous products minus the number of moles of gaseous reactants. Number of moles of gaseous reactants. For example, let's say you've got the reaction like this. N1A gas plus N2B gas. Let's say it's in equilibrium with N3C gas plus N4D gas. I'm assuming this is one balanced chemical equation. My dear students, if I want to write delta Ng for this particular reaction, we can do that. Delta Ng is equal to number of moles of gaseous products. See, this product, both are in gaseous state, so I'll be considering them. I'll be considering only those reactants and products to calculate delta Ng. To calculate delta Ng, I'll be considering only those reactants and products which are in gaseous state. And I'll always start with the product side. Gaseous state, gaseous state. How many moles of this? N3. How many moles of this? N4. So, N3 plus N4. It gives me the number of moles of gaseous products. It gives me the number of moles of gaseous products. Minus the number of moles of gaseous reactants. This is gaseous, this is gaseous. Its moles are N1, N2. So, it's going to be N1 plus N2. Right? This is how you exactly calculate delta Ng for any sort of reaction. Okay? Perfect. For example, you have got the reaction like this. Let's say, my dear students, you have got the reaction as, let me take the examples which we already took. What will be delta Ng for this particular reaction? Delta Ng is equal to number of moles of gaseous products, which is 2, minus number of moles of gaseous reactant, that's 1. So 2 minus 1 comes out to be 1. Look at this particular reaction. Calculate its delta Ng. Calculate its delta Ng. For the calculation of delta Ng, do I have to consider solid? No, I only need to consider gases. Start with the product. Its coefficient here is 1. Its coefficient here is 1. 1 plus 1 is 2. So 2 minus 0 comes out to be 2 only. So delta Ng for the reaction is 2. Okay. Delta Ng for the reaction is 2. All right. Look at this particular reaction, for example. If I ask you to calculate delta Ng for this reaction, number of moles of gaseous products, that is only 1. Nothing to do with this, nothing to do with this. So it's 1 only, right? For this particular reaction, calculate delta Ng. Delta Ng has to be equal to number of moles of gaseous product, which is 1, minus number of moles of gaseous reactants, which is 3 by 2. The value comes out to be minus 1 by 2. So this is delta Ng for this particular reaction. My dear students, remember, in short, in order to calculate delta Ng, what do we need? Number of moles of gaseous products minus the number of moles of gaseous reactants. That's how you are going to calculate delta Ng for a particular reaction. I hope all this stuff is absolutely clear to every one of you. Okay? All clear till here? All clear till here, people? Everybody. All clear till here? This is how exactly you guys are going to calculate delta Ng for the reaction. Now comes one of the most important topics of this chapter, that is the relation between Kp and Kc. See guys, relation between Kp and Kc for a particular reaction. Understand. Let's say I've got the balanced equation as N1A gas in equilibrium with, for example, N2B gas. Let's say this is one balanced chemical equation. So first of all, if this is a balanced chemical equation, if I ask you, what about delta Ng for this reaction? Delta Ng. Delta Ng will be number of moles of gaseous products minus number of moles of gaseous reactants. So it has to be N2 minus N1. It has to be N2 minus N1. This is delta Ng for the reaction, N2 minus N1. Now, my dear students, if I ask you to write the expression for Kp for the reaction, you should be in a position to write the expression for Kp. It's going to be partial pressure of B at equilibrium raised by N2 divided by partial pressure of A at equilibrium raised by N1. Similarly, if I ask you to write the expression for Kc, it's going to be concentration of B at equilibrium raised by N2 divided by concentration of A at equilibrium raised by N1. Okay, expression for Kp and Kc. Now, first of all, what is this partial pressure of B and what is this partial pressure of A? Let me first of all give you the elementary idea of what these partial pressures are. My dear students, look at this particular reaction. This reaction will be definitely taking place in a container, in a closed container, right? Definitely. At time t is equal to 0, if I ask you, at time t is equal to 0, how many gases are there in the container? At time t is equal to 0, how many gases are there in the container? I would say there will be only one gas in the container at time t is equal to 0. So entire pressure of the system is due to gas A at time t is equal to 0. As the reaction proceeds, moles of A are going to decrease with time, moles of B are going to increase with time. There would be a scenario when rate of forward and backward will be equal. At that point of time, moles of A and B would become fixed, would become constant. And that is something when you say equilibrium is established in the reaction. So if I ask you at equilibrium, whether there will be one gas or two gases in the container, I would say at equilibrium, there will be two gases present in the container. There are some moles of gas A left in the container, some moles of gas B which have formed, right, at equilibrium. So at equilibrium, there are two gases in the container. At equilibrium, there is a mixture of gas. There's a mixture of gas in the container at equilibrium. So at equilibrium in the container, there are some moles of A left, there are some moles of B formed. And the moles of A and B are fixed. They're constant. They're not going to change now. Okay? There is a gas A as well as gas B present in the container at equilibrium, mixture of gas. I'm assuming the total pressure of this particular mixture is PT. Let's say this PT represents total pressure. PT represents total pressure of the mixture at equilibrium. Okay. Now people, this total pressure of the mixture at equilibrium, will it only be due to A, B? Will it only be due to B, or both would have contributed? I would say A as well as B, gas A as well as gas B, both would have contributed towards the total pressure of the mixture. And Dalton's law says that total pressure of the mixture is basically the sum of partial pressures. So total pressure of the mixture at equilibrium will be the partial pressure of A at equilibrium plus partial pressure of B at equilibrium. What does that mean? That means, what is this PA? This PA represents contribution made by gas A. Contribution made by gas A towards the total pressure of the mixture at equilibrium. This PB represents contribution made by gas B towards the total pressure of the mixture at equilibrium, which is what you call as partial pressures. You call them as partial pressures. And if ever you would have studied how to calculate partial pressure of a gas, for example, I have to calculate partial pressure of gas A at equilibrium. Partial pressure of a gas in the mixture is always equal to total pressure of the mixture multiplied by mole fraction of that gas in the mixture. Similarly, if sometimes I have to write partial pressure of B at equilibrium will be equal to total pressure of the mixture at equilibrium multiplied by mole fraction of gas B in the container at equilibrium. Remember these two things. Okay? Remember these two things. Now guys, understand what exactly I'm going to say. This was just the quick idea of the Dalton's law. I believe this is clear. Okay? Tell me now one thing. You know the equation PV is equal to nRT, your ideal gas equation? Absolutely. Can't you write it like this? P is equal to N divided by VRT? Yes, we can do. P is equal to N by V is concentration. N by V is concentration. So P is equal to concentration RT. So can I say PA, partial pressure of A, will be equal to concentration of A, RT. Partial pressure of B is equal to concentration of B. With it, you'll be writing RT. So people, we are done almost. So Kp has to be equal to, instead of partial pressure of B at equilibrium, I'll write, instead of partial pressure of B, I'm writing concentration of B at equilibrium multiplied by RT whole raised power what? Whole raised power N2 divided by partial pressure of A. Instead of partial pressure of A, I'll write concentration of A at equilibrium RT whole raised power what? Whole raised power N1. Now people, if you analyze things properly, I'll write it like this. Concentration of B at equilibrium raised power N2 divided by concentration of A at equilibrium raised power N1. This is RT raised power N2, RT raised power N1. So I'll be writing RT raised power N2 minus N1. Now, we are almost done. I would say Kp is equal to this particular term. This particular term, if you see carefully, this particular term I assumed already as Kc. So this is your Kc multiplied by RT raised power N2 minus N1. Since I have got a gaseous phase reaction, N2 minus N1 represents delta Ng here. So this RT raised power N2 minus N1, and for this gaseous phase reaction, that's delta Ng. So my result came. Kp is equal to Kc RT raised by delta Ng for this particular gaseous phase reaction. I believe I'm clear with this. Yeah? Right, people? Remember this particular expression, Kp is equal to Kc RT raised by delta Ng. I'm writing it over here again, right? This is the relation between Kp and Kc for a reaction. Kp is equal to Kc RT raised by delta Ng for the reaction. Where R is a constant, gas constant, right? T is the temperature at which reaction takes place. Perfect. I hope I'm clear. Now, guys, there are a few things which you need to understand here. What are those things? First of all, remember, if delta Ng of any reaction is 0, any reaction whose delta Ng is 0, anything is power 0 is 1, I would say its Kp and Kc would be always equal. That particular reaction whose delta Ng is equal to 0, right? Its Kp and Kc would be always equal. Always equal. Okay? Now, people, see this R which you are seeing over here, the R value which you are seeing, the gas constant, it is equal to 1 by 12. Its value is 1 by 12 atm liter per Kelvin per mole. You know it. Or you can write 0.0821. R is equal to 1 by 12 atm liter per Kelvin per mole. Now, guys, here I've got certain cases. What are the cases? One by one, I'll make you understand. If R is equal to, see, R is already equal to 1 by 12. Let's say temperature at which the reaction is taking place, if that T is 12 Kelvin, if T is equal to 12, if T is equal to 12, R multiplied by T will be, R is 1 by 12, T is 12, 12 cancel, R multiplied by 12, 1 by 12 into 12 will be 1, RT value will be 1. And if RT is 1, 1 raised by anything is always 1. If 1 raised by anything is always 1, that means Kp and Kc for that particular reaction would be equal. So, this is your conclusion number 1. If the reaction is carried out at 12 Kelvin, as per this particular expression, do you see? If the reaction is carried out at 12 Kelvin, its Kp and Kc would be equal, irrespective of what its delta Ng is. Irrespective of what its delta Ng is. Now, second point. If, for example, the reaction is carried out at temperature greater than 12 Kelvin. If the reaction is carried out at temperature greater than 12 Kelvin, so R multiplied by T. R is 1 by 12, T is greater than 12, right? T is greater than 12. Imagine T is 13. So 13 into 1 by 12. 13 into 1 by 12 will be 13 by 12, which is greater than 1. RT is greater than 1. If the reaction is carried out at temperature greater than 12 Kelvin, therefore RT at that point of time will be greater than 1. So this term is greater than 1. This term I'm assuming right now is greater than 1. It is greater than 1. Okay. Now here we have got certain cases. If RT is greater than 1, the first case. In this particular scenario, if delta Ng is 0, if delta Ng is 0, Kp Kc would be equal. Nothing to do with the RT value. If, for example, delta Ng is greater than 0, if delta Ng is greater than 0, this value is already greater than 1. This value is greater than 1. And this value is greater than 0. Mathematically, we can say at this particular point of time, your Kp would be greater than Kc. And if by chance delta Ng for the reaction here is less than 0, RT value is already greater than 1. This is greater than 1, but this is less than 0. So mathematically, when you see it, Kp would be less than Kc. Okay, this is one more conclusion. Similarly, my dear students, if, for example, the same reaction is carried out at temperature less than 12 Kelvin, I would say the value of R multiplied by T will be less than 1. If temperature is less than 12 Kelvin, so R multiplied by T, it will be less than 1, right? Now here, look at the different scenarios. First scenario is pretty much common. If delta Ng is equal to 0, therefore Kp and Kc would be equal because anything raised by 0 is 1. Perfect. Now here, the second point. If in this particular case, delta Ng is greater than 0, see, RT is less than 1. This particular term is less than 1. And this particular term is greater than 0. So mathematically, I would say Kp would be less than Kc in this particular case. Similarly, if by chance delta Ng is less than 0, similarly you can check Kp would be greater than Kc in this particular case. So these are different scenarios from which questions can be asked in your NEET examination. All right, people. Am I clear with this? Am I clear with this, people? Quick, quick, quick. Everybody. Am I clear with this? I believe yes. Now, what is the general relation? Kp is equal to Kc RT raised by delta Ng here for a gaseous phase reaction. Okay, for a gaseous phase reaction. Now, my dear students, it has got a logarithmic form as well. It has got a logarithmic form as well. See what that logarithmic form is. See, you know, your Kp is nothing but it is Kc RT raised by delta Ng for a gaseous phase reaction. For a gaseous phase reaction. My dear students, let's do one thing. Let's multiply this equation throughout by log. When you multiply this equation throughout by log, it becomes log of Kp is equal to log of Kc RT raised by delta Ng. Okay, so this can be written like this: log of Kp is equal to log of m into n. It is nothing but log of m plus log of n. Log of m into n is nothing but log of m plus log of n. So I can write it as log of Kp is equal to, this is log of Kc plus log of m raised by n is n log m. So delta Ng comes to the front. Here you are going to write log of RT. So this is the logarithmic form of the same equation. This is the logarithmic form of the same equation. If this is the logarithmic form of the equation, if I ask you to plot a graph here, between log of Kp versus log of RT, you can do that. You can do that. Log Kp you are plotting along y-axis. Log RT you are plotting along x-axis. So this is going to be your m. This is going to be your c. The sign here is plus and here it's equal to. Y is equal to mx plus c. Y is equal to mx plus c. Y is equal to mx plus c is going to be a straight line like this, right? And what about its slope? Its slope here is going to be delta Ng, which I'm right now considering to be positive. The delta Ng value here is positive, right? That's why it's becoming y is equal to mx plus c. If delta Ng was negative, then the equation would have been y is equal to minus mx plus c. Then the graph would have changed accordingly, right? Perfect. So this is the graph over here between log of Kp versus log of RT when the slope, when delta Ng for the reaction is positive. If delta Ng would be negative, then it's going to be minus mx plus c. Then the graph is not going to be upwards, it's going to come downwards, basically. Straight line with negative slope. I hope I'm clear with this. So this was the relation between your Kp and Kc, right, people? Now, before showing you its questions, etc., there is one more topic which you need to know first of all. That is the relation between Kp and Kx. A relation between Kp and Kx. Okay. Again, I'll use the similar approach to get the relation between Kp and Kx. My dear students, let's assume we have got a gaseous phase reaction like this. Let's say we have got a balanced chemical equation, N1A gives N2B. It's a gaseous phase reaction which is carried out at some temperature. Okay. Now, my dear students, can I write the expression for Kp over here? We can do that. It's going to be partial pressure of B at equilibrium raised by N2 divided by partial pressure of A at equilibrium raised by N1. If I want to write the expression for Kx, Kx is going to be mole fraction of B at equilibrium raised by N2 divided by mole fraction of A at equilibrium raised by N1. Okay. Now, my dear students, can I write it like this? Kp is equal to, what is this Pb? It is partial pressure of B at equilibrium. Instead of partial pressure of B at equilibrium, can I write total pressure of the mixture at equilibrium multiplied by mole fraction of B at equilibrium, right? Instead of partial pressure of B at equilibrium, I wrote total pressure of the mixture at equilibrium multiplied by mole fraction of B at equilibrium raised by what? Raised by N2 divided by partial pressure of A at equilibrium will be total pressure of the mixture at equilibrium multiplied by mole fraction of A at equilibrium. Whole raised by stoichiometric coefficient, that's N1. Now, a bit of calculation is needed here. See, it's chi b raised per n2, chi a raised per n1. Chi b raised per n2, chi a raised per n1. Chi b raised per n2, chi a raised per n1. Instead of this particular term, I'll be writing kx. Or let me write it in a good way for you so that you can understand. So mole fraction of b at equilibrium raised per n2 divided by mole fraction of a at equilibrium raised per n1. This is pt raised per n2, pt raised per n1. So this is going to be pt at equilibrium raised per n2 minus n1. Okay. This particular term is nothing, is what you call as kx multiplied by total pressure of the mixture at equilibrium n2 minus n1. I'm calling as delta n over here. So I got a direct result, which I would want every one of you to remember from now onwards. Your Kp is always equal to Kx, total pressure of the mixture at equilibrium raised by delta Ng, if you have got a gaseous phase reaction. This is the relation between Kp and Kx. This is the relation between Kp and Kx, people. I believe I'm clear till here. Right? I believe I'm clear till here. Your Kp is equal to Kx multiplied by total pressure at equilibrium multiplied by delta raised by delta Ng. This is the result between Kp and Kx. All right. Similarly, my dear students, you can plot a conclusion here. If by chance you have got any reaction whose delta Ng is 0. If by chance you have got any reaction whose delta Ng is 0. If delta Ng is 0, anything raised power 0 is 1. So you can say Kp and Kx for that particular reaction has to be equal. Kp and Kx for that particular reaction has to be equal. One more thing. Yeah. Similarly, people, we can make a logarithmic form of it as well. If you want, we can convert this into the logarithmic form. Your Kp is equal to Kx. Your Kp is equal to Kx, total pressure of the system at equilibrium raised by delta N. Right? This is the equation which we have. Now, what I'll be doing, I'll be multiplying this equation throughout the log. It becomes log of Kp. I'll be writing the final expression. It's going to be log of Kx plus delta Ng, and it's going to be log of total pressure of the mixture at equilibrium, right? So this is the logarithmic form of the same equation. This is the logarithmic form of the same equation. This is the logarithmic form of the same equation. Now, guys, over here, if you want to plot a graph, let's say you want to plot a graph between log of Kp and log of Pt. What will be the nature of the graph? Understand carefully. Log Kp you are plotting along y-axis. Log Pt you are plotting along x-axis. I'm assuming delta Ng as positive. So this becomes your m, slope. This is your c. Sign here is positive. Here it's equal to y is equal to mx plus c. Y is equal to mx plus c. Y is equal to mx plus c means straight line with the positive slope. And if you want to get its slope, slope means the value of m. M here is delta Ng. And I'm assuming delta Ng here is greater than 0. Right? If delta Ng is greater than 0, then only the equation becomes y is equal to mx plus c. If delta Ng is negative, the equation would become y is equal to minus mx plus c. So at that time, it will be straight line with negative slope. I hope this is clear. And similarly, if you want to know this intercept here, you can know that intercept means the value of c, and the value of c over here, if you can see, it is log of kx, right? Okay, over here, if you wanted to know the intercept, I forgot to make it. Intercept here is c basically, and c is nothing but log of kc. Perfect, guys. I believe till here it's clear. So this was your result between between your Kp and Kx. All right. Now, guys, if you see carefully, I told you your Kp is equal to Kc RT raised by delta Ng for a gaseous phase reaction. And few minutes back only I told you your Kp is equal to Kx multiplied by Pt at equilibrium raised by delta Ng. So what can you conclude from this equation 1 and equation 2? What can you conclude from this equation 1 and equation 2? Kp is this, Kp is this. So I would say my Kc RT raised power, my Kc RT raised power delta Ng, this will be equal to Kx Pt at equilibrium raised power delta Ng, right? Or you can say Kc is equal to Kx, you are writing as such. This is Pt at equilibrium, whole divided by. This is RT, and the power is common here, that is delta Ng. So this is the result between Kc and Kx as well. So first one was Kp Kc, second one was Kp Kx, third one is Kc Kx. And here you can make conclusions. Conclusion is, if for example delta Ng for the reaction is 0, if delta Ng is 0, so this whole term becomes 1. At that point of time, your Kc is equal to Kx. Or guys, if I just want to write one statement. So we saw first of all, if delta Ng is equal to 0, Kp Kc is equal. Delta Ng is 0, Kp Kx equal. Delta Ng is 0, Kc Kx equal. So in short, I would say, for those particular reactions which have got delta Ng equal to 0, their Kp, Kc and Kx are equal. I hope I'm clear with this. And my dear students, at the same time, you can make the logarithmic form of this as well. And if you want to make its logarithmic form, you just have to multiply with log on both the sides. Your final expression will be log of Kc is equal to, it's going to be log of Kx plus delta Ng. It's going to be log of Pt at equilibrium divided by RT. This is the logarithmic form here. And if this is the logarithmic form, then definitely you can make a graph as well. Definitely you can make a graph over here as well. The log is going to be between log of Kc. The graph is going to be between log of Kc versus log of Pt equilibrium divided by RT. This is something which you are plotting along y-axis. This is something which you are plotting along x-axis. This becomes your M. This becomes your C. Sign is positive here. I'm assuming delta Ng is positive. So y is equal to mx plus c. Again, it's going to be a straight line like this. What about its slope? The slope here is going to be equal delta Ng if delta Ng is greater than 0. If delta Ng is negative, it becomes y is equal to minus mx plus c. So the graph is going to be straight line with a negative slope. I hope this particular stuff till here is clear to every one of you. And if this is clear, guys, can you solve these sort of basic questions? You should be in a position to solve them. You should be in a position to solve these sort of basic questions which we have here. Understand what these questions are. See guys, I'm giving you different reactions. Write the expression of Kp in terms of Kc. We have to write Kp in terms of Kc. If you look at the first reaction, in the first reaction, first of all, tell me the value of delta Ng. Delta Ng for the first reaction is number of moles of gaseous products minus number of moles of gaseous reactants, which is 1 plus 1, 2. So delta Ng is 0. So if delta Ng for the first reaction is 0, I would say its Kp is nothing but it is equal to Kc. So your Kp and Kc is equal in this particular case. Okay. Similarly, look at the second reaction. For the second reaction, what is the value of delta Ng? Delta Ng is number of moles of gaseous products, which is 1 plus 1, 2, minus 1. Value comes out to be 1. If delta Ng is 1, I would say your Kp is equal to Kc RT raised by delta Ng, that's 1. That's the relation between Kp, Kc here, right? Look at the third reaction, people. For the third reaction, calculate delta Ng. Delta Ng is nothing but number of moles of gaseous products, that's 2, minus number of moles of gaseous reactant, which is 3 plus 1, 4. So 2 minus 4 comes out to be minus 2. If delta Ng is equal to minus 2, I would say Kp is nothing but it is Kc RT raised by minus 2. Okay. Similarly, fourth one, calculate delta Ng. Delta Ng is equal to number of moles of gaseous product, which is just 1. There is no gaseous reactant otherwise. This is nothing. So I would say here Kp is equal to Kc RT raised by delta N, that's 1. So you have written Kp in terms of Kc in all these equations. Yeah? Right, people? I hope whatever stuff I've told you till now, it's absolutely clear to you. And there is one more small topic, that is units of Kp and Kc. How do we calculate units of Kp and Kc? Well, guys, I just want you to understand it like this. For example, I've got the reaction as N1A gas in equilibrium with N2B gas. Okay, this is the reaction. N1A gas in equilibrium with N2B gas, for example. Well, first of all, I want you guys to write the expression for Kc here. Kc expression is going to be concentration of B at equilibrium raised by N2 divided by concentration of A at equilibrium raised by N1. If I ask you about the Kp expression, Kp is going to be pressure of B at equilibrium raised by N2 divided by pressure of A at equilibrium raised by N1. If I ask you what is the delta Ng for this reaction, since I've taken a gaseous phase reaction, it's a gaseous phase reaction, its delta Ng is going to be N2 minus N1. Its delta Ng is going to be N2 minus N1. It's a gaseous phase reaction. Okay. Now, guys, if you want to know the units of Kc, this is concentration here. Concentration means moles by volume. So, the unit of the numerator here is moles per liter. Unit of the numerator is moles per liter. Raised by what? N2 divided by. Denominator is also in moles per liter because denominator also says concentration raised by N1. So, Kc units are going to be moles per liter raised by N2 minus N1, and for the above gaseous phase reaction, that is delta Ng. So Kc is nothing but it's moles per liter raised by delta Ng for the gaseous phase reaction. Okay, for the gaseous phase reaction. Similarly, here for example, you have to calculate the unit of Kp. Let's say the pressure I'm taking in atm. This is atm raised by N2, atm raised by N1. So it's atm raised by N2 minus N1, and N2 minus N1 for the above reaction, I'm writing it as N2 minus N1, I'm writing as delta Ng for the above gaseous phase reaction. So the units of Kp and Kc for a gaseous phase reaction, the units of Kp and Kc for a gaseous phase reaction, it depends on what? It depends on the value of delta Ng. I believe I'm clear with this. Yeah? Is it clear, guys? Is it clear? Is it clear? Quick. Is it clear? I hope this is clear to everyone. And if this is clear, you are going to answer me a few questions. If this is clear, you are going to answer me a few questions. This is one of the questions which is asked in your NEET examination. Understand the level. Understand the level, guys. Understand the level here. In the following equilibrium reaction, we are given with a reaction which is 2 times A in equilibrium with B plus C. Okay. The equilibrium concentrations of A, B and C are given. So, concentration of A at equilibrium, concentration of B at equilibrium, as well as concentration of C at equilibrium. All these three things are given to me. And what is the concentration of A at equilibrium? As per the question, it's 1 into 10 raised power minus 3 molar. Concentration of B at equilibrium is 2 into 10 raised power minus 3 molar. Concentration of C in the container at equilibrium is 3 into 10 raised power minus 3 molar. As per the question, what am I supposed to calculate? I want to get the value of Kc for this particular reaction. The question is done, guys. Nothing to think about this. Right? Just the expression for Kc. And Kc expression is nothing but it is concentration of B at equilibrium raised power coefficient 1, concentration of C at equilibrium raised power 1 divided by concentration of A at equilibrium raised power 2. Now, my dear students, concentration of B at equilibrium, that already you know, 2 into 10 raised power minus 3. Concentration of C at equilibrium is how much? 3 into 10 raised power minus 3. Divided by concentration of A at equilibrium, that's 1 into 10 raised power minus 3 raised power 2. Raised power 2, right? So the final answer is going to be 10 power minus 3, 10 power minus 3, and this square gets cancelled. So Kc value is nothing but, it is 6. Kc value is nothing but 6. Okay? Kc value is nothing but 6. My dear students, imagine that this was in aqueous state. This was also in aqueous state. This was also in aqueous state, right? Then what would have been the units of Kc? What would have been the units of Kc, right? If none of them is in gaseous state, so Kc units will be at that time moles per liter, not raised by delta Ng. At that time, it will be raised by delta N. Delta N, right? Number of moles of products minus number of moles of reactants. Moles of products minus moles of reactants. And you'll be considering all the reactants products there, which are going to be in aqueous state. 1 plus 1, 2, 2 minus 2, 0. So delta N is 0, anything raised power 0 is 1. So your Kc becomes unitless in this particular case. Okay? I hope I'm clear. This is when When do you, this is the general formula, moles per liter raised by delta N. Similarly, for such a reaction, your Kp will be equal to Kc RT raised by delta N, not delta Ng at that time. I hope I'm clear with that. If I'm clear, tell me the answer of this question. This is your, I think 1 or 2 years back, this same question was asked in your JEE mains examination. And you can see its level. You're given with a reaction. All are in gaseous phase. You just have to get the ratio of Kp and Kc. You know, your Kp and Kc relation. Kp is equal to Kc RT raised by delta N. Here it's gaseous, so delta Ng. So Kp divided by Kc will be equal to what? Kp divided by Kc will be equal to RT raised by delta Ng is 1. Delta Ng is number of moles of gaseous product minus number of moles of gaseous reactant. 1 plus 1 by 2 is 3 by 2. The value comes out to be minus 1 by 2. So the final answer is going to be RT raised by minus 1 by 2. Right? Kp by Kc is something which I was supposed to calculate. Done and dusted. Right? Similarly, look at this particular question. This is again one more question that can be asked on different type of question and simple at the same time. In which of the following Kp and Kc are not equal? In which of the following Kp and Kc are not equal? Calculate delta Ng for this reaction. Number of moles of gaseous products 1 plus 1 2 minus gaseous reactants 2. So 2 minus 2 is 0. If delta Ng is 0, that means Kp Kc are equal here. In the second case also your delta Ng is coming out to be 0. So Kp Kc are equal here also. In the third case, again you can calculate delta Ng and you'll observe the value of delta Ng is 0 here also. If delta Ng is 0, again your Kp Kc is equal. In the last case, calculate delta Ng. Delta Ng is equal number of moles of gaseous products, which is 2, minus number of moles of gaseous reactant, that's 1. This is something which you are not going to consider because this is in solid state. So 2 minus 1 is 1. So delta Ng is non-zero. And when delta Ng is non-zero, at that point of time, your Kp and Kc won't be equal, right? So it has to be option D, which is the final answer of the question. Absolutely, guys. All of you are perfectly right. Amazing. Amazing. Tell me the answer of this very simple and basic question. Value of Kp. What will be the expression for Kp? See, this is solid. Don't consider it. Solid, don't consider. Carbon dioxide gas. So Kp is going to be partial pressure of carbon dioxide at equilibrium raised per stoichiometric option 1. Is there any option like this? Right? Nothing to think. Nothing to think, people. Nothing to think. Can you solve this question? Again, simple and basic. Again, simple and basic. The rate constant of forward and backward reaction is given. They're asking you to calculate equilibrium constant. Kf is given to me as 1.1 into 10 raised power minus 2. Kb is given to me as 1.5 into 10 raised power minus 3. What are we supposed to calculate? They're asking me to calculate equilibrium constant. What is equilibrium constant actually? In reality, we discussed equilibrium constant. It is the ratio of rate constant of forward to that of backward. Rate constant of forward is 1.1 into 10 raised power minus 2. Rate constant of backward is 1.5 into 10 raised power minus 3. All this, get the value of equilibrium constant. Nothing to think in this particular question as well, right? Okay, so these are the basic questions which I solved on the basis of the concepts that we have discussed till now. Okay? I hope I'm clear. So let's take a break here. What's the time? It's 7:10. So I would say break till it is 7:10. 7:40. And at 7:40, guys, I would want every one of you to be back because now the chapter is going to start. Till now, whatever I taught you till now, that was all basics. That was all fundamental, right? Okay. So I hope your basics is now stronger than before. And now it's going to be the time for the, complicated things to be conquered after the break. So I'll see you exactly at 7:40 and I would want every one of you to be here on time. See you in a while. Take care. Is everyone back? Yeah, back on time. Is everyone back on time? So guys, tell me in the chats, whatever stuff we discussed till now, is every single thing clear? Say it in the chats quickly. Whatever things we discussed till now, is every single thing clear? No, I did not have my dinner yet. I'll have it afterwards. Quickly, people. Whatever stuff we discussed till now, is every single thing clear to every one of you? I would want the answers in the chats from everyone. All right. Perfect. Dinner break will be at almost 10. Yeah, almost 10. Perfect, people. So let's get going then. Let's get started with some other important stuff. What is that? Let's have a look. I'm marking the heading here as characteristics of equilibrium constant. Characteristics of equilibrium constant. From this particular topic also, questions are frequently asked. Characteristics of equilibrium constant. Now, my dear students, there are certain important characteristic features of equilibrium constant which we need to understand, and we need to remember them and apply them in the questions as well. Now, what are those characteristic features of equilibrium constant? Let's get to know about them one by one. My dear students, the first point which I'm mentioning over here, I would say equilibrium constant does not depend upon the initial concentration of reactants. The first and the important point which I would want every one of you to remember. Your equilibrium constant of a particular reaction, it does not depend on the initial concentration of reactants. How can we understand this? Say, for example, you have got the reaction like this. N1A in equilibrium with N2B. Let's say this is the reaction. Okay. If I want to write its equilibrium constant expression, I can do that. Its equilibrium constant Kc, for example. Its equilibrium constant Kc, for example, will be equal to concentration of B at equilibrium raised by N2 divided by concentration of A at equilibrium raised by N1. My dear students, if you look at this particular expression, can I say, in order to know the equilibrium constant Kc value, we need to know concentration of reactant and product at equilibrium. We need to know the concentration of reactant and product at equilibrium to get the equilibrium constant. So what does that mean? That means we have got nothing to do with the initial concentration of reactant, right? We have got nothing to do with the initial concentration of reactants. We have got everything to do with the concentration of reactants and products at equilibrium in the container. Okay, point number one. My dear students, point number two. Equilibrium constant Equilibrium constant does not depend upon the catalyst. Equilibrium constant does not depend upon the catalyst. I believe all of you would be knowing what a catalyst is. Catalyst is a substance that alters the rate of reaction, that either increases or decreases the rate of the reaction. Okay? And that catalyst which increases the rate of reaction, that is what you call as positive catalyst. Right? So what a positive catalyst does, positive catalyst increases the rate of reaction. And similarly, if I talk about the negative catalyst, it decreases the rate of reaction. So what happens to equilibrium constant when we add the catalyst? I'm talking about the positive catalyst. My dear students, what the positive catalyst does, remember it. I would say a positive catalyst increases the rate of forward and rate of backward reaction. A positive catalyst increases the rate of forward and rate of backward reaction by equal amounts. So positive catalyst, it is going to increase the rate of forward as well as the rate of backward reaction by equal amounts, due to which equilibrium is established in the reaction quickly. That's all. Due to which equilibrium is established quickly in the reaction. So a positive catalyst, it increases the rate of forward as well as backward reaction, due to which equilibrium in the reaction is established quickly, right? And it does not matter whether equilibrium in the reaction is established quickly or like sooner or later, equilibrium concentrations of reactants and products, they are still going to remain the same. Whether equilibrium is established in the reaction fast, whether equilibrium in the reaction is established in the reaction sooner or later, it has got nothing to do with the equilibrium concentrations of the reactants. They are still going to remain the same. If equilibrium concentrations of reactants and products are going to remain the same, that means your equilibrium constant, it is going to remain the same. So a catalyst does not change the equilibrium constant of the reaction. It just speeds up the forward and backward reaction, due to which equilibrium is established in the reaction quickly. And does not matter whether equilibrium in the reaction comes sooner or later, equilibrium concentrations of reactants and products, they are going to remain the same. Nothing is going to happen to them. Therefore, equilibrium constant remains unchanged. Okay, this is one more important point. My dear students, there is one more thing which I would want every one of you to remember. Okay, what is that? That is equilibrium constant. Equilibrium constant of a particular reaction. Equilibrium constant of a particular reaction depends only on temperature. Equilibrium constant of a reaction, it depends only on what? It depends only on temperature. And this is the point which basically we are going to study when I'll be teaching you the Le-Chatelier principle. In Le-Chatelier principle, I'll be letting you know in detail how your equilibrium constant depends on temperature. Right now, you just can take down two things which I'll be explaining later. What are those two things? First one, in case of your endothermic reactions, in case of the endothermic reaction, your equilibrium constant is directly proportional to temperature. And in case of your exothermic reactions, in case of your exothermic reaction, your equilibrium constant, that is inversely proportional to temperature. Okay, this is something which will be detailed, discussed when I'll be teaching you the Le-Chatelier principle. Okay, perfect. So remember it for now. Equilibrium constant for the endothermic reaction, that's directly proportional to temperature, and equilibrium constant for the exothermic reaction, it is inversely proportional to temperature. My dear students, there are From this particular statement, there are some graphs which are asked between equilibrium constant and temperature. Certain graphs are asked. Well, what all graphs are asked? Before showing you the graphs, I would want you guys to remember one equation, one important equation, guys. Okay, one important equation I would want every one of you to remember. That equation is like this. Ln of equilibrium constant is equal to minus delta H divided by RT plus delta S divided by R. This is one of the equation which I would want you guys to remember for now. And this equation will be discussed in detail when I'll be teaching you effect of temperature on equilibrium constant in the Le Chatelier principle in this chapter itself. Okay, this is first of all the equation which I would want you guys to remember. Now from this equation, certain graphs can be asked. What kind of graphs exactly? Have a look. My dear students, one thing. For example, I have to make a graph between, let's say I have to make a graph between ln of equilibrium constant versus 1 upon T, 1 upon temperature. Let's say I have to make it for the endothermic reaction. So first of all, in case of endothermic reactions, you must be knowing delta H value, enthalpy change. In case of endothermic, that's positive. Enthalpy change, delta H is positive. If delta H is positive for endothermic, so that positive and this negative makes this negative overall. So I can write the equation like this. Ln of KEQ is equal to minus delta H divided by R multiplied by 1 by T plus delta S divided by R. This is the equation which is valid for what? Which is valid for the endothermic reaction. Because for the endothermic reaction, delta H is positive. If delta H is positive, positive negative makes it negative only. Now people, if you look carefully, ln of KEQ, you're plotting along y-axis. Okay. 1 upon T, you're plotting along x-axis. So this whole term becomes your M. The sign here is minus. And this term becomes your C. The sign here is plus. Y is equal to minus mx plus C. And you know y is equal to minus mx plus C is a straight line with a negative slope. And if I ask you, what will be the slope of this graph? Slope will be the value of M here, which is minus delta H by R. Minus delta H divided by R. And this particular graph, it is valid for what? It is valid for your endothermic reaction. Okay. Similarly, my dear students, if you talk about your exothermic, if you have got the exothermic reaction, in case of exothermic reaction, if you'll be having the exothermic reaction, in case of exothermic reaction, the value of delta H is negative, right? In case of exothermic, the value of delta H is negative. If the value of delta H is negative, so negative makes it positive here. Negative makes it positive. So I would say ln of KEQ is equal to negative makes it positive. So it becomes delta H divided by R multiplied by 1 upon T plus delta S divided by R. Now guys, have a proper eye on this particular thing. See exactly. For example, I need to make a graph for the exothermic reaction between what? Between ln of equilibrium constant versus 1 upon temperature. Look at it properly. Ln of KEQ, I'm plotting along y-axis, right? 1 upon T, I'm plotting along x-axis. This becomes your M. This whole term becomes your M. This becomes your C. Sign in the middle is positive and this is equal to y is equal to plus mx plus c. Y is equal to mx plus c means? Y is equal to mx plus c means straight line with a positive slope, and its slope, as you can see, slope is basically the value of M, and M is nothing but delta H divided by R. Delta H divided by R. So these are the two graphs which I would want you guys to remember when it comes for the endothermic and exothermic reactions. In detail, the effect of temperature on equilibrium constant, I'll be teaching this stuff in your Le Chatelier principle after some time. Okay, right? Just these things you can remember for now. How these things come, you'll get the idea in some time when I'll be discussing Le Chatelier principle with you, right? In case of endothermic, equilibrium constant is directly proportional to temperature. In case of exothermic, equilibrium constant is inversely proportional to temperature. From where it comes, you'll get the idea in the Le Chatelier principle. Okay. So right now, what am I discussing? I'm discussing characteristics of equilibrium constant, right? The first one was equilibrium constant does not depend on the initial concentration of reactant. Equilibrium constant has got nothing to do with the catalyst added. Equilibrium constant of a particular reaction, it depends only on the temperature, right? And for endothermic, it's directly proportional. For exothermic, it's inversely proportional. That's all. And these are the two important graphs which are asked. Next point, which comes in equilibrium constant. I would say equilibrium constant, it depends on the stoichiometric. Equilibrium constant depends on the stoichiometric representation. It depends on the stoichiometric representation of the reaction. And how exactly? Have a look. See guys, understand. The first point here, equilibrium constant, it depends on the stoichiometric representation of the reaction. Understand what exactly I'm going to say. The first point here, I'll write, if a reaction which is at equilibrium, if the reaction is reversed, remember when a reaction is reversed, comma, its equilibrium constant is inversed. Its equilibrium constant is inversed. For example, what does that mean? Let's say this is your reaction, A in equilibrium with B, okay? If I write its equilibrium constant expression Kc, it is concentration of B at equilibrium raised power 1, concentration of A at equilibrium raised power 1. Okay? Let's say this value is equal to 10, for example. Let's say this Kc value is equal to 10 for this reaction. Now, my dear students, if I reverse the same reaction, and I'm asking you to write the equilibrium constant expression for this reaction, you'll be writing it like this. Concentration of A at equilibrium raised power 1, concentration of B at equilibrium raised power 1. If B by A was 10, that means A by B will be equal to 1 by 10. So what is happening if you see properly? This 10 was Kc. This 10 was the initial Kc. So this will be 1 upon initial, that is Kc. So when I reverse the reaction, what is happening to equilibrium constant? When I'm reversing the reaction, equilibrium constant is inversed, right? This is the direct result which I would want every one of you to remember. Okay? When you reverse the reaction, which is at equilibrium, you have to inverse its equilibrium constant. Point number 1. Point number 2, my dear students. On multiplying a reaction by some number, comma, that number goes to the power of its equilibrium constant. What does that mean? That means, for example, you have got the reaction like this. A gives B. Let's say its equilibrium constant is, for example, K1. Let's say its equilibrium constant is K1. Now, my dear students, if I'll be multiplying this reaction by some number, let me multiply this reaction by N. Now, it becomes Na in equilibrium with Nb. And when you multiply a reaction by some number, that number goes to the power of its equilibrium constant. Now, I'll say the equilibrium constant of this particular reaction won't be K1. It is K1 raised power N. It's going to be K1 raised power N. Okay? This is one more important point which you need to know, which you need to remember. Point number 3. Point number 3 here, guys. Point number 3. On adding the reactions which are at equilibrium, remember their equilibrium constants are to be multiplied. Their equilibrium constants are to be multiplied. What does that mean? For example, you got the reaction like this. A in equilibrium with B. Let's say its equilibrium constant is K1. Let's say you got one more reaction, C in equilibrium with D. Its equilibrium constant is, for example, K2. If I add these two reactions, the net reaction which I get, that's going to be A plus C gives B plus D. Now, if I ask you, what is going to be the equilibrium constant of this reaction? Remember, since this reaction you have made when you have added these two, and when you add these two reactions, their equilibrium constants are to be multiplied. So it's going to be K1 multiplied by K2. It's going to be K1 multiplied by K2. Remember these 3 points from which questions are made, questions are asked. Okay? Right? Number 1, when you reverse the reaction, equilibrium constant is to be inversed. When you multiply a reaction by some number, that number goes to the power of equilibrium constant. When you add two reactions, your equilibrium constants are to be multiplied. Right? Okay? I hope this particular stuff is clear. Now, how this is applied in the questions, what kind of questions can be asked. Let's have a look on this basic question over here so that you'll understand where this particular concept is asked. Sir, Tamil Nadu rain, shower problem, Unacademy give leave for 2 days. Is there rain in Tamil Nadu? I think that is one of the reasons why the strength of students is low today. Is it? I did not know. If I knew this, I would have cancelled the session. I would have taken it after 2 days. But anyways, it's okay now. Okay, got it. So in the entire south, it's raining today. I did not know. I thought it would be a normal rain. Like, I did not know it's a heavy rain. I was thinking why the strength is low today. So this is one of the major reasons. Okay, got it. Perfect. Chalo guys, have a look on this particular question now. Have a look on this particular question. Kp for the reaction is given. So we are given with a reaction whose Kp is given to us as 49. We are supposed to calculate Kp for this particular reaction. See guys, remember one just simple thing. One simple thing you have to remember. One simple thing. That reaction whose equilibrium constant is to be calculated. You are supposed to make that reaction. Out of the reaction whose equilibrium constant is given. That reaction whose equilibrium constant is to be calculated. You are supposed to make that reaction out of the reaction whose equilibrium constant is given to us. For example, see, this is the reaction whose equilibrium constant is to be calculated. So I will be making this reaction out of the above reaction. What is my above reaction? It is N2 gas plus 3 times H2 gas. It is in equilibrium with what? 2 times NH3 gas. As per the question, Kp value for this particular reaction is 49. Okay. Now, the reaction which we have to make, in that reaction, NH3 has to be on the left side. NH3 is on left side. Now, NH3 is on left side. That means what I'll be doing first? I'll be first of all reversing this reaction. And when I reverse this reaction, it becomes 2 times NH3 gives N2 plus 3 times H2. Since I've reversed this reaction, so you'll be inversing its equilibrium constant. So I would say equilibrium constant of this reaction now is going to be 1 by 49. Okay. Now people, what I'll be doing again, I'll be multiplying this particular reaction with 1 by 2. When I multiply it with 1 by 2, 2 gets cancelled. So it's NH3 gives, this is going to be half of N2 and this is going to be 3 by 2 times H2. Since I multiplied this particular reaction by 1 by 2, that 1 by 2 has to go to the power of equilibrium constant. So it's going to be 1 by 49 raised power 1 by 2. The value is going to be 1 by 7. Right? The value is going to be 1 by 7. Perfect. So do you see? The reaction whose equilibrium constant was to be calculated. We made that reaction and eventually we got its equilibrium constant, that is 1 by 7. I believe this is clear to everyone. Yeah? Perfect. Let's have a look on one more question. See guys, these are the 3 reactions which are given to us. Their equilibrium constants are K1, K2, K3 respectively. We are supposed to calculate equilibrium constant for this particular reaction. So what I'll be doing, the reaction whose equilibrium constant is to be calculated, we are supposed to make that reaction. We are supposed to make that reaction out of the given reactions. Out of the given reactions. So my dear students, the reaction which we have to make, in this reaction, NH3 is on the left side. And in these reactions, you will see NH3 is here. So what will be my first step? My first step will be to reverse the first reaction. And when I reverse the first reaction, it becomes 2 times NH3 gives N2 plus 3 times H2. And since you have reversed this reaction, its equilibrium constant is inversed. Now it's 1 upon K1. Okay, now it's 1 upon K1. Second reaction I'm writing as such. N2 plus O2 gives 2 times NO. Why I wrote the second reaction as such? Because the reaction which we have to make, in that reaction, NO is on right side. So here NO is on right side. So I wrote it as such. Okay. Now, my dear students, the reaction which we have to make, in that reaction, H2O is on right side. That too, it is 3 times H2O. That too, it's 3 times H2O. And here you can see H2O, but it's not 3 times H2O, it's 1 H2O. So I'll be multiplying this reaction with 3. When I multiply this reaction with 3, it becomes 3 times H2 plus 3 by 2 times O2, right? In equilibrium with 3 times water. Since I multiply this reaction by 3, that 3 goes to the power of its equilibrium constant. So it's K3 raised power 3. Now people, if you add these 3 reactions, what do you get? When you add these 3 reactions, this N2 gets cancelled. 3 times H2, 3 times H2 gets cancelled, right? So I'll be left with 2 times NH3 plus 3 by 2 O2 plus O2 makes it 5 by 2 O2, right? In equilibrium with. Here you're left with 2 times NO and you're left with 3 times H2O. So check it out. This was the reaction which we were supposed to form, and we have formed this reaction. And how did we form this reaction? When we added these 3. And when you add the reactions, their equilibrium constants are to be multiplied, right? So I would say the equilibrium constant for this reaction, which I'm representing with K4, that will be equal to 1 upon K1 multiplied by K2 multiplied by K3 raised power 3. Okay, is there any option like this? It is absolutely going to be option 1. That's going to be the correct answer of this particular question. I believe I'm clear with this. In short, the reaction whose equilibrium constant is to be calculated. You're supposed to make that reaction out of that particular reaction whose equilibrium constant is given. That's all. That is all. Well, this sort of a question, I mean, it should not take you like more than 10 seconds to solve this question. 2 reactions are given. Their equilibrium constants are K1, K2. You have to relate between the 2. You just have to relate between the 2. You just have to relate between the 2. So my dear students, just choose one of these reactions. Choose one of these reactions. For example, I'm choosing this one. Okay, I'm choosing this one. If I by chance reverse the reaction, it becomes 2 times AB. This is A2 plus B2. And when you reverse the reaction, you have to inverse its equilibrium constant, right? Now let's do one thing. Let's multiply this reaction with 3. 3 2s are 6. I'm multiplying the reaction with 3. Okay, since I'm multiplying the reaction with 3, so that 3 goes to the power of equilibrium constant. So it's 1 by K1 raised power 3. Now look at this reaction and this particular reaction. Okay, they are same. They are same. That means their equilibrium constants are to be same as well. So K2 is equal to 1 upon K1 raised power 3. Right? Now select K2 is equal to K2 is equal to 1 upon K1 raised power 3. So it has to be which option? It has to be option C, which is the correct answer of this question, right? It is option C, which is the correct answer of this particular question. A simple and basic one this was again. Okay, I want you guys to solve this question without using pen paper. Without using pen paper. Solve this. This is one reaction whose equilibrium constant is K. This is one more reaction whose equilibrium constant is, for example, K dash. For example, K dash. What will be the relation between K and K dash? So first of all, how do you make this particular reaction? When you multiply this one, when you multiply the first reaction by 1 by 2, you get this one. 1 by 2 means it's going to be K raised power 1 by 2 is equal to K dash. K dash is equal to K raised power 1 by 2. Option C. Yeah? I believe these are pretty much simple questions which I'm sure you can easily solve from now on. Okay, this is one more asked question, guys. This is one more asked question. This question has been asked in the examination, and you should be now in a position to solve this question on your own. Two reactions, their equilibrium constants are given. Third reaction whose equilibrium constants will be calculated. So we are supposed to make this third reaction. How do I make this third reaction? How do I make this third reaction? In the third reaction, SO2 is on left side. Here SO2 is on right side. So reverse the first reaction first. When I reverse the first reaction, it becomes SO2 gives sulfur plus O2. If I reverse it, its equilibrium constant becomes 1 upon 10 raised power 52. But if you think logically, the reaction which we have to make, in that reaction it's 2 times SO2. Here it's only SO2. So multiply with 2 also. Multiply with 2 also. So it is raised power 2. So it becomes 1 upon 10 raised power 104. Right? Perfect. Now second reaction, write it as such. Second reaction, write it as such. 2S plus 3 times O2 in equilibrium with 2 times SO3. If you're writing it as such, that means write its equilibrium constant as such, which is 10 raised power 129. Correct? Now just add these two reactions, people. When you add these two reactions, 2S cancel. 3O2, 2O2. So first of all, I'm writing 2 times SO2 here. This 2 times SO2, 3O2, 2O2. So there will be only one O2 remaining here, right? And this is going to be 2 times SO3. I think we made the reaction which we were supposed to make. How did I make this reaction? When I added these two. And when you add these two, you're supposed to multiply their equilibrium constants. So 1 divided by 10 raised power 104 multiplied by 10 raised power 129. So the final answer is going to be 10 raised power 25. 10 raised power 25 is the equilibrium constant of this reaction which we were supposed to calculate. I hope this is also clear to everyone. Okay? I hope this is also clear to everyone. I hope this is clear to everyone. Perfect. So with this, your basic stuff, that is your characteristics of equilibrium and all, that's absolutely clear, I believe. Now we are going to move into that particular section of this chapter wherein majority of the students, they face problems. Okay, but we'll make sure we'll study this particular topic in such a manner that you are not going to get any sort of issue, any sort of problem while solving these sort of questions which are based on calculation of Kp and Kc. Okay. So my dear students, this is our new topic, calculation of Kp and Kc. How Kp and Kc are calculated for any sort of reaction. How Kp and Kc is calculated. Okay. Well, first of all, you need to remember two things. There are two methods by means of which you can calculate Kp and Kc for a reaction. The first method is what you call as mole method. The second method is what you call as degree of dissociation method. So one-on-one, we shall be discussing these two things. Okay. The first is going to be calculation of Kp and Kc with the help of which method? With the help of mole method. First, we are going to discuss this one in detail, right? First, we are going to discuss this one in detail. After that, we are going to move into degree of dissociation method. My dear students, this is very important, right? And what is important here? That's something I'm teaching you right now first. First, I'll be teaching you some important things. If you master them, you're sorted. What is that? Let me first of all teach you the calculation. The calculation of moles, concentration, and partial pressure of reactants and products at equilibrium. This is something which is super important, I believe. Calculation of moles, concentration, partial pressure of reactants, products at equilibrium. Understand, guys. Understand properly. For example, you have got the reaction like this. Let's say you have got the reaction A gas is in equilibrium with B gas plus C gas. Let's say this is the reaction which is taking place in some container, in some closed container. Okay. First of all, if I write at time t is equal to 0, time t is equal to 0 means the reaction has not started yet. There will be only a reactant in the container. Let's say you have got A moles of this reactant initially in the container. Okay. So, since the reaction has not started, so this is going to be 0. This is going to be 0 in the beginning, right? Because the reaction has not started yet. Now, my dear students, there will be a time when equilibrium will be established in the reaction. I'm assuming at that point of time, when equilibrium is established, let's assume at that time, out of A moles of reactant, let's say out of A moles of reactant, X moles of reactant got converted into products. Let's say at equilibrium, out of A moles of reactant, X moles got converted into products. So can I say I'll be left with A minus X moles of reactant at equilibrium? Right? So I would say these are the moles of reactant left in the container at equilibrium. Right? These are the moles of reactant left in the container at equilibrium. Right, people? Now understand. Use the stoichiometry now. 1 mole of A gives 1 mole of B. If 1 mole of A gives 1 mole of B, I would say X moles of A would be giving us X moles of B. Similarly, 1 mole of A gives 1 mole of C. Therefore, X moles of A are going to give us X moles of C. Okay? So these are basically the moles of reactants and products in the container at equilibrium. These are the moles of reactants products present in the container at equilibrium. Right? Perfect. Now guys, for example, you have got the reaction in this format. Let's say you have got 2 times A in equilibrium with B plus C. This is, for example, one more reaction. Okay, I have slightly changed the stoichiometry. Understand what I'll be doing. Let's say at time t is equal to 0, we have got A moles of this reactant in the container. So this is supposed to be 0, this is supposed to be 0. Now let's say at equilibrium, out of A moles of reactant, let's say X moles got converted into products. So I'll be left with A minus X moles of reactant at equilibrium. Right? Now use the stoichiometry. 2 moles of A are giving us 1 mole of B. If 2 moles of A are giving us 1 mole of B, so can I say 1 mole of A gives 1 by 2 moles of B? 1 mole of A gives 1 by 2 moles of B. Therefore, X moles of A will be giving us 1 by 2 into X. That means X by 2 moles of B. Similarly, 2 moles are giving 1 mole of C. 1 mole of A gives 1 by 2 moles of C. X moles of A is going to give us X by 2 moles of C. So what did I calculate? What are these terms? I would say these are the moles of reactants and products in the container at equilibrium. Right? Similarly, here, these were also the moles of reactants products present in the container at equilibrium. Correct? This is the most important thing which is to be learned, right, while doing the KPKC calculation. For example, let's say you have got the reaction like this. 2 times A in equilibrium with 3 times B plus, for example, 5 times C. Let's say this is the reaction. Okay, let's do the similar calculation. First of all, at time t is equal to 0, let's assume we have got A moles of reactant in the container. So this is going to be 0, this is going to be 0. Now, at equilibrium, let's assume out of A moles of reactant, X moles got converted into products. So I'll be left with A minus X moles of reactant. Okay, now, 2 moles of A gives 3 moles of B. If 2 moles of A gives 3 moles of B, 1 mole of A gives 3 by 2 moles of B. X moles of A gives 3 by 2 multiplied by X moles of B. Okay. Similarly, 2 moles of A gives 5 moles of C. 1 mole of A gives 5 by 2 moles of C. X moles of A gives us 5 by 2 multiplied by X moles of C. So, this is how you guys are going to calculate the moles of reactants and products in the container at equilibrium. Right? These are the moles of reactants products present in the container at equilibrium. Now, people, for example, I'm giving you a scenario like this. Let's say you've got the reaction like this. A gives 2B plus 3C. Let's say this is the reaction. Now, you know, initially at time t is equal to 0, there will be reactant present. How many moles of reactant? A moles. Let's say before the start of the reaction itself, I've kept some B and C in the container already. Before the start of this reaction, let's assume I've already kept some moles of B and C in the container. Let's say I've got B moles of this and C moles of this in the container already before the start of the reaction itself. Right? Now, when the reaction starts, its moles will decrease, its moles will keep on increasing. Can I say at equilibrium? at equilibrium. Out of A moles of reactant, let's say X moles got converted into products. So I'll be left with A minus X moles of reactant. Already in the container, there were B moles of this particular product. Now, some new moles of B would have got formed. Check it out. 1 mole of A gives 2 moles of B. So X moles of A would have given 2X moles of B, right? So B plus 2X, this is going to be, these are the moles of B in the container at equilibrium. Yeah? Talk about C now. 1 mole of A gives 3 moles of C. Already in the container, there were C moles. Now, some new moles would have got formed. 1 mole gives 3 moles. So X moles are going to give us 3X moles. So these are the moles of C in the container at equilibrium. Did you understand? Did you understand all this stuff, people? This is the most important point here to solve the questions, right? On KPKC with the help of mole method, this is the most important point to calculate the moles of reactants products at equilibrium. I believe I'm clear. Let me show you one more type of reaction and then we can move ahead. Let's say you've got the reaction like this. A gas plus 3 times B gas in equilibrium with 2 times C gas. Let's say this is the reaction. So till now, I was showing you those reactions wherein we only had one reactant. Now this is the reaction which has got more than one reactant. So how to carry forward in this particular reaction? Let's say initially at time t is equal to 0, we have got A moles of this, we have got B moles of this in the container, and this is going to be 0. Let's say at equilibrium, out of A moles of this reactant, let's say X moles reacted with B. So can I say I'll be left with A minus X moles of this reactant at equilibrium? Now, 1 mole of A reacts with 3 moles of B. So X moles of A are going to react with 3X moles of B. I took B moles, but out of B moles, how many are reacting? 3X are reacting. So I'll be left with B minus 3X moles of B in the container. Right? Did you understand this? 1 mole of A reacts with 3 moles. So X moles are going to react with 3X moles of B. X moles of A are going to react with 3X moles of B. I took B. Out of B, 3X is reacting. I'll be left with B minus 3X. Now, 1 mole of A gives 2 moles of B. So X moles are going to give us 2X moles of C here. Right? So people, these are the moles of reactants and products which I got in the container at equilibrium. This was something super important. Okay? Now, look at the calculations. Look at the stuff now. Let me write the heading here as KP and KC calculation. KP and KC calculation by which method? By mole method. KP and KC calculation by which method? By mole method. My dear students, for example, I'm taking one reaction. The reaction is like this. A gas in equilibrium with B gas plus C gas. Okay, this is the reaction. Now, for example, at time t is equal to 0, let's say at time t is equal to 0, we have got A moles of this reactant. So this would be 0, this would be 0. Correct? Now, my dear students, at equilibrium, let's assume that out of A mole of reactant, X moles got converted into products. So I'll be left with A minus X moles of reactant. Now, 1 mole of A gives 1 mole of B. So X moles are going to give us X moles, and this will also give us X moles. So what did I calculate till now? What are these terms? These are the moles of reactants and products present in the container at equilibrium. Okay? These are the moles of reactants and products present in the container at equilibrium. Now, my dear students, imagine that this particular reaction is taking place in a container whose volume is V liter. Let's say this particular reaction, it is taking place in a container whose volume is V liter. Understand, people. If I divide A minus X with V, if I divide this X with V, what do I get? Moles divided by volume in liters. That gives us concentrations. So These are the concentrations of reactants products in the container at equilibrium. These were the moles. Now these are the concentrations. These are the concentrations of reactants products present in the container at equilibrium. Moles by volume gives us concentration. Okay. If you got the concentrations of reactants products in the containers at equilibrium, can't you write Kc expression? Kc expression is going to be concentration of B at equilibrium raised power stoichiometric coefficient, concentration of C at equilibrium raised power 1 divided by concentration of A at equilibrium raised power 1. Now people understand here, Kc is equal to, what is concentration of B at equilibrium? X by V. What is concentration of C at equilibrium? X by V. So X by V makes it X square divided by V square, all divided by. What is concentration of A at equilibrium? It is A minus X by V. It is A minus X divided by V. So one of the V got cancelled. So I would say Kc over here, you calculated and got to know it's X square divided by V multiplied by A minus X. So this is how you calculate Kc of a reaction with the help of mole method. So first of all, you calculate moles at equilibrium, then you calculate concentrations at equilibrium, then you write the expression for Kc. Number one. Number two, if you want to do the calculation of Kp, then your expression is supposed to be partial pressure of B at equilibrium raised power 1, partial pressure of A at equilibrium raised power 1. Sorry, not A, this was C. Partial pressure of C at equilibrium raised power 1 divided by partial pressure of A at equilibrium raised power 1. So basically, in order to get the value of Kp, what do I need? I need the partial pressures of reactants products. Now, how do I get the partial pressures? See guys, how do I get the partial pressures? First of all, if I ask you at equilibrium, how many gases are there in the container? I would say at equilibrium, these are the moles of gas A in the container. These are the moles of gas B in the container. These are the moles of gas C in the container at equilibrium, right? At equilibrium. So can I say at equilibrium, we have got three gases, some moles of gas A, some moles of gas B, some moles of gas C, right? So there are three gases in the container at equilibrium. So I can say in short, there's a gaseous mixture. There's a gaseous mixture present in the container at equilibrium. There is a gaseous mixture present in the container at equilibrium. My dear students, there is a gaseous mixture present in the container at equilibrium. If I ask you, how many total moles are there in the container at equilibrium? At equilibrium, there will be A minus X plus this X plus this X. Okay, so this gets cancelled. So it comes out to be A plus X. So these are the total moles present in the container at equilibrium. Let's assume total pressure. Let's assume total pressure of the mixture. At equilibrium is nothing but PT. This is the total pressure of the mixture at equilibrium. As per Dalton's law, total pressure of the mixture at equilibrium will be the sum of the partial pressures of the individual gases. So can I say total pressure at equilibrium will be equal to partial pressure of A at equilibrium plus partial pressure of B at equilibrium plus partial pressure of C at equilibrium, right? We can say this. Now guys, understand. First of all, how many moles of reactant are there in the container at equilibrium? A minus X. These are the moles of reactant in the container. These are the moles of gas A in the container at equilibrium. If I divide this with total moles present in the mixture, moles of gas A in the mixture divided by total moles of the mixture, should I be calling this as mole fraction? This is mole fraction of gas A at equilibrium, right? Similarly, X divided by A plus X. This is the mole fraction of B in the container at equilibrium. Similarly, X divided by A plus X. This is the mole fraction of gas C in the mixture at equilibrium. Well, if you got the mole fractions, do you remember partial pressure is equal to total pressure multiplied by mole fraction, right? You got the mole fractions, so multiply them with total pressure of the mixture at equilibrium, which is PT. I'm multiplying everyone with total pressure of the mixture at equilibrium. So what do I get? I got the partial pressures of reactants products at equilibrium. Why do I need the partial pressures? Because I need to get the value of Kp. So Kp has to be equal to partial pressure of B in the container at equilibrium, that is this one, partial pressure of C in the container at equilibrium, that is this one, divided by partial pressure of A in the container at equilibrium, that is this one, right? So do a bit of calculation and we are done. So this multiplied by this, that means this into this will be x into x is x square, multiplied by this is going to be pt ka square, pt square, divided by what? Divided by a plus x ka square, whole divided by a minus x multiplied by pt divided by a plus x, right? One of the a plus x cancelled, one of the pt cancelled, so it comes out to be x square multiplied by pt divided by a plus x into a minus x is going to be a square minus x square. So this is how you got Kp for this particular reaction as well. I hope you understood, people. I hope you understood how to get the value of Kc and Kp for the reaction. Well, in order to get the Kc, what do we need? We need the concentrations at equilibrium. In order to get the Kp, what do we need? We need the partial pressures of reactants products at equilibrium. That's all. And you got to know how do we convert. For everything, whether you want partial pressures, whether you want concentrations, what do you need? You need first the moles of reactants products at equilibrium. Okay, I believe this is clear. I'll show you one more example with a different format of stoichiometry so that you'll understand this in detail. Then we'll see a lot of questions based on the same. For example, people, you have got the reaction like this. 2 times A in equilibrium with B plus C. Right? This is, for example, one reaction. Understand each and every step I'm going to repeat again. First thing, people, first thing which I can conclude from here. What is the delta Ng for this reaction? What is the delta Ng for this reaction? Do you see? Delta Ng for this reaction is 0. And people, if delta Ng for this reaction is 0, that means, of course, its Kp and Kc are supposed to be equal. They should be equal. They must be equal. Right? Now let's get to know how Kp and Kc will be equal for this particular reaction. Okay? Same process which I'll be following. Imagine at time t is equal to 0, we have got A moles of this reactant. This is 0, this is 0. Now, at equilibrium, let's assume out of A moles of reactant, X moles got converted into product. So I'll be left with A minus 6. 2 moles are giving 1. 1 mole gives 1 by 2. X gives X by 2. This will be also X by 2. So what are these terms? These are the moles of reactants products in the container at equilibrium. Since, people, these are the moles. Let's say the volume of the vessel in which reaction takes place, that's V liters. If I divide all these terms with V, A minus X divided by V, X divided by 2 divided by V, X by 2 divided by V, what do I call them? I'll be calling them as concentrations. So these are the concentrations of reactants products at equilibrium. These are the concentrations of reactants products at equilibrium, right? Now, one more thing. How do we calculate partial pressures of reactants products? So first of all, if I ask you at equilibrium, how many gases are there? 3 gases. So we have got a mixture of gas at equilibrium. How many total moles are there in the container at equilibrium? Total moles in the container at equilibrium. This plus this plus this. So x by 2 plus x by 2 makes it x. So that x and this x gets cancelled. So total moles in the container at equilibrium is equal to A. Total moles in the container at equilibrium is equal to A. So if I divide this A minus x with A, if I divide with this x by 2 with A, if I divide this x by 2 with A, what do I get? I got mole fractions. These are the mole fractions of the gases in the container at equilibrium. Let's say the total pressure of the mixture is P. If I multiply this with total pressure of the mixture at equilibrium, total pressure of the mixture at equilibrium, what do I get? Mole fraction multiplied by total pressure. That gives you partial pressure, right? Mole fraction of the gas multiplied by mole fraction of the gas in the mixture multiplied by total pressure of the mixture. That gives us the mole fraction. Sorry, that gives us the partial pressure. So these are the partial pressures of reactants products. So we have calculated each and everything. Now it is just the time to write the Kc and Kp expression. Kc expression is going to be concentration of B at equilibrium, that's x by 2V. Concentration of C at equilibrium, x by 2V, which becomes basically x square divided by 4V square, whole divided by concentration of A at equilibrium, that's A minus x divided by V, whole raised power stoichiometric coefficient, that's 2, right? So it's power 2. So Kc has to be equal to V square cancelled. So it's going to be x square divided by 4 multiplied by a minus x ka square. So this is how you calculate Kc for this sort of a reaction. So you got the Kc. Now what is the second thing? You're supposed to get the Kp as well. You're supposed to get the Kp as well. Well, how do I write the expression for Kp here? It's partial pressure of B at equilibrium multiplied by partial pressure of C at equilibrium divided by partial pressure of A at equilibrium raised power 2. Okay, so first of all, this multiplied by this. So it's going to be x square multiplied by at square whole divided by 2a means 4a square whole divided by this particular stuff. It is a minus x multiplied by pt divided by a, but there has to be square here because the stoichiometry here is 2. Yeah. Okay. Now do the calculation a bit. So pt square cancel, a square cancel. So kp here comes out to be equal to x square divided by 4 multiplied by a minus x square. Just check it out. This is the value of kp for the reaction. Okay. My dear students, one thing that I already told you. Since the reaction has got delta and G0, its Kp and Kc must be equal. Of course, you are saying Kp and Kc are equal for the reaction. Okay? Right? Because its delta and G was 0, for sure. Did you get to know the process which you are going to follow to do the Kp and Kc calculation? I just want to know that, so that I could give you some questions. Did you get to know the process which you are going to follow? I just want to know that, people. Now, there are some lot of questions which I have come up with for Kp-Kc calculation with the help of mole method. You can see there are a lot of questions. Now, let's have a look how these lot of questions are to be solved over here. Because this is the main topic in chemical equilibrium. See guys, look at the first question. For the reaction A plus B gives 2C. For the reaction A plus B, A gas plus B gas, it gives 2 times C gas. Okay. 2 moles of A, 1 mole of B and 1 mole of C are placed in a 10-liter vessel. The volume of the vessel in which the reaction is going to take place, that's 10 liters. Now, as per the question, initially, we are starting with 2 moles of A. We are starting with 1 mole of B. And already before the start of the reaction, there is 1 mole of C also in the container. Now, what is my first step? Calculate the moles at equilibrium. Let's assume out of 2 moles of A, X moles are reacting. So I'll be left with 2 minus X. 1 mole of A reacts with 1 mole of B. So X moles of A will be reacting with X moles of B. I've taken 1. Out of 1, X are reacting. So I'm left with 1 minus X. Already there is 1 mole of C in the container. Now due to the reaction, some new moles of C would have got formed. 1 mole of A gives 2 moles of C. So X moles of A are going to give us 2X moles of C. So I got the moles of reactants products in the container at equilibrium. Yeah. These are the moles of reactants products in the container at equilibrium. What do we need to calculate? Kc. If I need to calculate Kc, do I need moles here or I need concentrations? I need concentrations of reactants products here. So how do I convert these moles into concentrations? Just divide these moles by the total volume of the vessel. That's 10 liters. So these are the respective concentrations. These are the respective concentrations of reactants products in the container at equilibrium. Now, my dear students, if you see logically, in the question they are saying if the final concentration of C is 0.2 molar. What is meant by final concentration? See, I've told you already, when equilibrium is established in the reaction, after that, concentrations of reactants products, they are not going to change. So, equilibrium concentrations of reactants and products are basically the final concentrations of reactants products. Right? Equilibrium concentrations of reactants products are basically the final concentrations of reactants products. Right? Because after that, concentrations do not change. Correct? So I can say concentration of C at equilibrium is given to me as 0.2 molar. Now, what did we calculate? Concentration of C at equilibrium. We got to know that. That's 1 plus 2x divided by 10. And this value is equal to 0.2. 0.2 means 2 by 10. So 10 cancelled. So x value will come out to be 0.5. So x you got to know as 0.5. X is your 0.5 here. If x is 0.5, put the value of x. Put the value of x in all these people. So 2 minus x, 2 minus 0.5. 2 minus 0.5 is 1.5. 1.5 divided by 10 is equal to 0.15 molar. 1 minus 0.5 is 0.5. 0.5 divided by 10 is 0.05 molar. 1 plus 2x by 10. 1 plus 2x by 10. That's already 2 by 10. That means 0.2 molar. So you got the actual concentrations of reactants and products at equilibrium. And since you got the actual concentrations of reactants and products at equilibrium, dear students, you can easily write the expression for Kc. Kc expression is going to be concentration of C at equilibrium raised power 2 divided by concentration of A at equilibrium raised power 1 multiplied by concentration of B at equilibrium raised power 1. I would say Kc is equal to concentration of C at equilibrium. That's 0.2. So 0.2 ka square divided by concentration of A at equilibrium. How much is that? 0.15 raised power stoichiometric coefficient 1. Concentration of B at equilibrium. That is 0.05 raised power stoichiometric coefficient 1. Solve this. This is going to give you the value of Kc for this particular reaction, people. That's something which you were supposed to calculate, Kc for the reaction, and you did it. You're done with this. You are done with this, people. Am I clear with this? Am I clear with this, people? People are saying 16 by 3. Yes, you're right. 5.3 is the correct answer. 5.3 is the correct answer. All right. So this was the first question, which I believe you got to know how to solve. Let's have a look on one more. Let's have a look on one more. This is the asked question, guys. This is the asked question. As far as this particular equation is concerned, we are given the reaction, and the reaction is x plus y in equilibrium with 2 times z. This is the reaction. As per the question, we are starting with 1 mole of x. We are starting with 1.5 moles of y, and there are 0.5 moles of z already there in the container, whose volume is 1 liter. Now, as per the question, they're allowed to reach equilibrium. At equilibrium, the concentration of z is given. So, concentration of z at equilibrium is given to me as 1 molar, right? Now, technically, what am I supposed to calculate? Equilibrium constant Kc. Equilibrium constant Kc we have to calculate, okay? Now, see, guys, how exactly you are going to solve this. The same process, the same process, the same process, the same process. At equilibrium, out of 1 mole of x, out of 1 mole of this reactant, let's say x moles have reacted. So I'm left with 1 minus x. There are 1 minus x moles of this reactant in the container at equilibrium. Now 1 mole reacts with 1 mole. So x moles would have reacted with x moles of y. X moles of this reactant would have reacted with x moles of y. I had taken 1.5. From 1.5, x are reacting. So I'll be left with 1.5 minus x. Already in the container, there are 0.5 moles of z. Now some new moles of z would have got formed. See, 1 mole of x gives 2 moles of z. Therefore, x moles of this reactant would have given 2x moles of this z. So you got the moles of reactants products in the container at equilibrium. Since you got the moles, what do I need? I need Kc. In order to get the Kc, do I need moles or concentrations? I need concentrations. So I'll be dividing all these moles with the volume of the vessel, that's 1 liter. So divide by 1, divide by 1, divide by 1. So these are basically the concentrations of reactants products at equilibrium. Now, my dear students, concentration of Z at equilibrium is 1 molar. And concentration of Z at equilibrium, we know that is 0.5 plus 2x. So technically, I would say 0.5 plus 2x is equal to 1. So I would say x is equal to 1 minus 0.5 is 0.5. 0.5 by 2 is 0.25. This is the value of x. If you got the actual value of x, so 1 minus x, 1 minus 0.25 is 0.75 molar. This is the actual concentration of this reactant at equilibrium. 1.5 minus x, 1.5 minus 0.25, that's 1.25 molar. Similarly, people, this particular term, 0.5 plus 2x and 0.5 plus 2x is given to me as 1 molar in the equation itself. Okay, so I got the actual concentrations of reactants products in the container at equilibrium. Since you got the actual concentrations, so Kc expression, Kc is going to be equal to concentration of Z at equilibrium raised power stoichiometric coefficient 2, concentration of X at equilibrium, stoichiometric coefficient 1, concentration of Y at equilibrium, stoichiometric coefficient 1. What is the concentration of Z at equilibrium? It's 1. So 1 ka square divided by concentration of X at equilibrium 0.75. Concentration of Y at equilibrium 1.25. And I think when you solve this, the value comes out to be 16 by 15. So Kc value from here comes out to be 16 divided by 15. But as per the equation, they are mentioned Kc is equal to X by 15. They have mentioned that Kc is equal to X by 15. So X by 15 is equal to 16 by 15. What does that mean? It means your X here is 16. That means your X here is 16, which you are supposed to calculate. So done and dusted, right? Got it? This was the second type of question that can be asked. Second type of question that can be asked. Have a look on one more, guys. One more type of question which can be asked. Look at the question. On starting with 1 mole of HI in a 2-liter container, calculate the concentration of each species at equilibrium if Kp for the decomposition of HI. So first of all, you should know what is the decomposition reaction of HI. And you should be knowing when HI decomposes. When HI decomposes, what does it give? It gives H2 gas. And with this H2 gas, you'll be getting I2 gas as well. As far as the question is concerned, on starting with 1 mole of HI. So initially, we are starting with 1 mole of HI. So this will be 0 in the beginning. This will be 0 in the beginning. The volume of the vessel in which reaction takes place, that's 2 liters. Calculate the concentration of each species at equilibrium if Kp for the reaction. Kp for the reaction is given to me as 16. Kp for the reaction is given to me as 16. Guys, tell me one thing. What is delta Ng for this reaction? Who is this Kevin? He needs to be blocked. Sorry, man. Some other time. Okay. Who's this Vinesh? Sorry, bro. Someone is asking, किसको क्या बोल रहे तुम कहाँ से हो? स्टेट बोलो अपना, बताता हूँ स्टेट तुम्हें. Who else? They are gone. They're over. Okay. So guys, if you look at this particular reaction, delta Ng for the reaction is 0. If you see carefully. If delta Ng is 0, that means Kp and Kc are supposed to be equal. Kc is also this much. Kc is given to me technically, right? Kc is given to me. Now, what are we supposed to calculate? We are supposed to calculate the concentration of each species at equilibrium. Concentration of each species at equilibrium. Concentration of each species at equilibrium. Now, the same process which I'll be following. Let's assume at equilibrium, out of 1 mole of reactant, X moles have got converted into products. So I'll be left with 1 minus X moles of reactant at equilibrium. 2 moles are giving me 1 mole. So 1 mole gives me 1 by 2. X will give me X by 2. In the similar way, this is going to be X by 2. So these are the moles of reactants products in the container at equilibrium. Now, if I divide these moles by the volume, so 1 minus X divided by volume is 2 liters, right? Similarly, X by 2 divided by 2, that means X by 4. This will be also X by 4. So what are these terms? These are the concentrations of reactants products in the container at equilibrium. And as per the question, we are supposed to calculate these concentrations only. As per the question, we are supposed to calculate these concentrations of reactants products only at equilibrium. How do I get to know the concentrations? In order to know the concentrations, we should know the value of X. Now, how do I get the value of X? From this particular expression. We know Kc is equal. We know Kc is equal to 16, right? Kc is equal to 16. Now, how do I get the expression for Kc? Kc expression is going to be concentration of H2 raised power 1, concentration of I2 raised power 1, X by 4 into X by 4 makes it X square divided by 4 square divided by concentration of Hi, that is 1 minus X divided by 2 raised power stoichiometric coefficient, that's 2, and this value is equal to 16, right? Perfect. So this 2 ka square is 4, 1 4 cancels. So X square divided by 4 multiplied by 1 minus X square is equal to 16, correct? Now, a bit of calculation is needed here. How do I do this particular calculation? Let's try to check it out. This is x ka square. Instead of x ka square, I'm writing x divided by. This is 4. 4 is 2 ka square multiplied by 1 minus x. I'm taking square as common here. I'm taking square as common, right? So it's 16. Take root on both the sides. So it's x divided by 2 ones are 2 minus 2x is equal to 4. So we can say x is equal to 8 minus 8x, or I can say 9x is equal to 8, or I can say x is equal to 8 by 9. If you got the value of x, you're done. If you got the value of x, you're done. The concentration of HI at equilibrium will be 1 minus x, 1 minus 8 by 9 by 2. So 9 minus 8 is 1, 1 by 9 by 2. So it's 1 by 18. So this is the concentration of HI at equilibrium. Number 1. X by 4. X is 8 by 9, right? So it's 8 divided by 9, 4 is 36. So 8 by 36 molar. This is the concentration of H2 at equilibrium. Similarly, this will be also 8 by 36 molar. This will be the concentration of I2 in the container at equilibrium. Done? One simple question, basic question. It is just a bit of calculations needed, and bus, that's it. Look at this one. Look at this one. You should be in a position to solve this one as well. The question is N2 plus 3 times H2 gives 2 times NH3. The partial pressure of N2, H2 are this and this at equilibrium. The total pressure of the system at equilibrium is this much. Calculate Kp for the reaction. Very basic question, guys. Very basic question. Matthew, wait. Kp, for Kp also there will be a lot of questions. Wait for it. See, guys. As far as the reaction is concerned, we have got N2 gas plus 3 times H2 gas in equilibrium with 2 times NH3 gas. Tell me one thing. When equilibrium will be established in the reaction, when equilibrium will be established in the reaction, when equilibrium will be established in the reaction, tell me how many gases will be there. There will be 3 gases in the container when equilibrium will be established, right? There will be some moles of N2, some moles of H2, and some moles of NH3 in the container. So when equilibrium is established, there are some of the moles of N2 in the container. There are some of the moles of H2 in the container. Plus some of the moles of NH3, which would have got formed in the container too, at equilibrium. So I would say at equilibrium, I've got a mixture of 3 gases. At equilibrium, I've got a mixture of 3 gases. As far as the question is concerned, the total pressure of the mixture at equilibrium is given. Total pressure of the mixture at equilibrium is given to me as 2.8. My dear students, as per Dalton's law, total pressure of the mixture at equilibrium has to be equal to the sum of their partial pressures. So I'll write partial pressure of N2 at equilibrium plus partial pressure of H2 at equilibrium plus partial pressure of NH3 at equilibrium. This has to be equal to 2.8. What is the partial pressure of N2 at equilibrium? 0.8. Partial pressure of H2 at equilibrium, 0.4. So from this particular equation, I can calculate partial pressure of NH3 at equilibrium. And when you solve this equation, you can say partial pressure of NH3 at equilibrium will be equal to this 1.2. So it's going to be 1.6 atm. Right? So this is the partial pressure of NH3 at equilibrium. If you know the partial pressure of all these 3, don't you think we can easily write the Kp expression? Kp is going to be partial pressure of NH3 raised power 2, that is 1.6 ka square, divided by partial pressure of N2 at equilibrium 0.8 raised power stoichiometric coefficient 1, partial pressure of H2 at equilibrium 0.4 raised power stoichiometric coefficient 3. When you solve this, the value comes out to be 50. If I ask you what are going to be its units, units of Kp, atm raised power delta Ng here, and delta Ng for the reaction is moles of gaseous products minus moles of gaseous reactants. So 2 minus 4 is minus 2. So this is the final answer. Kp is done and dusted, right? Kp has been calculated. Kp has been calculated. All right. Look at this particular question. This was asked last year in your JEE mains examination, and it's pretty much simple. The question is, the equilibrium constant Kc for the reaction is 100. Okay, Kc is given for the reaction. If the initial concentration of all the 4 species are equal to 1 molar, okay, calculate concentration of D at equilibrium. So my dear students, in the question, they are telling us that the initial concentration of all the species, be it A, B, C or D, it's equal to 1 molar each as per the question. They are saying the initial concentration of all the species is 1 molar. And one more thing, AC value is given to us as per the question. How much? 100. What are we supposed to calculate? We are supposed to calculate concentration of D at equilibrium. It's a simple question. See, till now we were starting with the moles. Now here in this question, you are going to start with the concentration directly. Here in this question, they have given you concentrations directly. So you have to start with the concentrations directly. Simple. Whatever treatment you were doing with the moles, same treatment you are going to do with the concentration. That's it. Whatever treatment you were doing with the moles, same treatment you are going to do with the concentration. So if this is at equilibrium 1 minus x, this is supposed to be 1 minus x2, this is supposed to be 1 plus x, and this is supposed to be 1 plus x. Right? Simple. Whatever things we were doing till now, same things we are following. So these are the concentrations of reactants products in the container at equilibrium. Write the expression for Kc. Kc expression. Concentration of C, concentration of D. That means square. Divide by concentration of A, concentration of B. That means square of this. So I'll take square common. 1 plus x divided by 1 minus x whole raised power 2 is equal. Kc value as per the equation is 100. So take the root on both the sides. It's 1 plus x divided by 1 minus x is equal to 10. So I would say 1 plus x is equal to 10 minus 10x. Or I would say 11x is equal to 9, which is telling me that x is equal to 9 by 11. X is equal to 9 by 11. So people, if x is equal to 9 by 11, what am I supposed to calculate? Concentration of D at equilibrium. And as you can see, concentration of D at equilibrium is nothing but 1 plus x. So it's going to be 1 plus 9 by 11. The value is 11 plus 9. That means 20 divided by 11 molar. So this is the concentration of D in the container at equilibrium, which I was supposed to calculate, right? Which I was supposed to calculate. Am I clear? Am I clear? What is the order of oxidizing agent for HClO, HClO2, HClO3, HClO4? Generally, strength of oxidizing agent is directly proportional to oxidation state of the central atom. So it is supposed to be HClO4, but no. The strongest will be HClO, right? HClO will be strongest oxidizing agent, followed by HClO2, followed by HClO3, followed by HClO4. Exception here. Okay, remember it. All right, people. Look at the next one. Look at the next one. Look at the next one. You should be able to solve this one too. You should be able to solve this one too. If the initial concentration of B is 1.5 times that of A, if the initial concentration of B is 1.5 times that of A, let's say if the initial concentration of this was A, so this is supposed to be 1.5 times A as per the question. Okay? This is 0, this is 0. At equilibrium, concentration of A and B are equal. Now again, we are starting with the concentration directly. So first of all, at equilibrium, let this be A minus x, and this will be 1.5 A minus 2x, because 1 mole reacts with 2 moles, x will react with 2x, so 1.5 minus 2x. This will be 1 gives 2, x gives 2x, 1 gives 1, x gives x. So this is basically, these are the concentrations of reactants products. These are the concentrations of reactants products in the container at equilibrium, right? Now, as per the question, at equilibrium, the concentration of A and B is equal. This is mentioned in the question itself. It's mentioned in the question itself. At equilibrium, concentration of A and B is equal. So concentration of A and concentration of B is equal at equilibrium. Concentration of A at equilibrium is 1 minus x. Concentration of B at equilibrium is 1.5 A minus 2x. So it will be, take this on this side. So x is equal to 0.5 A. If x is equal to 0.5 A minus x, A minus 0.5 A comes out to be 0.5 A. 1.5 A minus 2x. X is 0.5 A. So 2 into 0.5 A means A. So it becomes 1.5 A at the end, right? 2 into x. 2 into this comes out to be A. X is 0.5 A. So you got the concentrations of reactants products in the container at equilibrium. If you got the concentrations, what are we supposed to calculate? Kc. So Kc has to be equal to, Kc has to be equal to concentration of C ka square, so it's A ka square, multiplied by concentration of D, that is 0.5 A, divided by concentration of A, that is 0.5A, multiplied by concentration of B, that is 0.5A ka square. So first of all, A square into A makes it A cube. A cube here also, A cube cancel. So the final answer is 0.5 divided by 0.5 multiplied by, this will be in short 0.5 ka cube, right? So 1 divided by 0.5 ka square. 0.5 ka square is 0.25. So it's 100 divided by 25. Value comes out to be 4. So Kc value here is coming out to be 4. That's it. Okay. I hope I'm clear with this. Kc value is coming out to be 4 in this particular question. All right. Moving on to one more. Reaction is given. Its Kc is given. What must be the volume of the flask? What must be the volume of the flask? Means volume of the container. If mixture of 2 moles of A, B and C are at equilibrium. So basically in the question, they are directly telling us that at equilibrium, there are 2 moles of this, 2 moles of this and 2 moles of this at equilibrium. In the mixture at equilibrium, there are 2 moles of A, 2 moles of B, 2 moles of C as per the question. Let's say the volume of the container is V liters. So if I ask you, what about the concentration of A at equilibrium? It's going to be 2 by V. Concentration of B, 2 by V. Concentration of C, 2 by V, right? If you want to write the expression for Kc, Kc expression is going to be concentration of B, that's 2 by V, raised power 1. Concentration of C, that's 2 by V, raised power 3, because stoichiometric coefficient here is 3, divided by concentration of A, that's again 2 by V, raised power 2. Okay, so this and this gets cancelled. So it becomes 2 2s are 4 by V square is equal to Kc. Kc as per the question is 16, right? Or you can write it as 2 divided by V ka whole square is equal to 16. Or you can say 2 by V is equal to 4. Or you can say V is equal to 2 by 4. That means 1 by 2 liters. So this is something which I was supposed to calculate. Volume of the flask. So volume of the flask here in which the reaction is taking place, that's equal to 0.5 liters, half liter. This sort of a question, I believe, you should be in a position to solve this one. Similarly, one more simple and basic question this is. One more simple and basic question. You've got a vessel whose volume is 1 liter containing 1 mole of SO3. So initially, you are starting with 1 mole of SO3. So this would be 0, this would be 0, right? Now at equilibrium, if this is 1 minus X, right? 2 moles gives 2 moles, 1 mole gives 1, so X gives X. 2 gives 1, 1 gives 1 by 2, X gives X by 2. So these are the moles of reactants products in the container at equilibrium, right? Now in the question only they are mentioning that, 0.6 moles of SO2 are present at equilibrium. So moles of SO2 at equilibrium is X. As per the question, technically I would say X is equal to 0.6. They are saying 0.6 moles of SO2 are found at equilibrium. And at equilibrium, how many moles of SO2 we have? X. So X is 0.6. First done. 1 minus 0.6, that is 0.4. This is 0.6. 0.6 divided by 2 is 0.3. So these are the moles, right? So divide them with volume, 1 liter. So these are the concentrations also. These are the concentrations of reactants products at equilibrium. If you got the concentrations of reactants products at equilibrium, what are we supposed to get? We are supposed to get the Kc value. Kc expression. Concentration of SO2, 0.6 at equilibrium, raised power. Stoichiometric coefficient, that's 2. Here it's going to be concentration of O2, that is 0.3, divided by concentration of SO3 ka square, that means 0.4 ka square. When you solve this, you're here going to get the Kc value, which you were supposed to get as per the question was concerned. Okay? I believe this is clear. Simple question this was. All right, look at this one. We are given the reaction. Its Kc is given to me as 5. How many moles of carbon dioxide must be added to a 1 liter? How many moles of carbon dioxide must be added to a 1 liter already containing 3 moles each of CO and water? Already containing 3 moles of CO and water. How many moles of carbon dioxide must be added to a 1 liter container already containing 3 moles each of this and this to make 2 molar equilibrium concentration of carbon monoxide? Concentration of carbon monoxide at equilibrium is also going to be as 2 mole. Basically, have a look. As per the question, in the container, we have got 3 moles of this, 3 moles of this. Now, as per the question, in the question, they are saying, how many moles of carbon dioxide should be added in the beginning itself? How many moles of carbon dioxide should be added in the beginning itself, such that the concentration of carbon monoxide at equilibrium becomes 2 molar. Let's say for that purpose, I'm adding A moles of carbon dioxide here. Let's say in the beginning itself, I've added A moles of carbon dioxide, then only concentration of carbon monoxide at equilibrium is equal to 2 molar. Now, first of all, at equilibrium, let's say out of 3 moles of this reactant, X have reacted. So I'm left with 3 minus X. This will be also 3 minus X because stoichiometry is 1. This will be how much? 1 mole gives 1 mole. So this is X gives X. So A plus X. 1 gives 1. So X gives X. Right? Perfect. Now, people, as per the question, concentration of carbon monoxide at equilibrium. Concentration of carbon monoxide at equilibrium, which is 3 minus X. As per question, 3 minus X is equal to 2. Right? X value is equal to 1. You got the value of X. X is 1. So 3 minus 1 is 2. 3 minus 1 is 2. This is A plus 1. And this is X, which is already 1. Perfect. So these are what? These are the concentrations because volume is 1 liter. Because volume is 1 liter. These are the concentrations. If these are the concentrations, if I would want to write the expression for Kc, Kc expression is going to be concentration of this A plus 1 raised power 1. Concentration of H2 is 1 divided by concentration of this is 2 and concentration of this also 2. So 2 ka square is 4. 2 ka square is 4. I think we missed something. I think we missed something. Did we miss something, guys? Or not? No, we did not miss anything. So A plus 1 divided by 4. Kc as per the question is given to be as 5. Right? So it's A plus 1 is equal to 5 4s are 20. So A comes out be 19. What is this A? I would say in the beginning itself, I was supposed to add 19 moles of carbon dioxide. Then only the concentration of carbon monoxide in the container at equilibrium would be 2 molar. I hope this sort of a question, if it comes in your exam, I hope you should be in a position to solve this one as well. Okay? Perfect, guys? Right? Okay, this question I won't be able to show you now. For this, I have to teach you degree of dissociation. That will be done afterwards. Yeah. I think this is the one which you can do on your own. Check it out once. Check it out once, people. Check it out once. Will you be able to solve this one now? I think yes. Nothing. I mean, there is nothing to do here. It's simple. It's simple. All the parameters are given. Moles of all the reactants products at equilibrium are given. Volume is 1 liter, right? So if moles at equilibrium are given, divide them with volume, you'll be getting concentration. If you get concentration of each, write the Kc expression. Done and dusted, right? I hope I'm clear with this. So this can be your homework. This can be your homework question. And do let me know afterwards the answer of this particular question. Yeah? See, moles of all the reactants products at equilibrium are already given. So divide those moles by the volume, get the concentration. If you get the concentration, write the expression for Kc. Okay? Now, guys, one question I'm going to show you here. Okay. Look at this. Look at this question. Look at this question, guys. If the total pressure at equilibrium for the following reaction is 2 atm, calculate the volume fraction of Cl2 at equilibrium. One thing I'm telling you right now, do remember it. Sometimes they might ask you a question wherein they'll just confuse you with some fancy terminologies. They might confuse you with some fancy terminologies, right? For example, they might ask you to calculate volume fraction. They might ask you to calculate volume fraction of this or this at equilibrium. Okay? They might ask you to calculate volume fraction of this at equilibrium, volume fraction of this at equilibrium, volume fraction of this at equilibrium. Remember, volume fraction of anyone. Let's say volume fraction of Cl2. In this question, they're asking you to calculate volume fraction of Cl2. Let me tell you, volume fraction of Cl2 at equilibrium is nothing but, indirectly, they're asking you to calculate mole fraction of Cl2 at equilibrium. Okay? Remember this stuff. So sometimes, just to confuse you, basically at constant pressure temperature, mole fraction, volume fractions, they're equal. Since at equilibrium, the pressure of the mixture is constant, temperature of the mixture is also constant. So I would say equilibrium mixture is present at constant pressure temperature. Therefore, mole fraction and volume fraction of each component is the same. So in short, remember it like this. Whenever they ask you to calculate volume fraction of, for example, Cl2 at equilibrium, understand they're asking you to calculate mole fraction of Cl2 at equilibrium. If they ask you to calculate a volume fraction of PCl5 at equilibrium, that means they're asking you to calculate mole fraction of PCl5 at equilibrium. Okay? One more thing. Sometimes they might ask you to calculate volume percentage. Let's say volume percentage of Cl2. Let's say if they ask you to calculate volume percentage of Cl2. Volume percentage of Cl2 at equilibrium will be nothing but it will be mole percentage of Cl2 at equilibrium. At equilibrium, volume percentage, mole percentage is same, right? Similarly, what is mole percentage? Mole percentage of Cl2, for example, at equilibrium is nothing but mole fraction of Cl2 at equilibrium. It is nothing but mole fraction of Cl2 at equilibrium. Mole fraction of Cl2 at equilibrium multiplied by 100. This is going to give you mole percentage of Cl2. Mole percentage of Cl2 is nothing but volume percentage of Cl2. So take a note of all this stuff. Take a note of all this stuff. They might, trick you from these particular fancy things. Okay, otherwise it's a simple question. Calculation might be a bit difficult for you. Let's first of all check it. As far as the question is concerned, we are given with a reaction. The reaction is like this. PCl5 gas gives PCl3 gas plus Cl2 gas. This is the reaction that's given to me. As far as the question, if you see, Kp is also given. We are supposed to calculate volume fraction of Cl2 at equilibrium. Volume fraction of Cl2 at equilibrium means mole fraction of Cl2 at equilibrium, right? So basically, we are supposed to calculate mole fraction of Cl2 at equilibrium. How do I do it? How do I get the mole fraction? Guys, one more thing is given. Total pressure of the mixture is given as 2 atm. PT, total pressure of the mixture at equilibrium, is given to me as 2 atm. All right. Kp, as per the question, is given to me as 0.2 atm. Okay. So let's try to do the stuff. Understand. Let's say we are starting with A moles of reactant. Since initial moles of reactant is not given, so I'm assuming that I'm starting with A moles of reactant, right? A moles of reactant. So this is going to be 0. This is going to be 0. Now at equilibrium, this is supposed to be A minus X. This will be X. This will be X. So if I ask you how many total moles are there in the container at equilibrium, this plus this plus this, X cancel, the value comes out to be A plus X. So I'm dividing this with A plus X, this with A plus X, and this with A plus X. So what are these terms? These are basically the mole fractions of each reactant product in the container at equilibrium. And I'm supposed to calculate this particular value basically. As per the question, I'm supposed to get this particular value because this is something which I'm calling as mole fraction of Cl2 at equilibrium, right? But one thing. Let me do one thing. Let me multiply these mole fractions with what? With total pressure of the mixture at equilibrium, which is 2, I believe. Yeah, 2. So this will be 2x divided by A plus X. This will be 2x divided by A plus X. So I would say these are the partial pressures of reactants products at equilibrium. These are the partial pressures of reactant products at equilibrium. Okay. Now guys, if these are the partial pressures of reactants products at equilibrium, if I write the expression for Kp, Kp expression is going to be partial pressure of this multiplied by partial pressure of this. So it comes out to be this multiplied by this is 4x square divided by what? Divided by A plus X ka square whole divided by partial pressure of PCl5, which is 2 multiplied by A minus X divided by A plus X. And this value as per the question is 0.2. 0.2 means 2 by 10. 0.2 means 2 by 10. Is that? Yeah, 0.2 is 2 by 10. Now a bit of calculation is needed first of all here. A plus X cancel, 2, 1, 2, 2. So finally it's going to become 2x square divided by A plus X, A minus X is A square minus X square is equal to 2 divided by 10. So 2 gets cancelled here. When 2 gets cancelled, this becomes finally 10x square is equal to A square minus X square, or you can say 11x square is equal to A square, or you can say X is equal to A divided by root 11. So you got the value of X first of all. You got the value of X. X is equal to A divided by root 11. If x is equal to a divided by root 11, what am I supposed to calculate as per the question? Volume fraction of Cl2, which is nothing but mole fraction of Cl2 at equilibrium. And you can see mole fraction of Cl2 at equilibrium is what? Mole fraction of Cl2 at equilibrium is what? It is x divided by a plus x. Now tell me, what is x? X is a by root 11 divided by a plus x is again a by root 11. So a, everywhere cancel. In the numerator, I'm left with 1 by root 11. In the denominator, it's going to be root 11 plus 1 divided by root 11. So this term cancels. The final answer I'm writing here, final answer, that's going to be 1 divided by root of 11 plus 1. So this is basically the mole fraction of Cl2 in the container at equilibrium. This is something which I'll be calling as volume fraction of Cl2 in the container at equilibrium. This is something which I was supposed to calculate. I believe I'm clear with all this stuff. Okay. Perfect, guys. Am I clear? Am I clear? Am I clear, guys? Well, guys, it's not a big chapter. It'll just take like, 3 more hours to complete. That's it. It will take 3.5 more hours to complete. Small chapter. I told you in the beginning itself. Don't worry. Okay. So here in the mole method, there is one more thing. And then we'll be taking a dinner break. Okay. Dear students, here I've mentioned a statement. Usage of pressure instead of moles. Usage of pressure instead of moles. Usage of pressure instead of moles in a gaseous reaction. So first of all, just one thing, guys. You know PV is equal to nRT? You know your PV is equal to nRT. Perfect. PV is equal to nRT. If I keep volume and temperature constant, can I say pressure is directly proportional to moles? If I keep volume and temperature constant, I can say pressure is directly proportional to moles. So if moles are decreasing, pressure will decrease. Moles are increasing, pressure will increase. Right? Moles are decreasing, pressure will decrease. Moles will increase, pressure will increase. And you know it already. As the reaction proceeds, moles of reactant decrease with time. Pressure of reactant also decrease with time. Moles of product increase with time. Pressure of product also increase with time. And this equation says us that the proportion in which moles are changing, in the same proportion, pressure is also changing. The proportion in which moles will be changing, in the same proportion, pressure will be changing. What does that mean? In one statement, I'm telling you. Whatever treatment till now we were doing with the moles, same to same treatment you are directly going to do with the pressure. Whatever treatment we were doing with the moles, same to same treatment you are going to do with the pressure as well if the reaction is carried out at constant volume temperature. Because as the reaction proceeds, moles of reactant decreases. Therefore, pressure of reactant also decreases. Okay? Moles of product increases. Therefore, pressure of product also increases. And the proportion in which moles change, in the same proportion, pressure will also change. Okay? Am I clear? Am I clear? Am I clear with this? See what I mean exactly. We will, for example, you have got the reaction like this. Let's say A gas. It gives B gas plus C gas. A gas gives B gas plus C gas. A gas gives B gas plus C gas. For example, this particular reaction is carried out at constant volume and temperature. Let's say this reaction is carried out at constant volume and temperature, wherein I can say pressure is directly proportional to moles. Okay? Let's say at time t is equal to 0. At time t is equal to 0, there will be only one gas in the container, that's gas A. So whatever is the pressure at time t is equal to 0, that is due to A, which is, for example, how much? P naught. This is 0, this is 0. So till now I used to start with the moles, but here now we can start with the pressure directly. We can start with the pressure directly. I start with P naught. This is the pressure of reactant at time t is equal to 0. Now whatever treatment we were doing with the moles, same treatment you are going to do with the pressure. So I would say at equilibrium, Imagine this was your moles. Then you were supposed to write it as P naught minus X. 1 gives 1, X gives X, 1 gives 1, X gives X. Done. Now what are these? These are not the moles. These are the partial pressures directly. These are the partial pressures of reactants products at equilibrium. These are the partial pressures of reactants products at equilibrium. I hope you're getting this. Let's say you've got the reaction like this. Let's say the reaction is 2 times A gas in equilibrium with, let's say 3 times B gas plus 4 times, 5 times C gas. This is the reaction, for example. Okay? Imagine this reaction is carried out at constant volume temperature. Therefore, again, pressure is directly proportional to moles. So whatever treatment we used to do with the moles, same treatment with the pressure. So time t is equal to 0. There'll be only a reactant in the container. So whatever is the pressure at time t is equal to 0, that is due to A, which is nothing but P naught. This will be 0. This will be 0. Right? So at equilibrium, this is supposed to be P naught minus X. Now, 2 moles gives 3. 1 gives 3 by 2. X gives 3 by 2x. And similarly, this is pi by 2x. And if I ask you what are these terms, you're not going to say these are the moles. These are the partial pressures of reactants products directly. These are the partial pressures of reactants products directly. See guys, where it's used. See where it's used. Look at this question. Simple. Look at this question, guys. I'm given with a reaction, and the reaction is given this format. AB3 gas in equilibrium with, and say it's AB2 gas plus half of B2 gas. This is the reaction that's given to me. As per the question, the initial pressure of AB3, that's given to me as 900 torr. This is 0. This is 0. Now, at equilibrium, I must say, pressure due to AB3 will be 900 minus X. 1 gives 1, X gives X. 1 gives 1 by 2, X gives X by 2. So, these are technically the partial pressures. These are the partial pressures of reactants products in the container at equilibrium. If these are the partial pressures, we are done almost. We are done almost, people. As per the question, the total pressure of the mixture at equilibrium is how much? The total pressure of the mixture at equilibrium is 1000 torr. And total pressure of the mixture will be the sum of these partial pressures. So it is basically 900 minus X plus X by 2, right? So this term cancel. And as per the question, this is 1000. So I would say X will come out to be 200 from here. X came out to be 200, right? If X is 200, 900 minus 200 is 700 torr. This will be 200 torr, 200 by 2, 100 torr. So what are these basically? These are the partial pressures of reactants products at equilibrium. If you got the partial pressures of reactants products at equilibrium, you can easily get the Kp value. Kp is equal. Partial pressure of AB2, that's 200. Raised per stoichiometric coefficient 1. Partial pressure of B2, that's 100. Raised per stoichiometric coefficient 1 by 2. Partial pressure of AB3, that's 700. Raised per stoichiometric coefficient 1. So it comes out to be finally, this will be 10, 2000 by 700, which comes out to be 20 by 7, right? And its units. Its units are going to be torr raised by delta Ng. Delta Ng is 1 plus 1 by 2, 3 by 2. 3 by 2 minus 1 is 1 by 2. So this is the final answer of the question. I believe this is clear. Did you understand? If we start with the pressure directly, right, a lot of calculation is saved. Because here, you directly get the partial pressures. You are not supposed to get the total moles, then get the mole fraction first, then finally get the partial pressures. No, you're not supposed to do that. I hope this is clear. Let's do one more question, and after that, we are going to take a break. Okay? Let's do this question first. Let's do this question first. My dear students, as far as the question is concerned, I'm given with a reaction. Let me write the reaction. 4 times HNO3, 4 times NO2, 2 times water, and this is O2. The total pressure at equilibrium is given to me as 30, okay? And the partial pressure of HNO3 is 2. Calculate Kp. Calculate Kp. Yeah? All right. Let's see how to do this question. My dear students, initial pressure of reactant is not given. Let the initial pressure of the reactant is P naught. So this will be 0, this will be 0, this will be 0. At equilibrium, let this be P naught minus X. 4 gives 4, 1 gives 1, X gives X. 4 gives 2, 1 gives 2 by 4, 1 by 2. So X gives X by 2. Similarly, this is going to be X by 4. So what are these things? What did I calculate? These are nothing but the partial pressures. These are the partial pressures of reactants products at equilibrium. These are the partial pressures of reactants products in the container at equilibrium. Okay. If these are the partial pressures of reactants products at equilibrium, as far as the question, look at the statement. The partial pressure of HNO3 at equilibrium is 2 atm. Partial pressure of HNO3 is P naught minus X. Technically, I would say P naught minus X value is given to me as 2. Right? And total pressure of the mixture is 30 atm. Total pressure of the mixture at equilibrium is 30 atm. So what do you think? Total pressure of the mixture will be sum of these partial pressures. So it's going to be P naught minus X plus X by 2 plus X by 4, and this value has to be equal to 30. Now this P naught minus X as per the question is given to me as 2. So this value is 2. Take this 2 on this side. So this becomes 30 minus 2, 28. And this becomes 7x divided by 4 is equal to 28. So 7, 7, 4. X is equal to 16. X is equal to 16. If you got X, P naught minus X is already 2 atm. Right? X is 16 atm. X by 2. 16 by 2 is 8 atm. 16 by 4 is 4 atm. So I got the partial pressures of each reactant product. If I got the partial pressure of each reactant product, I can easily calculate the expression for Kp. I can easily write the expression for Kp. It's partial pressure of NO2, 16, raised power stoichiometric coefficient, that's 4. Partial pressure of water, that's 8, raised power stoichiometric coefficient 2. Partial pressure of O2, that's 4, raised power stoichiometric coefficient 1, divided by partial pressure of HNO3, that's 2, raised power stoichiometric coefficient 4. Matter of calculation. Solve this, get the value of Kp. And people, this is how you do the Kp and Kc calculation with the help of which method? With the help of mole method. Now, our next topic will be calculation of Kp and Kc with the help of degree of dissociation method, right? But that's happening after the break. So, here we are taking the break till, but I would want every one of you to be back, okay? Break till, it's a dinner break. It's 9:30. Let's be back at 10:10. Okay. So 40 minutes of break I'm giving you. But I would want every one of you to be back on time. And we'll be done with this chapter by 12:30 or 1. Okay. Perfect. I would want every one of you to be back. Chalo, you guys have your dinner? Let me write it as dinner break. Dinner break. See you. See you in a while. See you in a while, people. Are you guys back on time? Yes, is everyone back? Is everyone back, people? All right. So, people, tell me once in the chats, whatever we have discussed till now, if every single thing is clear to you or not. Let me know quickly in the chats. Everyone. Whatever concepts I have taught you till now, are all the concepts clear? Are all the concepts clear? Yeah? Are all the concepts clear? All right. Perfect, perfect, perfect. So let's get going. Let's get started then with one more topic, that is your degree of dissociation, right? So first of all, this degree of dissociation is represented by alpha. Degree of dissociation is represented by alpha. What this degree of dissociation exactly is all about? Just have a look at its definition. Degree of dissociation, it is basically defined as the fraction of reactant. The fraction of reactant. That fraction of reactant which dissociates into products. Dissociates means breaks down. Dissociate means breaks down. That fraction of reactant that breaks down into products, that fraction of reactant which gets converted into products, that fraction of reactant which dissociates into products. That is something which you call as degree of dissociation. Say, if I talk about this degree of dissociation alpha, since I'm telling you it is the fraction of reactant that gets converted into product, how do we write it exactly? How do we write its formula? I would say degree of dissociation alpha, it is equal to number of moles of reactants dissociated into products, number of moles of reactants dissociated into products divided by the initial moles of reactants. Number of moles of reactants dissociated into products divided by initial moles of reactants. So, in short, I'll be writing it's ND divided by NI. Let's try to understand this a bit more in detail. See guys, for example, imagine that you have got a reaction. Let's say you have got the reaction A gas in equilibrium with B gas plus C gas. Let's say this is the reaction. Okay, let's say this is the reaction. For example, if I say at time t is equal to 0, let's assume initially I have got A moles of this reactant. Let's say I've got A moles of this reactant. So this is supposed to be 0, this is supposed to be 0 because I'm talking at time t is equal to 0, right? Now, my dear students, if I say the degree of dissociation of the reactant is alpha, what does that mean? Alpha represents that fraction of reactant which gets converted into product. Alpha represents that fraction of reactant which gets converted into product. Now understand. Say, I told you alpha is equal to number of moles of reactants dissociated into product divided by initial moles of reactant, right? So I can say alpha is equal to ND divided by NI. What is NI? Initial moles of reactants. How many initial moles of reactants do we have? A. So can we calculate ND from here? Can I say ND is nothing but A alpha? What is ND? These are now the moles of reactants which are dissociating into products. right? So A alpha, ND is equal to A alpha. These are the moles of reactants which are dissociated into products, right? So my dear students, in the beginning, if I took A moles of reactants, and I got to know out of A moles of reactants, A alpha moles are being dissociated into products. So can I say I'll be left with A minus A alpha? These are the moles of reactant left in the container at equilibrium, right? Now, use the stoichiometry, same approach. 1 mole of A gives 1 mole of B. Therefore, A alpha moles of A are going to give us A alpha moles of B. Therefore, similarly, 1 mole of A gives 1 mole of C. Therefore, A alpha moles of A gives us A alpha moles of C. So what are these terms here? These are again the moles of reactants and products present in the container at equilibrium. But now, these moles are present in terms of alpha. We have written these moles in terms of alpha. Earlier, instead of A alpha, we used to write X. It used to be A minus X. This used to be X. This used to be X. Now here, instead of that X only, we are writing A alpha, nothing else. So in short, remember, out of A moles of reactant, A alpha moles gets converted into products. Out of A moles of reactant, A alpha moles get dissociated into products. Correct? Similarly, if I take few more examples so that it will be like properly clear to you. Let's say people, I've got a reaction like this. 2 times A gas in equilibrium with B gas plus C gas. This is the reaction. Okay. Let's say initially at time t is equal to 0, we have got A moles of reactant. So this is 0, this is 0. Let's assume its degree of dissociation is alpha. So I would say at equilibrium, out of A moles of reactants, how many moles got dissociated? A alpha. So I'll be left with A minus A alpha moles of reactant at equilibrium. Correct? Earlier it used to be X. Again, I'm repeating the same thing. Earlier it used to be X here. Now instead of X, I'm using the term A alpha. Okay, now use the stoichiometry. If 2 moles of A are giving us 1 mole of B, therefore 1 mole of A gives 1 by 2 moles of B. A alpha moles of A gives us A alpha by 2 moles of B. Simple. 2 moles of A gives us 1 mole of C. 1 mole of A gives us 1 by 2 moles of C. A alpha moles of A gives us A alpha by 2 moles of C. So these are the moles of reactants products present in the container at equilibrium, right? And I've written them in terms of alpha. In mole method, they were written in terms of X. In degree of dissociation method, we write them in terms of alpha, like you're seeing here. For example, let's say you've got the reaction like this. 2A gives 3B plus 5 times C. Let's say this is the reaction. Degree of dissociation alpha. At time t is equal to 0. Imagine I'm starting with A moles of reactant. So this is 0. This is 0 in the beginning. Now at equilibrium, out of A moles of reactants, I would say A alpha would have got dissociated. So I'll be left with A minus A alpha moles of reactant at equilibrium. Now we use the stoichiometry again. 2 moles of A are giving us 3 moles of B. 1 mole of A gives us 3 by 2 moles of B. A alpha moles of A gives us 3 by 2 A alpha moles of B. Similarly, this is going to be 5 by 2 A alpha moles of C. So these are the moles of reactants products present in the container at equilibrium. I believe this is clear to everyone. Similarly, people, for example, we have got the reaction in this format. A gas plus 3 times B gas. It's in equilibrium with 2 times C gas. Let's say this is the reaction. For example, in the beginning, we have got A moles of this, for example, B moles of this, and 0 moles of this. And this alpha here. Okay. So at equilibrium, I must say, out of A moles of this reactant, A alpha would have reacted with B. So I'll be left with A minus A alpha here. Okay, I'll be left with A minus A alpha. Now we use the stoichiometry again. 1 mole of A reacts with 3 moles of B. If 1 mole of A reacts with 3 moles of B, I would say A alpha moles of A reacts with 3 A alpha moles of B. I had taken B. Out of B, 3 A alpha are reacting. So I'll be left with B minus 3 alpha. Right? Similarly, 1 mole of A gives 2 moles of C. Therefore, A alpha moles of A are going to give me 2 A alpha moles of C. I hope you got to know how do we calculate the moles of reactants products in terms of alpha. I hope you got to know how to calculate moles of reactants products in the container at equilibrium in terms of alpha. Okay. If you got it, let's see exactly how Kp and Kc calculation is done with the help of degree of dissociation. But before that, take a note of one more thing. Take a note of one more thing. Sometimes I'll be writing a term percentage dissociation. Sometimes I'll be writing a term percentage dissociation. Percentage dissociation is nothing. That is alpha. Fractional dissociation multiplied by 100. Okay. So percentage dissociation is nothing. That's alpha multiplied by 100. Sometimes they won't give you in the question the direct value of alpha. They'll tell you that the reactant is 20% dissociated, 30% dissociated, 40% dissociated. You can calculate alpha from there easily. Okay? You can calculate alpha from there easily. I believe I'm clear with this. Yeah? Clear, guys? Is it clear? Is it clear? Let's move on and let's do the calculation of Kp and Kc by degree of dissociation method. Calculation of Kp and Kc by degree of dissociation method. See guys, let me take one reaction so that it'll be clear to you. Understand properly what exactly I'm going to say. I'm going to take a basic, I'm taking a basic reaction over here. Simple reaction. The reaction is like this. A gas in equilibrium with B gas plus C gas. Understand properly. Let's say I'm starting with A moles of reactant. So this will be 0 in the beginning. This will be 0. Degree of dissociation is alpha. At equilibrium, out of A mole of reactant, I would say A alpha would have dissociated. So I'll be left with A minus A alpha moles of reactant at equilibrium. 1 mole gives 1, A alpha gives A alpha. This is also A alpha. So what I got, these are the moles of reactants products present in the container at equilibrium, right? Now people, let's say the volume of the container. Let's say the volume of the container in which the reaction takes place. Let's say that is V. If I divide this particular term, by the volume of the container, I'm dividing this particular term with the volume of the container. I'm dividing this particular term with the volume of the container in liters. What do I get? I'll be calling these terms as the concentrations of reactants products at equilibrium, right? Similarly, people, if I ask you, how many total moles are there in the container at equilibrium? If I ask you, how many total moles are there in the container at equilibrium? I would say at equilibrium, there is a mixture of gas present. And that mixture of gas contains these many moles of A, these many moles of B, these many moles of C. So total moles at equilibrium is nothing but A minus A alpha plus this A alpha plus the other A alpha. So this alpha cancels out. So I'll be getting A plus A alpha here. So these are the total moles in the container at equilibrium, right? Now, what I'll be doing? If I divide A minus A alpha with the total moles present in the container at equilibrium, I divided this particular term. I divided this particular term with the total moles in the mixture at equilibrium. What do I get? This is something which I call as mole fraction of A at equilibrium. Similarly, mole fraction of B will be A alpha divided by A plus A alpha, right? Mole fraction of C at equilibrium will be A alpha divided by A plus A alpha, correct? Now people, let's assume the total pressure of the mixture at equilibrium is represented by PT. So I'll be multiplying this term with PT. I'll be multiplying this term with PT. I'll be multiplying this term with PT as well. So what do I get? I'll be getting the partial pressures of reactants products at equilibrium, right? Same approach. What we used to do in mole method, same thing we are doing here. So here I got the concentrations of reactants products at equilibrium. I got the partial pressures of reactant products at equilibrium. Now, it is just, we have to write the expression of Kc and Kp, and we are done. Kc expression will be equal to concentration of B at equilibrium raised power stoichiometric coefficient, concentration of C at equilibrium raised power stoichiometric coefficient, concentration of A at equilibrium raised power stoichiometric coefficient. So Kc is equal. What is the concentration of B at equilibrium? A alpha by V. C at equilibrium, A alpha by V. So it becomes A alpha divided by V ka whole square divided by concentration of A at equilibrium is nothing but it is A minus A alpha divided by V. Right? Now, what is going to be the final expression here? One of the V gets cancelled out. This A gets cancelled out. So I'll be left with A alpha square divided by V multiplied by 1 minus alpha. So this is the expression of Kc which we got for the reaction in terms of alpha. In terms of alpha. In terms of alpha. Okay? In terms of alpha. This is the expression of Kc. Similarly, people, you can get the expression for Kp too, right? If you want to write the expression for Kp, you can do that. Kp expression is going to be partial pressure of B at equilibrium raised power stoichiometric coefficient, partial pressure of A at equilibrium, sorry, not A, partial pressure of C at equilibrium raised power stoichiometric coefficient divided by partial pressure of A at equilibrium raised power stoichiometric coefficient. So Kp has to be equal. What is partial pressure of B at equilibrium? This is the partial pressure of B at equilibrium. This is the partial pressure of C at equilibrium. So this multiplied by this. Take a square of it. It is Pt multiplied by A alpha divided by A plus A alpha whole raised power 2. Whole raised power 2 divided by partial pressure of A. This is the partial pressure of A, which is Pt multiplied by A minus A alpha divided by A plus A alpha. Okay. So first of all, let's see what all things are going to get cancelled out. This A ka square, A ka square cancel, A everywhere cancelled. So Kp finally will be equal to Pt gets cancelled out. So what are we left with? I think we are left with one of the Vt gets cancelled. So one Pt is left in the numerator, right? This A square here cancelled. So this is alpha square divided by this, and this is going to be finally 1 minus alpha square. Okay, this is the expression for Kp which we got over here. After doing all the calculations, after cancelling out things, right, you'll be getting the value of Kp over here like this. Alpha square Pt divided by 1 minus alpha square. I hope this is clear to everyone. Okay, so this is the process, people, which you have to follow. This is the process which you have to follow for the calculation of Kp and Kc in terms of alpha. In terms of alpha, yeah? Perfect. I'll take one more reaction so that it becomes like properly clear to you. See, for example, I've got the reaction like this. 2 times A gives B plus C. First of all, tell me one thing. What is delta Ng for this reaction? Tell me the value of delta Ng for the reaction. Tell me the value of delta Ng for the reaction. I would say delta Ng for this particular reaction is 0. And if delta Ng for the reaction is 0, I would say its Kp and Kc must be equal. Right? Its Kp and Kc must be equal. So let's exactly get to know how Kp and Kc for this reaction will be equal. Understand properly what I'm going to do. Initially, at time t is equal to 0, we have got A moles of reactant. So this is 0, this is 0. Degree of dissolution alpha. At equilibrium, I would say this is going to be A minus A alpha. These are the moles of reactant. Now, 2 moles are giving 1. 1 gives 1 by 2. A alpha is going to give us A alpha by 2. Similarly, this gives us A alpha by 2. Perfect. These are the moles of reactants products at equilibrium. Similarly, concentration of reactants products at equilibrium. What am I supposed to do? I'm supposed to divide all these terms with the total volume of the vessel in liters. So this is A minus A alpha divided by V. This is A alpha divided by 2 multiplied by V. This is A alpha divided by 2 multiplied by V. Okay. Now, if I ask you first of all, what are the total moles in the container at equilibrium? Total moles in the container at equilibrium will be this plus this plus this. A alpha by 2, A alpha by 2 makes it A alpha. And that A alpha with this A alpha gets cancelled out. So total moles at equilibrium is equal to A. I'll be dividing this term, A minus A alpha. I'll be dividing with the total moles. Similarly, A alpha divided by 2, I'm dividing with the total moles. Similarly, A alpha divided by 2, I'm dividing with the total moles. So what did I get over here? I got the mole fractions. I got the mole fractions of reactants products at equilibrium. Let's say the total pressure of the mixture at equilibrium is Pt. So multiplying everyone with Pt here, what did I get? I got the partial pressure of each reactant product at equilibrium. Okay, perfect. Now guys, if I want to write the Kc expression is going to be concentration of B at equilibrium, concentration of C at equilibrium, which is going to be A square alpha square divided by 4V square whole divided by concentration of A at equilibrium, that is A minus A alpha divided by V whole raised power 2. Okay, so Kc is equal to, see, A square common, cancel, right? A V square cancel, so it's alpha square divided by 4 multiplied by 1 minus alpha ka square. So this is the expression, final expression of Kc, which you get after solving this. Okay, this is Kc. Now Kp. Now get the value of Kp. So first of all, Kp. If you look at these partial pressures, do you see some of the terms are getting cancelled out? If you take A common here, A gets cancelled. So it's finally 1 minus alpha multiplied by Pt. A gets cancelled. So it's alpha Pt divided by 2. Similarly, this is alpha Pt divided by 2. Right? These are the partial pressures of reactance products in the container at equilibrium. Now, partial pressure of B, that's alpha Pt by 2. Partial pressure of C, alpha Pt by 2. So it's alpha square Pt square divided by 2 ka square is 4 whole divided by partial pressure of A at equilibrium, that is 1 minus alpha multiplied by Pt raised power stoichiometric coefficient, that's 2. Okay, so Pt square gets cancelled out, and I would say Kp value came out to be alpha square divided by 4 multiplied by 1 minus alpha ka square. If you look carefully, this is the value of Kp which you are getting. And my dear students, as I told you already, this is the reaction whose delta Ng is 0. And if delta Ng for this reaction is 0, then definitely its Kp and Kc were supposed to be equal. And this is how you got their Kp, Kc values. Right? They are equal. I believe this is clear to everyone. I believe this is clear to everyone now. Okay? All clear, people? All clear? So this is how you make Kp and Kc expressions in terms of alpha. Sometimes in a lot of questions, you will have to solve this particular equation to get alpha. Okay? You will see a lot of questions. For example, see, if I consider this equation, if I write alpha divided by 2 multiplied by 1 minus alpha, raised power what? Whole raised power 2. It's equal to Kc. Perfect. If I take root, so this becomes square root of this. Okay? So square root of Kc is equal to alpha divided by 2 minus 2 alpha. Perfect. Now you can do the cross multiplication and stuff, and you can get alpha from here as well. So my point is, sometimes in some of the questions, right? In some of the questions, you'll have to solve these equations furthermore to get the value of alpha if it's not given. Yeah? Perfect. Now, let's see what kind of questions can be framed out of all this. I believe simple questions only will be framed from all this. See. Calculate the Kp for the dissociation of 1 mole of PCl5. First of all, you should know when PCl5 undergoes dissociation. It gets converted into what? It gets converted into PCl3. With PCl3, you get Cl2. This is the reaction. Okay. Now, as per the question, we are starting with how many moles of PCl5? We are starting with 1 mole of PCl5. So this is 0, this is 0, right? Now, in the question, they are not mentioning alpha. They are telling us that 20% is dissociated at equilibrium. So, I would say alpha is equal to, how much percent is dissociated? 20 divided by 100. So, alpha is nothing but 0.2. Okay, simple. Alpha is nothing but 0.2. I told you already, percentage dissociation is equal to alpha into 100. So, alpha is equal to percentage dissociation divided by 100. So, I know the alpha value 2. So, at equilibrium, out of A moles of reactant, A alpha would have got converted. So, I'll be left with A minus A alpha. This would be A alpha and this would be A alpha. Now, we know the value of alpha, 0.2. We know the value of A. So, get the exact moles. Get the exact moles at equilibrium. So, 1 minus 1 into 0.2. So, this comes out to be 0.8. 1 into 0.2. This is 0.2. Even this is 0.2. So, these are the moles of reactance products present in the container at equilibrium. If these are the moles of reactance products at equilibrium, can you let me know how many total moles are there in the container at equilibrium? This plus this plus this. It comes out to be 1.2. Divide this with 1.2. Divide this with 1.2. Divide this with 1.2. So you got the mole fractions now. These are the mole fractions. These are the mole fractions of reactants products at equilibrium. Now, after this, what do? We are supposed to multiply these mole fractions with the total pressure at equilibrium. How much is the total pressure at equilibrium? 1 atm. So multiply this with 1, multiply this with 1, multiply this with 1. So what do I get here? I got the partial pressures of reactants products in the container at equilibrium, right? So this value will come out to be 2 by 3. This value will come out to be 1 by 6. This value will also come out to be 1 by 6. So these are the partial pressures of reactants products in the container at equilibrium. If these are the partial pressures of reactants products in the container at equilibrium, can't we write the expression for Kp? We can do that. Partial pressure of PCl3 at equilibrium, that's 1 by 6 multiplied by partial pressure of Cl2 at equilibrium, 1 by 6 whole divided by partial pressure of PCl5 at equilibrium, that's 2 by 3. Okay, so it is 1 by 6 multiplied by 1 by 6 multiplied by 3 by 2. So 3, 1, 3, 2. So the final value is going to be 1 divided by 24. If I ask you about the units, since the pressure is in atm, so atm raised power delta Ng. Atm raised power delta N. What is the delta Ng for this reaction? 1 plus 1 is 2, 2 minus 1 is 1. So atm raised power 1. So this is the Kp value which we were supposed to calculate as far as the question was concerned. Is that clear? Is that clear, people? Wait, I think I need to block some people. I don't know what they're typing. So yeah, they're busy in some other stuff, I feel. Okay. Please, one more. Done. One more needs to be wait. Perfect. I hope this sort of a question, you should be in a position to solve easily from now on. Okay, easily means easily from now on. Similar sort of question, guys. Similar sort of question this is. The degree of dissociation of N2O4 at 1.5 atm and 25 degrees centigrade is 0.25. So alpha is given, 0.25. Calculate Kp for the reaction. I'll just show you the process, calculation part, etc. you can do on your own afterwards. This N2O4 gas in equilibrium with 2 times NO2 gas, right? So first of all, are we given with the initial moles of reactants? We are not given with the initial moles of reactants. We are not given with the initial moles of reactants. Now, if we are not given with the initial moles of reactants, so what do? Let's assume that we have got A moles of reactant. This is 0. Degree of dissociation is alpha, which as per the question is equal to 0.25, right? So at equilibrium, this is supposed to be A minus A alpha. This is supposed to be 2A alpha. Now, if I ask you how many total moles are there in the container at equilibrium, this plus this, which comes out to be A plus A alpha. If I'm dividing this with A plus A alpha, dividing this with A plus A alpha, what do I get? I got mole fractions. I got mole fractions of reactants products at equilibrium. If I multiply these mole fractions by the total pressure, how much is total pressure? 1.5. 1.5. This is also 1.5. I got the partial pressures of reactants products at equilibrium. See, A gets cancelled. A and A gets cancelled here. So 1 minus alpha. 1 minus alpha. 1 minus 0.25 is 0.75 divided by. This will be 1 plus alpha. So 1 plus 0.25 will be 1.25 multiplied by what? Multiplied by 1.5. So this is the actual partial pressure of reactant at equilibrium. Similarly, this A and A here gets cancelled. 2 into alpha. 2 into 0.25 is 0.5 divided by 1 plus alpha. It is 1.25 multiplied by what? Multiplied by 1.5. So again, this is basically the partial pressure of product at equilibrium. If you got the partial pressures, you can easily write Kp expression. You can easily write Kp expression, people, right? And write the Kp expression. Kp expression is going to be partial pressure of NO2 at equilibrium raised power stoichiometric coefficient divided by partial pressure of N2O4 at equilibrium raised power stoichiometric coefficient. That's 1. Now both the things are, we have calculated, put the values, get the value of Kp at the end, right? Again, one simple and basic question which I believe you should be in a position to solve from now on, if it is asked. Okay, if it is asked. If it is asked. Look at this question. Look at this question, guys. Let's see what the question says. If 1:3 mixture of N2 and H2 yields NH3 20% by volume at 30 atm, okay, create Kp for this reaction. All right. See, the reaction that's given to me is N2 gas plus 3 times H2 gas in equilibrium with 2 times NH3 gas. Correct? Now, my dear students, I'm given with their molar ratio. This is 1, this is 3, this is 0. So imagine we have got 1 mole of N2, 3 moles of H2, and 0 moles of NH3 in the beginning, right? Well, you can solve this particular question in terms of alpha, or you can directly solve this question in terms of x. I feel x is going to be easier here. See how? Let's say at equilibrium, out of 1 mole of reactant, 1 mole of N2, x moles have reacted. So I'll be left with 1 minus x. 1 mole reacts with 3 moles. X moles will react with 3x moles. I've taken 3. Out of 3, 3x are reacting. So I'm left with 3 minus 3x. 1 mole gives 2 moles. So x is going to give me 2x. Okay, clear till here? Now, tell me how many total moles are there in the container at equilibrium. Total moles at equilibrium will be 1 minus x plus 3 minus 3x plus 2x, right? This plus this plus this. It comes out to be 4 minus 2x. Is that? 3 plus 1, 4. 4 minus 2x. So if I divide this with 4 minus 2x, if I divide this with 4 minus 2x, if I divide this with 4 minus 2x, what do I got? What do I get here? I got the mole fractions. I got the mole fractions of reactants products at equilibrium. If you see properly, I got the mole fractions of reactants products at equilibrium. Now guys, try to understand. As far as the question is concerned, volume percentage of NH3 at equilibrium is given. Volume percentage of NH3 at equilibrium is given to us as 20. If you remember, I told you already, at equilibrium, volume percentage is nothing but mole percentage. So technically, I'm given with mole percentage of NH3 at equilibrium, right? I'm given with mole percentage of NH3 at equilibrium. How much? That is 20. Perfect. Now, mole percentage is what? It is basically mole fraction of NH3 multiplied by 100. Right? So, I would say mole fraction of NH3 at equilibrium is equal to 0.2. I got the mole fraction of NH3 at equilibrium. Now, guys, we are done. If mole fraction of NH3 at equilibrium we got, how much? This value is equal to 0.2. 0 point means 2 by 10. And this mole fraction of NH3 at equilibrium we have already calculated. This is 2x divided by 4 minus 2x is equal to 2 divided by 10. I would say 2 cancels out. So 10x is equal to 4 minus 2x. I would say 12x is equal to 4. So x is equal to 1 by 3. X is equal to 1 by 3. Right? If you got x, put the value of x here, x here, x here, x here, x here, x here. What do I get? Mole fractions. Once you get the mole fractions of reactants products, total pressure is given to us. Right? So multiply all the mole fractions by the total pressure. You'll be getting the partial pressure of each. And if you got the partial pressure of each, that means you can easily get the value of Kp, right? Make the Kp expression and get it done. I believe from here you can solve this question. If yes, let me know once in the chats quick. If yes, say it once in the chats. You got the x value. Put the value of x here, x here, x here. You got the actual mole fractions. Those mole fractions multiplied by total pressure gives us the partial pressures of each reactant product. If you got the partial pressure of each reactant product, what do we supposed to do after that? If we got the partial pressures of reactants products at equilibrium, write the Kp expression, right? I mean, just the calculation part is left. Just the calculation part is left. And I believe you can solve this question on your own. Is that people? So have an eye on this sort of question as well. Now, there is one more way to calculate alpha. There is one more way to calculate alpha. That's called as vapor density measurement. That's called as vapor density measurement. My dear students, I'm going to give you two results. Okay? We are going to remember those results. No need to go for the derivations and stuff. Okay? We are going to remember those results and we'll use those results in the questions directly. Okay? See. For example, I've got the reaction like this. AN gives N times A. AN gives N times A. The stoichiometric coefficient here I'm keeping as 1. Here the stoichiometric coefficient is N. I'm assuming N value is greater than 1. I'm assuming this N is greater than 1. If N is greater than 1, that means it can be 2, it can be 3, it can be 4. If N is 2, what does that mean? If N is 2, that means one particle of reactant is giving us 2 particles of product. If N is 3, one particle of reactant is giving us 3 particles of product. If N is 4, one particle of reactant is giving us 4 particles of product. So from one particle, you are getting more than 1 particles. From one particle of reactant, you are getting more than 1 particles of products. From one particle of reactant, you are getting more than 1 particles of products. So I would say reactant is dissociating into more than 1 particles, right? Reactant is dissociating into more than 1 particle. So this is something which I'll be calling as the case of dissociation. This is something which I'll be calling as the case of dissociation, right? This is something which I'll be calling as the case of dissociation. And my dear students, whenever this is the scenario and you are supposed to calculate alpha, I'm giving you one direct result. There's a derivation for it as well. I'm not doing that, right? Leave that aside. How do we calculate alpha? Alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. This is alpha here. What is this capital D? What is the small d? Have a look. My dear students, this capital D I'm calling it as the theoretical vapor density, or you can directly call it as vapor density of reactant. You can directly call it as vapor density of reactant at T is equal to 0. Vapor density of reactant. And you should be knowing vapor density is nothing. It is molar mass by 2. So molar mass of reactant divided by 2. This is capital D. Capital D is equal to molar mass of reactant divided by 2. That's it. Capital D is equal to molar mass of reactant divided by 2. Capital D is what you call as theoretical vapor density, or you can say vapor density of the reactant. Okay. The small d, my dear students, I am calling the small d as experimental vapor density. This is something which I call as experimental vapor density, or let me directly call it as vapor density of the mixture. Vapor density of the mixture at equilibrium. Since at equilibrium you have got a mixture of gas, vapor density of that mixture of gas at equilibrium, vapor density of that mixture of gas at equilibrium is small d, and vapor density of the mixture is nothing but it is going to be average molar mass of the mixture at equilibrium divided by 2. It's equal to average molar mass of the mixture divided by 2. Remember these terms. Capital D, theoretical vapor density, which is equal to molar mass of reactant by 2. Small d, experimental vapor density, or vapor density of the equilibrium mixture, which is average molar mass of the mixture divided by 2. Okay, and this alpha here represents what? This alpha here represents degree of dissociation. And you know, this N, what does this N represent? N represents the number of moles. N represents the number of moles of products obtained from 1 mole of reactant. Number of moles of products obtained from 1 mole of reactant. For example, let's say you have got the reaction like this. PCl5 gas gives PCl3 gas plus Cl2 gas. Let's say this is the reaction. If I ask you what is the value of N for this reaction, have a look carefully. I'll say 1 mole of reactant is giving 1 plus 1, 2 moles of products. So 1 mole of reactant is giving me 2 moles of products, so N value is 2. N value is 2. For example, you have got the reaction like this. 2A gives 3B plus 4C. 2A gives 3B plus 4C. All the reactants products in gaseous state. Do you see? 2 moles of reactants are giving us 4 plus 3, 7 moles of product. If 2 moles of reactants are giving us 7 moles of product, or let me write it like this, wait. This is 5 times C. 5 times C. If 2 moles of reactant are giving us 8, 5 plus 3, 8. 8 moles of products. So 1 mole of reactant will give me, if 2 moles of reactants are giving us 8 moles of products. So 1 mole reactant will give me 8 by 2, 4 moles of products. And number of moles of product which we get from 1 mole reactant, that's called as N. So N value for this particular reaction will be nothing but 4. Yeah? Do you understand all this stuff? Do you understand, people? Do you understand? Do you understand? Okay. Perfect. Now, in case of dissociation, let me show you one more thing. See, guys. Alpha is equal to capital D minus small d divided by small d multiplied by N minus 1. Okay. This is the equation which we use in case of dissociation. This is the equation which we use in case of dissociation for the calculation of alpha. Now, understand. If I write this equation like this, I'm writing alpha as such. This N minus 1 I'm taking here is equal. This becomes capital D minus small d divided by small d, right? So let me write it like this. N minus 1 into alpha is equal. Capital D divided by small d minus 1. Or I can say capital D divided by small d is equal to 1 plus N minus 1 into alpha. Why did I make this equation? Because here I wanted to plot a graph. Because here I wanted to plot a graph. The graph is between capital D by small d. The graph is between capital D by small d versus alpha. Versus alpha. Now, people, just it's done. Capital D by small d, I'm taking along y-axis. Alpha, I'm taking along x-axis. This particular term is your M, and this is what you call as C. The sign is plus. Y is equal to mx plus c. Y is equal to mx plus c. This is a straight line, and its slope is nothing but slope is n minus 1. Slope means m, and here the slope is n minus 1. From this graph also sometimes questions are asked, and I'll show you in some time how this particular from this particular graph questions are framed. Okay. Okay, guys. So this was the case of what? This was the case of dissociation. Now, similarly, let me show you the case of association, and after that, we'll see what kind of questions can be framed. Let me show you the case of association as well. Let me show you the case of association as well. See, for example, you have got the reaction like this. Na in equilibrium with An. Na in equilibrium with An. What am I assuming here? I'm assuming n value greater than 1. I'm assuming n value greater than 1. Okay? If n is greater than 1, so n can be, for example, 2. If n is 2, that means 2 particles of reactant are giving 1 particle of product. N can be 3. 3 particles of reactant are giving 1 particle of product. 4 particles of reactant are giving 1 particle of product. So I would say more than 1 particles of reactants are associating and forming 1 particle of product. Right? I would say more than 1 particles of reactant are associating to form 1 particle of product. So this is the case of association. More than 1 particle of it. See, n value is greater than 1. If n is 2, that means 2 particles of reactant are forming 1 particle of product. 3 particles of reactant are forming 1 particle of product. So more than 1 particles of reactant are associating and forming 1 particle of product. So this is the case of association basically. Like you have got dimer formation. What happens in dimer formation? 2 particles of A They associate and they form one particle of A2. So this is the case of dimerization, right? This is the case of dimerization. Similarly, if three particles of reactant are associating and forming one particle of product, this is the case of trimerization. Trimer formation. Okay? This is the case of trimer formation. Now here, this alpha is not called as degree of dissociation. I would say this alpha is called as degree of association. Alpha is called as degree of association. And alpha is equal to capital D minus small d divided by small d multiplied by. It used to be n minus 1, but here it's going to be 1 by n minus 1 over here. Okay? So only change in the formula is, in the dissociation case, it used to be n minus 1 here. In the association case, it's going to be 1 by n minus 1. In the association case, it's going to be 1 by n minus 1. Now, all the other stuff, that's same. What is capital D? You know it. Theoretical vapor density. Small d, experimental vapor density. But what is n here now? N. What does n represent? N represents number of moles of reactants, associated, to form 1 mole of product. Number of moles of reactants associating to form 1 mole of product. Okay. Now guys, here also we need to make one graph. Here also one graph is needed. Let's see how the graph can be formed. You know, degree of association alpha is equal to capital D minus small d divided by small d multiplied by 1 by n minus 1. So let's do one thing. Let's write it like this. 1 by n minus 1 multiplied by alpha is equal to capital D minus small d divided by small d. Simple. Just reshuffling things, nothing else. Right? So 1 by n minus 1 into alpha is equal to capital D by d minus 1. Or I would say capital D by small d is equal to 1 plus, this is 1 by n minus 1 into alpha. Okay, capital D divided by small d is equal to 1 plus 1 by n minus 1 into alpha. So here you can easily make the graph. The graph is between capital D divided by small d versus alpha. Capital D by small d you are plotting along y-axis. Alpha you are plotting along x-axis. This whole term is your m and this is your c. The sign is plus. Y is equal to mx plus c. Y is equal to mx plus c means straight line with the positive slope, and the slope here is going to be 1 divided by n minus 1. Okay, this is the graph which we have made over here. Perfect. Now guys, all this dissociation and association, perfect, whatever things we have discussed for the calculation of alpha, let's see what kind of questions can be framed out of all this. One simple and basic question. Look at the question. Just tell me whether you will be able to solve this or not. Just tell me that. Just tell me that. Tell me in the chats whether you'll be able to solve this or not. Quick. Yeah? Can be done, right? See guys, let's write the reaction once. N2O4 gas in equilibrium with 2 times NO2 gas. This is the reaction. Now, what are we supposed to calculate? Calculate the percent dissociation of N2O4. Percentage dissociation we have to calculate. Percentage dissociation of N2O4, which will be nothing but degree of dissociation multiplied by 100. So what am I supposed to calculate? I'm supposed to calculate alpha basically. I'm supposed to calculate alpha. Check first of all, is this the case of dissociation or association? one particle, 1 mole of reactant is giving 2 moles of products. 1 mole is giving 2 moles. So this is the case of dissociation. So alpha has to be capital D minus small d divided by small d multiplied by n minus 1. What is the n value here? 1 mole of reactant is giving me 2 moles of products. So n is 2. 1 mole of reactant is giving me 2 moles of products. So n is 2 here. Okay. Now, as per the question, the vapor density of N2O4 and NO2 mixture, vapor density of the mixture at equilibrium is represented by small d. So as per the question, this is the value of small d that's given to me. Vapor density of the mixture at equilibrium, that's small d. Small d is given to me. Okay. How do I get the capital D? What is capital D? Theoretical vapor density, or you can say it is the vapor density of the reactant, which is nothing but molar mass of reactant divided by 2. Molar mass of reactant, molar mass of N2O4 is 92 divided by 2. The value comes out to be 46. So capital D is 46. We are done. Alpha is equal to capital D 46, small d 30, small d 30, n value 2 minus 1. The value will come out to be 0.52. If alpha is equal to 0.52, that means how much percentage of N2O4 has dissociated? I would say it is alpha multiplied by 100. 0.52 multiplied by 100, the value is 52%. I believe I'm clear with this. Yeah? Is it clear, people? Is it clear? This is one of the simplest questions which can be asked from this particular topic. Okay? Let's see one more question. Let's see one more question. Look at this one. Look at this one. In the reaction given below, the vapor density of the mixture means small d. Vapor density of the mixture, that means small d, is reduced to half when equilibrium is achieved. The vapor density of the mixture, the vapor density of the equilibrium mixture is reduced to half. Half of what? Half of theoretical. Half of theoretical. That means small d is equal to capital D by 2. This is something which is given to us as per the question, number 1. Number 2. If the percentage dissociation is 25, reactant is being 25% dissociated. So alpha will be equal to 25 by 100. Alpha is equal to 25 by 100. Okay. Now the question is saying how many moles of B would be formed on starting with 2 moles of A. See guys, the reaction is A gas in equilibrium with N times B gas. This is the reaction. Its alpha already I know, that is 0.25. Alpha is 0.25. At time t is equal to 0, I'm starting with how many moles of A? I'm starting with 2 moles of A. Okay. So this has to be 0 in the beginning. Now when equilibrium is established, I would say from A alpha moles would have converted. So I'll be left with A minus A alpha. Similarly, 1 mole of A gives n moles of B. Therefore, A alpha moles of A gives us Na alpha moles of B. And this is something which we are supposed to calculate. We are supposed to calculate number of moles of B formed at equilibrium. That is nothing but Na alpha. We know the value of alpha given to us. A value is given to us. What do we need? We need the n value here first. We need the n value. So how do I get the n value? How do I get the n value? See guys, you know, alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. So alpha is equal to 1 by 4 is equal to capital D minus small d. So capital D minus small d divided by small d multiplied by n minus 1. So this term as well as this term cancels out. So 1 by 4 is equal to 1 by n minus 1. So n here comes out to be 5. So n also we got. N also we got. A we have, alpha we have. So put all the values. So n is 5, A is 2, and alpha is 1 by 4. After solving, the value comes out to be 2.5. So we got to know that 2.5 moles of B have got formed at equilibrium. Am I clear? Am I clear, people? Is this particular question clear? Perfect. See, guys. Look at this particular question. Look at this particular question. Look at this particular question. The graph is given. Capital D by small d versus alpha. Its slope is given. All right. For the reaction, the curve between this is given. Calculate the percentage dissociation. Okay. Calculate the percentage dissociation. Percentage dissociation is what? That is alpha multiplied by 100. So technically, I have to get the value of alpha first. Okay. Calculate the percentage dissociation when? Experimental vapor density. Experimental small d. When experimental vapor density becomes half of theoretical. Calculate alpha when small d becomes half of capital D. Okay. First of all, this is the d by d versus alpha graph. Its slope is 2. Slope means n minus 1. So n minus 1 is 2. So what does that mean? That means n value is 3. I got the n value. Now, just the matter of calculation. Capital D minus small d divided by small d multiplied by n minus 1. Capital D minus small d divided by small d. N minus 1 is 2, right? So this gets cancelled. 1 by 2 is 0.5. If alpha is 0.5, I would say percentage dissociation is equal to 50%. So 50% of the reactant has got dissociated at equilibrium. I believe I'm clear with this. Yeah? Clear? Clear, people? I hope this sort of stuff you can easily do from now on. Now I'm moving on to the last topic of the chapter, that is your Le-Chatelier principle. But before understanding the Le-Chatelier principle, it's mandatory to understand the reaction quotient. Okay? Now tell me in the chats first, is every single thing clear? Is every single thing clear till now? It is not going to take more than 1.5 hours now. It's almost done. It's almost done. But tell me first of all whether all the things which we discussed till now, whether they are clear or not. It should not be like I am continuously moving and you are not getting anything out of it. Perfect. That's great. You guys are with me till the end. Amazing. Amazing. Okay, let's see, people, what this reaction quotient is. First of all, this reaction quotient, we represent it with Q. Reaction quotient, we represent this with Q. What is the reaction quotient? See, I would say the expression similar to equilibrium constant. The expression similar to equilibrium constant. At any stage apart from equilibrium. expression similar to equilibrium constant when written at any stage apart from equilibrium. What does that mean? Understand. For example, you have got the reaction like this. Let's say one simple reaction here, N1A, it gives N2B. This is one reaction which we have, okay? If I ask you, how do you write the expression for equilibrium constant Kc? How do you write it? You write it concentration of B at equilibrium raised per N2 divided by concentration of A at equilibrium raised per N1. Correct? This is how you write equilibrium constant Kc expression. This is how you write equilibrium constant Kc expression. Okay? Now, my dear students, if you write the similar expression, but this time don't write concentration of B at equilibrium, just write concentration of B raised per N2. Just write concentration of A raised per N1. I'm not taking the concentration of B at equilibrium now. I'm just writing concentration of B raised per N1. Concentration of A raised per, concentration of B raised per N2. Concentration of A raised per N1. I'm taking the concentrations of reactants and products at any stage apart from equilibrium. I'm taking the concentrations of reactants and products at any stage apart from equilibrium. Right? I'm calling this expression as QC. I'm calling this expression as Q, reaction quotient. Did you understand what is the difference between the two? When we write equilibrium constant expression, we take the concentrations of reactants and products at equilibrium. So, when the concentrations of reactants and products are taken at any stage apart from equilibrium, at that time you do not call it as equilibrium constant. You call it as reaction quotient. You call it as reaction quotient. When this expression is written at any stage apart from equilibrium. Okay? Now, people, tell me first one thing. If you have got a reaction, I'm telling you, Q for the reaction is equal to Kc. If, for example, QC is equal to Kc, right? QC is equal to Kc, what does that mean? If you have got a reaction whose Kc and QC are equal, what does that mean? That means the reaction is at equilibrium. The system is at equilibrium. Right? The system is at equilibrium. Perfect? Or wait, let me make you understand this a bit more in detailed manner. For example, you have got the reaction like this, A, B. Okay? Understand. Let's say at time t is equal to 0, its concentration is 10 molar. This is for example 0 molar. Let's say at 10 seconds, this is 5 molar. This is also 5 molar. Or let me write it as, let's say at 10 seconds, this is 8 molar, this is 2 molar. Let's say at 20 seconds, this is, for example, 6 molar, this is 4 molar. Let's say at 30 seconds, this is 4 molar, this is 6 molar. Okay? And let's say this is the time at which equilibrium is established in the reaction. This is the time at which equilibrium is established in the reaction. So first of all, can I write the equilibrium constant expression Kc? Kc is going to be concentration of B at equilibrium, that is 6, divided by concentration of A at equilibrium, that's 4. This is your equilibrium constant for the reaction. Okay? This is your equilibrium constant for the reaction. Now, let me first talk about this particular instant. At this particular instant, let me get the value of concentration of B raised per stoichiometric coefficient divided by concentration of A, 2 by 8. What do I call this as? I'll be calling this as the reaction quotient at 10 seconds. This is 4 divided by 6. I'm calling this as a reaction quotient at 20 seconds. This is 6 divided by 4. I'm calling this as a reaction quotient at 30 seconds. At 30 seconds, this is the reaction quotient. At 20 seconds, this is the reaction quotient. At 10 seconds, this is the reaction quotient. What is the equilibrium constant? 6 by 4. What is the reaction quotient here? 6 by 4. So when QC is equal to Kc, can I say at that point of time, I can say in the reaction there is already equilibrium. When QC of the reaction, when reaction quotient becomes equal to equilibrium constant, what can we say? We can say equilibrium is established in the reaction if reaction quotient already got equal to the equilibrium constant. Okay? Perfect. My dear students, if you remember, I told you in the beginning, what is equilibrium? What is equilibrium? Equilibrium is basically that state of the system at which entropy of the system is maximum, free energy of the system is minimum. Entropy of the system is maximum, free energy of the system is minimum. And as per thermodynamics, that state of the system at which entropy is maximum, free energy is minimum, that is considered to be the most stable state of the system. So at equilibrium, I would say equilibrium is that state in a reaction at which the system is maximum stable. System means your reaction, that is maximum stable. That is why in every reversible reaction, sooner or later, equilibrium is established. Why? Because every system wants to be at the stable position. Every system wants to be present at the stable state. And in case of reactions, in case of reversible reactions, which is that stable state? That is equilibrium. That is the reason why in every reversible reactions, equilibrium is established sooner or later, because every system wants to be present at the stable state. And in case of reactions, that stable state is equilibrium. In case of reactions, that stable state is equilibrium. Okay? Okay, perfect. In other words, I can say, every reaction wants its Q value to be equal to K. In other words, I can say every reaction wants its Q value to be equal to K. Because when Q of the reaction becomes equal to K, then only I would say equilibrium is established. And if equilibrium is established in the reaction, system is present at its maximum stable state. Yeah? So every reaction wants its Q to be equal to K. Got it? Now people, tell me one thing. Let's say you got the reaction whose Q is less than K. Let's say you got the reaction whose Q is less than K. Q is less than K. This is K, this is Q. Let's say you got the reaction whose Q is less than K. So system is not at equilibrium. System is not at equilibrium. System will be at equilibrium when Q will be equal to this K. Right? Let's say you got a reaction whose Q is less than K. So I would say there is no equilibrium set right now. System is not at stable state. System wants to be at the stable state. System wants to be at its stable state. That means system wants to be at equilibrium. Right? So system wants its Q to be equal to K. So what this system has to do? Should it increase its Q value? Yes, system has to increase its Q value, then it will become equal to K. System has to increase its Q value now. Then it will come to equilibrium. How system can increase its Q value? System can increase its Q value when numerator increases, denominator decreases. Numerator increases means concentration of B increases. How can concentration of B increase? When the shift is forward, right? I would say here, the forward shift favors. Here, the forward shift favors. I hope you got this particular point. Yeah. Similarly, people, if by chance QC is greater than KC, let's say QC is greater than K, Q is greater than K, system is not at equilibrium, but system wants to be at equilibrium. So system wants its Q to be equal to K. So what the system has to do? It has to decrease its Q value such that it becomes equal to K. And how system will decrease its Q value? How system will decrease its Q value? System will decrease its Q value only if this decreases, this increases. How can A increase? How can A increase? If backward shift favors. So remember, in order to attain equilibrium, backward shift favors here. In such kind of the reaction, to attain equilibrium, to be at the stable state, backward shift favors. I believe this is clear to everyone. I believe this is clear to everyone. For example, if I take one simple question, the question is, you got the reaction A plus B, it gives C plus D. Okay? Just I'm framing a question like this. Let's say Kc is equal to 100. Kc for the reaction is 100. And I am telling you, if at t is equal to 50 seconds, at time t is equal to 50 seconds, at time t is equal to 50 seconds, the concentration of all the four species, is equal to 1 molar each. Is equal to 1 molar each. I'm asking you to predict the direction of shift Predict the direction of shift to attain equilibrium. Predict the direction of shift to attain equilibrium. Can you let me know? What will be the answer? Equilibrium constant is given. Now, get the value of Q at 50 seconds. Q at 50 seconds will be concentration of this divided by this. So, all the concentrations are 1 molar. So, it becomes 1 into 1 divided by 1 plus 1. QC is 1. So, QC is coming out to be less than KC. If QC is less than KC, then QC has to increase its value. How? I would say here, forward shift is favored to attain equilibrium. Forward shift is favored to attain equilibrium. I believe this is clear. Forward shift is favored to attain equilibrium. Okay? Right, people? All clear with this? All clear with this? Perfect. Let's move on to our last topic. What is that? That is your Lee-Chatter's principle. Lee-Chatter's principle. Lee-Chatter's principle. From this particular concept also, questions are frequently asked and many a times asked. Questions have been many a times asked from this particular topic. So what is this Lee-Chatter principle? Before reading the statement and etc. etc. My dear students, tell me one thing. Tell me one thing. If I have got any system at equilibrium, what does that mean? That means the system is present at its maximum stable state as per thermodynamics. Yeah? System is present at its maximum stable state as per thermodynamics. Now, since you know that the system is present at its maximum stable state, that means system is at equilibrium. Now, if I want to do some changes to the system, I already know system is at equilibrium, system is at maximum stable state, but still I want to do some changes. What will happen due to that? I want to do certain changes. Change as in, I want to increase, decrease the pressure of the system. I want to increase, decrease the volume. I want to increase, decrease the concentrations. Anything, whatever I could do, I can do. I want to do. What would happen because of that? Because of that, equilibrium will get disturbed. Equilibrium will get disturbed. Okay? Equilibrium will get disturbed because so system initially was at present at its maximum stable state. Now, the stability of the system has altered. It changed a bit. System has moved towards destability. But no doubt, system has moved towards destability. System has moved towards instability because of the changes which I did towards the system. But system would never want to be at the unstable position. System want to bring back its stability. How will it bring back its stability? Whatever changes I did to the system, system has to do the changes opposite to that. Then only it can bring back the stability. Have a look on this particular statement. You'll understand. According to this principle, if any change is imposed on the system at equilibrium, equilibrium shifts in such a direction in which effect of change is nullified. This is the clear-cut example, right? This is a steady state right now. Let me call this as equilibrium, just to make you understand, right? This is not the appropriate example, but you can remember it like this. Let's say this is equilibrium right now between the two sides, okay? Perfect. If I put more weight on this side, it will be like this. But the system would again want to be at the stable state, right? System would again want to be at the stable state. Basically, in short, if I say something like this, whatever we do to the system at equilibrium, equilibrium exactly does opposite of what we do to nullify the effect of change. Are you getting what I'm trying to say? Yeah? Nullify means cancelled. If any change is imposed on the system at equilibrium, equilibrium is going to shift in such a direction in which effect of change is nullified. So, in short, whatever we do to the system at equilibrium, right, the system is going to opposite of what we do. That's all. To nullify the effect of change. To nullify the effect of change. Do you get this? Do you get this? Yeah? So when the system is at equilibrium, it is present at its maximum stable state. Now, I am doing certain change to the system, right? I'm doing some change to the system. I'm doing something like changing pressure, changing temperature, whatever. Due to which, the system which was already at stable state, now, system has moved from stability towards instability. What system won't be like willing to stay at the unstable state? It would want to bring back its stability. How it is going to bring back its stability when system again moves towards equilibrium? How system moves towards equilibrium? Whatever changes I did to the system is going to do opposite of what I did to that, so as to bring back the equilibrium. Yeah, so as to bring back to equilibrium. Okay. Got it? So, in short, I would want you guys to remember one statement. And I'm going to write it over here. From this particular statement, you can do all the things correct. I would say, whatever we do to the system, whatever we do to the system at equilibrium, I would say system does exactly opposite of that to restore equilibrium, to restore stability, to restore equilibrium, to restore stability. Okay? Now, the first thing, let's get to know the effect of addition or removal of a reactant or product. The effect of addition or removal of a reactant or product on equilibrium. Have a look, guys. For example, you have got the reaction like this. You have got the reaction like this, for example. Okay. Imagine, my dear students, this particular reaction is at equilibrium. Right? This particular reaction is at equilibrium. If this reaction is at equilibrium, I would say its QC and KC would be equal. Right? Its QC and KC would be equal, which is going to be concentration of B raised power 1, concentration of A raised power 1. I would say the reaction is right now at equilibrium. Okay? That's the reason why since its QC and KC is equal, the reaction is at equilibrium. Since the reaction is at equilibrium, it is present at its maximum stable state. Now, I am going to do certain changes to disturb the equilibrium, right? I am going to do some change to disturb the equilibrium. Perfect. Let's see what will be the changes from the system. What system is going to do in return? Let's get to know about that. For example, if reactant is added or product is removed. If reactant is added or product is removed at equilibrium, what will happen? If reactant is added or product is removed at equilibrium, what happens? If reactant is added or product is removed at equilibrium, what happens? Understand. If reactant is added, that means A is added, or product is removed, If A is added or product is removed, that means you are increasing the amount of A, decreasing the amount of B. You're either increasing the amount of A or you're decreasing the amount of B. Anyways, if you're increasing the amount of A or decreasing the amount of B, right? What will happen to QC? What will happen to QC? If amount of B is reduced or amount of A is increased, I would say QC will decrease. I would say QC will decrease. QC will decrease. QC was earlier equal to KC. Now QC has decreased by my actions. Whatever I did, because of that QC has decreased. Earlier QC was equal to KC. The system was at equilibrium. Now, because of my changes, because of me, QC has decreased. So now the system is not at equilibrium. But system would again want to restore equilibrium. How? That means system has to increase its QC. How system will increase its QC? How system can increase its QC? System can increase its QC if amount of B increases and amount of A increases. How amount of B will increase? When equilibrium shifts forward. I would say in this particular case, equilibrium shifts forward. Yeah? Equilibrium shifts forward. I hope this is clear. Number one. Number two, if reactant is removed or product is added. If reactant is removed or product is added, where? At equilibrium. What happens due to that? What happens due to that? If reactant is removed, right? Or product is added. If we are adding reactant, if we are removing reactant, that means if we are decreasing the concentration of A, if we are decreasing the concentration of A or increasing the concentration of B, if we are increasing the concentration of B, what will happen to QC? QC will increase. Earlier, QC and KC were equal. Now we are increasing QC basically. So now QC and KC are not equal. Equilibrium is disturbed. So system would again want to bring back the equilibrium. How? When QC, that means system will make its QC to decrease so that it becomes again equal to KC. How QC will decrease? How QC will decrease? How can QC decrease? QC can decrease if amount of B decreases, concentration of B decreases, and concentration of A increases. How will that happen? How will concentration of A increase when equilibrium shifts backward? Is this particular point clear to everyone? Is this particular point clear to everyone? Yeah? Right, people? So when the system is at equilibrium, QC, KC are equal. Now, if we do certain changes to A and B, let's say we are increasing the amount of A. If I increase the amount of A, that means I'm increasing the reactant. If I'm increasing the reactant, QC will decrease. QC will decrease. Earlier QC, KC were equal. Now QC will decrease. So QC again has to increase its value. How can QC increase its value? When equilibrium shifts forward. Simple. Yeah? Guys, remember one more thing. Take a note over here. On adding or removing a solid at equilibrium. On adding or removing a solid at equilibrium, there will be no shift. There will be no shift. Why is that? Why is that? My dear students, shift happens when QC changes. When QC either becomes greater than KC or when QC becomes less than KC. That's why shift happens. Okay? Now imagine out of these two, let's say this B is in solid state. If B is in solid state, so its active mass is unity. So in this expression, there'll be no B. Now, if you want to increase B or decrease B, since B is not in the expression, that means nothing will happen to Q. Q will still be equal to KC. Nothing. Q is neither increasing nor decreasing. It is still equal to K. So there'll be no shift. Shift happens when Q becomes greater than KC or Q becomes less than KC. That's why shift happens. If there is some solid, in the reaction, okay, since its active mass is unity, that solid won't come in this expression. If that solid is not coming in this expression, by increasing or decreasing the amount of that solid, since that solid is not in the expression, QC does not change. If QC does not change, that means there will be no shift at all. Got it? Is it clear, people? I hope this particular stuff is clear. For example, this is the reaction. Calcium carbonate solid, calcium oxide solid, carbon dioxide gas. This is the reaction at equilibrium. If you increase or decrease the amount of calcium carbonate, there will be no shift. If you increase or decrease the amount of calcium oxide, there will be no shift. Because they are in solid state. Right? They are in solid state. Because if I say at equilibrium Q and K are equal. Perfect. And the expression is going to be just concentration of carbon dioxide raised power 1. This is going to be the expression. Okay. So if you increase calcium carbonate, if you increase the amount of calcium carbonate, since it's not in the expression, nothing happens to Q. Q is still equal to K, right? So there'll be no shift at all. So guys, finally, how do you remember this? This is the actual concept which I told you, but how do you remember this? Just remember it like this. Whatever you do to the system is going to do opposite of that. For example, I'm increasing the amount of A. I'm increasing the concentration of A. Let's say I'm increasing the concentration of A. Equilibrium will try to decrease it. How? It will make sure reaction shifts forward. Let's say if I decrease the concentration of A, equilibrium will try to increase it. How? Backward. If I decrease the amount of B, equilibrium will try to increase it. How? Forward. If I increase the amount of B, equilibrium will try to decrease it. How? Backwards. This is how you are going to remember it. Actual logic is in terms of reaction quotient. But this is the way you can remember it, which I told you. Okay? Got it? Now, effect of change in pressure. See guys what it means. Look at the statement first of all. The statement is on increasing the pressure, reaction will shift in the direction in which the total gaseous moles decreases. On increasing the pressure, reaction will shift towards lower gaseous moles. For example, this is the reaction. On reactant side, how many gaseous moles do you have? 3 plus 1, 4. On product side, how many gaseous moles do you have? 2. Okay, 2. Let's say this reaction is carried out at constant volume temperature. Or let me not use this particular statement. Let's keep it simple only. Reactant side, how many gaseous moles do you have? 3 plus 1, 4. Okay, product side, how many? 2. Two. Okay. My dear students, if you look carefully, in the forward direction, are the gaseous moles decreasing? Yes, in the forward direction, the gaseous moles are decreasing. So that means in the forward direction, if the gaseous moles are decreasing, so pressure is decreasing in the forward direction. In the backward direction, gaseous moles are increasing, so pressure is increasing. In the forward direction, pressure is decreasing. In the backward direction, pressure is increasing. Okay, in this particular reaction. Now, for example, since I know in the forward direction, pressure decreases. In the backward direction, pressure increases. If I increase the pressure of this system, equilibrium will try to decrease it. If I try to increase the pressure of this system, equilibrium will try to decrease it. How? How equilibrium will decrease the pressure? It will shift the reaction in the direction of decreasing moles. That means in the direction of decreasing pressure. So at that time, reaction shifts forward. If reaction shifts forward, in the forward direction, gaseous moles are decreasing basically. So I would say when I increase the pressure of the system at equilibrium shifts in the direction of decreasing moles. If moles are decreasing in forward direction, that means reaction will go forward. If moles are decreasing in backward direction, that means reaction will go backward. I hope you understood what I said. This is how you can remember it in short, in simple words. Yeah? See, this is the reaction wherein you are saying in forward direction, gaseous moles are decreasing, so pressure is decreasing. In backward direction, pressure is increasing. Okay? Now, if I want to increase the pressure of the system, equilibrium would want to decrease it. How equilibrium would decrease it? How equilibrium would decrease the pressure? It will shift the reaction towards decreasing pressure. That means forward. And in the forward direction, gaseous moles are decreasing. That's what I said. Equilibrium, on increasing the pressure, equilibrium will shift in such a direction in which the total gaseous moles decrease. Okay? Let's say this is one reaction. For this reaction, delta Ng is 0. Delta Ng is 0 means on left side, gaseous moles are 2. On right side, gaseous moles are 2. Right? So are the moles changing? No. If moles are not changing, if gaseous moles are not changing, will the pressure change? No. Okay? So if you increase or decrease the pressure, will there be any shift? There will be no shift. So remember that particular reaction was delta Ng is 0. Nothing happens due to the change in pressure. Nothing happens due to the change in pressure. There will be no shift due to the change in pressure. Okay, if you increase or decrease the pressure of this particular system, suppose delta Ng is 0, right? There will be no shift at all. Because in both the directions, there is no increase or decrease in the pressure. Remember this particular statement as well. Now comes one important one, that is effect of temperature. Effect of temperature. My dear students, effect of temperature is explained by the equation. That's something which you call as Van 't Hoff equation. Log of K2 divided by K1 is equal to delta H divided by 2.303 R 1 upon T1 minus 1 upon T2. This is the equation which is going to let us know what happens to equilibrium constant on increasing or decreasing the temperature. Understand what I'm going to say? My dear students, for example, this is the reaction. This is the reaction, A gives B. Let's say when the temperature of the reaction was T1, when this reaction was carried out at this temperature, let's say its equilibrium constant was K1. Now, for example, I'm changing the temperature of the reaction from T1 to T2. Let's say at temperature T2, the equilibrium constant of the reaction is K2. Okay. For example, at temperature T1, when reaction was carried out at temperature T1, okay, when reaction was carried out at temperature T1, its equilibrium constant was K1. Now the same reaction is carried out at temperature T2. Now its equilibrium constant is K2. This is something which I'm assuming. So understand. Understand, guys. For example, let's assume that this particular reaction is endothermic in nature. Let's assume that the reaction is endothermic. If the reaction is endothermic, its delta H is positive. Its delta H is positive. Okay, delta H is positive. Imagine that we are changing the temperature from T1 to T2. For example, we are increasing the temperature. Let's say we are increasing the temperature of the reaction. We are increasing the temperature of the reaction. If we are increasing the temperature of the reaction, can I say T2 will be greater than T1? If we are increasing the temperature of the reaction, definitely T2 would be greater than T1. If T2 is greater than T1, I would say T2 minus T1 will come out to be positive. T2 minus T1 will come out to be positive. If this is positive, this is positive. Overall, this term will come out to be positive. Overall term coming out to be positive. That means log of K2 divided by K1 is coming out to be positive. When is the log of X positive? Log of X is positive when X is greater than 1. That means K2 by K1 has to be greater than 1, which simply means K2 has to be greater than K1. What does it mean? What does it mean? Since I increase the temperature, K2 is coming out to be greater than K1. K2 is coming out to be greater than K1. What does that mean? That means equilibrium constant has also increased. On increasing the temperature, equilibrium constant has also increased. So that clearly tells me that equilibrium constant is directly proportional to temperature when it comes to which reactions? When it comes to endothermic reactions. Now the reaction could have been exothermic too. If the reaction was exothermic, if that reaction was exothermic, I would say its delta H would be negative. If the reaction was exothermic, its delta H was negative. Its delta H was negative. Now imagine that this reaction is exothermic, so delta H negative. For example, I'm increasing the temperature of the reaction. Let's say I'm increasing the temperature of the reaction. That means T2 is greater than T1. If T2 is greater than T1, T2 minus T1 will come out to be positive. T2 minus T1 will come out to be positive. I'm increasing the temperature of the reaction. So T2 minus T1 is coming out to be positive. This term is already negative. Positive, negative makes it negative. So I would say overall term is coming out to be negative, which means log of K2 by K1 is negative. When is log of X negative? Log of X is negative when X is less than 1. So I would say here K2 will be less than K1. Here K2 will be less than K1. Here K2 will be less than K1. What does that mean? That means when you increase the temperature, equilibrium constant, K2 is less than K1. That means equilibrium constant has decreased. So in case of exothermic reactions, remember equilibrium constant is inversely proportional to temperature. In case of exothermic reactions, remember equilibrium constant is inversely proportional to temperature. Am I clear with this? Am I clear with this? Am I clear with this particular concept? Yeah? So basically, in case of endothermic reaction, when you increase the temperature, equilibrium constant has to increase. How will equilibrium constant increase? How will equilibrium constant increase? Equilibrium constant will increase when reaction shifts forward. So there will be forward shift. Similarly, in case of exothermic, when you increase the temperature, equilibrium constant will decrease. How equilibrium constant will decrease? How equilibrium constant will decrease? When reaction shifts backwards. When reaction shifts backwards. Okay, when reaction shifts backwards. I hope this is clear. And it's ln K versus 1 by T graph I've shown you already. When I taught you characteristics of equilibrium constant, okay, ln K versus 1 by T graph, I've shown you already for endothermic as well as exothermic in the beginning of the chapter itself. Okay. Got it? This was effect of temperature. Now comes one important thing. Effect of inert gas addition at constant pressure. Effect of inert gas addition at constant pressure. My dear people, I'm going to divide this slide into 3 parts so that it becomes like properly clear to you. Let's say here I'm writing the reaction in this format. A gas, this is gas, okay? A gas gives B gas plus A gas gives B gas plus C gas. This is one of the reaction. A gas gives B gas plus C gas. Let's say one more reaction I'm writing like this. A gas plus B gas gives C gas. Okay. The third one I'm writing like this. 2A gas in equilibrium with B gas plus C gas. Now, what is different in these reactions? For this particular reaction, I would say delta Ng is positive, right? For this particular reaction, I would say delta Ng is negative. For this particular reaction, I would say delta Ng is 0. These are the 3 possibilities, right? These are the 3 possibilities. These are the 3 possibilities. My dear students, let's assume that at equilibrium, in the container, there are A moles of this, B moles of this, B moles of this. Okay. Let's assume at equilibrium there are A moles of this, B moles of this, B moles of this. If I divide them with volume, so it becomes the concentration. So these are the concentrations of reactants products at equilibrium for this reaction. If the reaction is at equilibrium, that means its Q and K will be equal. Q and K will be equal at equilibrium, which will be B square by V square divided by A by V, which is going to be finally B square divided by V multiplied by, or let me write it like this. It is going to be B square by V square whole divided by A by V. So one of the V get cancelled. So B square divided by A multiplied by 1 by V. Okay. Since this particular reaction, I'm assuming at equilibrium. At equilibrium, QC and KC are equal, and this is the expression. Now, for example, assume that the reaction which I took over here, this particular reaction. Imagine this particular reaction is taking place at constant pressure. Imagine this particular reaction is taking place at constant pressure. Okay? Imagine this particular reaction is taking place at constant pressure. First of all, you know, majority of the reactions, or I would say all the reactions, they are carried out at constant temperature. They are carried out at constant temperature. Apart from that, right now I'm keeping pressure constant as well. Right now I'm keeping pressure constant as well. So PT is constant. You know, PV is equal to nRT. So if pressure temperature is constant, R is already constant. Can I say volume is directly proportional to moles? Yes. That means if moles are increasing, volume will increase. Moles are decreasing, volume will decrease. Now guys, since this particular reaction is carried out at constant pressure temperature, imagine you are adding inert gas in this container. Inert gas means that particular gas which is neither going to react with A nor B nor C. Inert gas is that particular gas which is neither going to react with A nor B nor C. Okay? You are adding inert gas here in this container. Now, since you are adding inert gas into this container, so what is happening to the total moles present in the container? I would say total moles in the container is increasing. That means volume of the system is increasing. If V is increasing, means QC will be decreasing. If V is increasing, that means QC will be decreasing, inversely proportional. Earlier they were equal. Now, due to the addition of inert gas, QC has decreased. So, equilibrium is disturbed. So, QC would again want its value to be equal to KC. So, that equilibrium is restored. So, that means QC has to increase its value. How QC will increase its value? QC will increase its value when reaction shifts forward. QC will increase its value when equilibrium shifts forward. When equilibrium shifts forward. When equilibrium shifts forward. So, when I'm adding inert gas right now, equilibrium is shifting forward in this particular reaction whose delta Ng is greater than 0. Okay? Whose delta Ng is greater than 0. Equilibrium is shifting forward. Okay, equilibrium is shifting forward here. For which reaction whose delta Ng is greater than 0. Let me first of all talk about this particular reaction now, whose delta Ng is less than 0. Let's say at equilibrium, let's say when equilibrium is established in this reaction, there are A moles of this, and for example B moles of this in the container. If I divide this with V, this V, this V, so these are the concentrations now. So at equilibrium, your QC and KC will be equal, which will be concentration of C at equilibrium divided by A by V into A by V, that's A square by V square. So it comes B divided by A square multiplied by V. Okay. Now, for example, since this particular reaction right now, it's carried out at constant pressure and temperature. So if I'll be adding inert gas in the container in which this reaction carries out, if I'll be adding inert gas, total moles in the container will increase. If total moles are increasing, total volume of the system will increase. If volume of the system increases, that means QC will increase. Already QC was equal to KC. Now due to inert gas addition, QC is increasing. So QC would again want its value to decrease. How QC would decrease its value? QC would decrease its value when reaction shifts backward. I would say equilibrium shifts backward here upon the addition of inert gas. Upon the addition of inert gas here, equilibrium shifts backward. Right? Equilibrium shifts backward. For the reaction whose delta Ng is less than 0. This was delta Ng greater than 0. Look at this particular reaction now. Let's say at equilibrium we have got A moles of this, B moles of this, B moles of this. If I divide this with V, divide this with V, divide this with V, what will happen? So I got the concentrations of react. See, A, B, B. These are the moles of reactants products at equilibrium, which I'm assuming. Okay. Now when I divided them with V, I got the concentrations of reactants products at equilibrium. Now, since if this reaction is at equilibrium, that means its QC and KC are equal. The expression will be concentration of this, which is V square by V square, whole divided by concentration of this ka square, A by V ka square. So V square gets cancelled out. It's B square by A square only. Right? Now, this particular reaction is taking place in some container. whose pressure and temperature we have kept constant. Whose pressure and temperature we have kept constant. Now, if you add inert gas, due to the addition of inert gas, total moles will increase. So total volume will increase. But do you see volume in the expression here? In the expression, volume is not there. QC is right now equal to Kc. You are doing the inert gas addition at constant pressure, due to which moles are increasing. So volume is increasing, but volume is there not in this expression. So will anything happen to QC here? Nothing is going to happen to the QC. QC and Kc are still equal. Nothing is happening to QC. Nothing is happening to QC, right? If QC is neither increasing nor decreasing, will there be any shift? There will be no shift. So remember, that particular reaction was delta Ng is 0. That particular reaction was delta Ng is 0. If you add inert gas at constant pressure, there will be no shift. Yeah, there will be no shift. Am I clear with this? Or if you want to remember this in one statement, you can do that too. First of all, I took that reaction whose delta Ng is greater than 0. Here I took that reaction whose delta Ng is less than 0. Here I took that reaction whose delta Ng is equal to 0. And in all the cases, I added inert gas at constant pressure. I added inert gas at constant pressure. And when you add, in the first case, when you add inert gas at constant pressure, equilibrium shifts forward. That means towards more gaseous moles, towards higher gaseous moles. Equilibrium shifts backwards, again towards higher gaseous moles. Because over here, on the reactant side, there are more gaseous moles. So in short, remember. What is something you are going to remember? This particular statement only. This statement. On adding inert gas at constant pressure, reaction shifts towards highest gaseous moles. Reaction shifts towards highest gaseous moles. If the highest gaseous moles are on reactant side, so equilibrium shifts forward. Sorry. If the highest gaseous moles are on product side, that means equilibrium shifts forward. If the highest gaseous moles are on reactant side, that means equilibrium shifts backward. If delta Ng is 0, there will be no shift. Am I clear with this now? Am I clear with this, people? And all this, I believe you understood from this particular scenario, right? Right, people? All clear till here? Say it in the chats once if it is clear. Say it in the chats if it is super clear. Everybody. Everybody in the chats. Quick. Is it clear? I hope you exactly got to know why shifting takes place. So when the reaction is at equilibrium, QC and Kc are equal. It's at equilibrium. Now if QC either increases or decreases somehow, then shifting takes place. Yeah? Then shifting takes place. I would want every one of you to let me know in the chats quickly if this is clear. Okay. Effect of inert gas addition at constant volume. This one more case. Effect of inert gas addition at constant volume. First one was at constant pressure. Now it's at constant volume. For example, let's say I've got the reaction like this. Let's say I've got the reaction like this. Okay. This particular reaction is happening in a container, for example, in some closed container. Perfect. Now this reaction is, for example, taking place keeping volume and temperature constant. Reaction is taking place at constant volume and temperature. And at constant volume and temperature, what can we say? At constant volume and temperature, I'll say pressure is directly proportional to moles. That means if moles are increasing, pressure will increase. If moles are decreasing, pressure will decrease. Or I can say the proportion in which moles will be increasing, pressure will be increasing in the same proportion. The proportion in which moles will be decreasing, pressure will be decreasing in that proportion only. What does that mean? That means if you double this, this will double. If you halve this, this will halve. So pressure and moles are changing in same proportion. Pressure and moles are changing in same proportion. Okay, now understand. Let's say at equilibrium, we have got A moles of this, B moles of this, and let's say we have got B moles of this as well at equilibrium. At equilibrium, we have got A moles of reactant, B moles of this one, B moles of this one at equilibrium. Okay. If I ask you how many total moles are there in the container at equilibrium, it is going to be A plus B, which makes it A plus 2B. If I divide this with total moles at equilibrium, if I divide this with total moles at equilibrium, if I divide this with total moles at equilibrium, what do I get? Mole fractions. If you got mole fractions at equilibrium, if I multiply these mole fractions by the total pressure at equilibrium, if I multiply these mole fractions by the total pressure at equilibrium, what do I get? Partial pressure. Can I say at equilibrium, your Q and K are equal? At equilibrium, if the reaction is at equilibrium, its Q and K must be equal. That means QP and KP are supposed to be equal, right? QP and KP are supposed to be equal. Now make the expression, KP expression. Partial pressure of this multiplied by partial pressure of this divided by partial pressure of this. So it's going to be B square PT square divided by NT square whole divided by A PT divided by NT. So one of the NT cancels, one of the PT cancels. So I would be getting B square divided by A multiplied by PT divided by NT. This is the final expression. Okay. Now, my dear students, just understand one simple thing. Imagine in this container, I'm adding the inert gas at constant volume. I'm adding inert gas at constant volume. If I'm adding inert gas at constant volume, that means total moles in the container are increasing. Due to the inert gas addition, total moles in the container I'm increasing. If total moles are increasing, pressure is also increasing. And I told you already, the proportion in which moles will be increasing, in the same proportion, pressure will be also increasing, right? So, I'm adding inert gas at constant volume, due to which total moles are increasing in the container. I would say total pressure will be also increasing. See, P is directly proportional to N. What does that mean? That means P by N is equal to constant. P by N is already constant. Okay? So, when you add inert gas here, total moles are increasing. If total moles are increasing, but still P by N is constant, it won't change. If P divided by N value is not changing, that means Q is not changing. If Q is not changing its value, that means it's equal to K. So there'll be no shift at all. Why shifting happens? Shifting happens only due to? Why shifting happens? Because Q either increases or decreases. That's the reason why shifting happens. But here, there'll be no shifting at all. Perfect. I would say we are putting inert gas into the container. Total moles in the container are increasing. Total pressure is also increasing. Total moles are increasing, total pressure is also increasing. So I would say the proportion in which moles increase, in the same proportion pressure will also increase. So the effect will get cancelled out, due to which Q will not change. Q is equal to K only. Okay. So remember this particular stuff. When you add inert gas at constant volume, there will be no shift. One last thing, as I told you already in the characteristics of equilibrium, okay, catalyst, it just speeds up the rate of the reaction or decreases the rate of the reaction, depending on whether the catalyst is positive or negative in nature. Positive catalyst increase the rate of forward and backward reaction by equal amounts. Negative catalyst decreases the rate of forward and backward reaction by equal amounts, right? If I talk about positive catalyst, in presence of positive catalyst, equilibrium comes in the reaction quickly, but nothing happens to equilibrium constant, right? Remember this particular point. Due to the positive catalyst, equilibrium is attained in the reaction quickly. Nothing happens to equilibrium constant basically, right? So equilibrium constant is not affected by the catalyst. We have discussed this particular point long back when I was teaching you characteristics of equilibrium constant. Tell me the answer of all these questions. This is the last. All these 4 or 5 questions we'll do on this so that you'll understand where do we use it. First of all, people understand. The first question says, if we add more H2, if you increase H2, equilibrium will try to decrease it. How equilibrium will decrease it? When it will shift the reaction forward, the forward shift. If NH3 is added, if I increase NH3, equilibrium will try to decrease it. How? When it will shift the reaction backward. Since in this particular reaction heat is absorbed. Heat is absorbed means delta is positive. reaction is endothermic. For endothermic reactions, equilibrium constant is directly proportional to temperature, right? And if temperature is increased, if we increase the temperature, equilibrium constant increases. How equilibrium constant increases? Reaction shifts forward. It shifts forward. Inert gas is added at constant volume. At constant volume, never any shift. No shift. Inert gas is added at constant pressure. Inert gas is added at constant pressure. And you know, when inert gas is added at constant pressure, reaction shifts towards higher gaseous moles. So which side is the higher gaseous moles? Reactant side. It's backward shift. It is backward shift. Done? Done? Wait, let me check this one. Inert gas is added at constant pressure. At constant pressure, what was the logic, guys? Reaction shifts towards higher gaseous moles. Yeah, reaction shifts towards inert gas added at constant pressure. Okay. Yeah, backward. So change it here. Make it backward. Huh? Make it backward. At constant pressure, reaction shifts towards higher gaseous moles. Higher gaseous moles means backward. Yes, it is backward here. Okay. What do you think about this particular question? What do you think about this particular question? You are given with the reaction. The reaction is taking place in a closed container. What is meant by that? Closed container means volume constant. Closed container means volume constant. So, inert gas is added at constant volume. Inert gas is added at constant volume. There will be no shift. If there is no shift, what will happen? If there is no shift, there will be no change in the amounts of these reactants products. There will be no change in the amounts of these reactants products. Right? There will be no change at all. I hope this is clear. I hope this is clear. What about this question? Reaction is carried out. The equilibrium amount of carbon dioxide can be increased by. How can you increase the amount of carbon dioxide? As per the question, we want to increase the amount of carbon dioxide. How can we increase the amount of carbon dioxide? Amount of carbon dioxide can be increased if reaction shifts forward. So what can we do so that reaction shifts forward? If you increase the amount of CO, equilibrium will try to decrease it. How equilibrium will try to decrease the CO? It will shift the reaction forward, due to which carbon dioxide production will increase. So option D is the one. Yes? Right, people? Okay. When NaNO3 is heated, when NaNO3 solid is heated, what does it give? It gives NaNO2 plus half of O2 gas. This is the reaction. When NaNO3 is heated in the closed vessel, oxygen is liberated and NaNO2 is left behind at equilibrium. Addition of NaNO2 favors reverse reaction. Addition of NaNO3 favors forward reaction. Decreasing temperature favors forward reaction. Increasing pressure forwards reverse reaction. First of all, see, this is solid, this is solid. On increasing or decreasing the amount of solid, nothing happens, no shift. So this cannot be, this cannot be. Since we are heating NaNO3, If we are heating NaNO3, we are decomposing it. So reaction is endothermic. If reaction is endothermic, its equilibrium constant will be directly proportional to temperature, right? He's saying decreasing temperature. If we decrease temperature, equilibrium constant decreases. Equilibrium constant decreases, that means reaction shifts backward. But he's saying forward. This cannot. Last one. Increasing pressure favors reverse reaction. See, this is solid, this is solid, this is gas. That means in the forward direction, gas is forming. See, on the reactant side, you have got solids. On the reactant side, on the product side, you have got gas. Basically, in the forward direction, pressure increases. In the backward direction, pressure decreases. Gas to solid, solid to gas, right? Now, if you increase the pressure, equilibrium will try to decrease it. Equilibrium will try to decrease it. How equilibrium will decrease the pressure? It will shift the reaction backward. Backward means reverse. Increasing pressure favors the reverse reaction. Correct? Right? And guys, that's it. This is the topic which is basically the part of ionic equilibrium. right? I'll be doing this as an ionic equilibrium, this particular topic. I was not supposed to keep it here in these slides. Anyways, it's okay. I hope this particular chapter, chemical equilibrium, is done and dusted. Yeah? Is it clear, people? We are done. By the way, next chapter is not going to be ionic equilibrium. Next chapter is going to be thermodynamics. So first of all, we'll be covering the chapter thermodynamics. And this particular chapter will happen on Monday. It will happen on Monday, 5 p.m. Coming Monday. Okay? Monday, 5 p.m. it's going to happen. Got it? This particular topic I'll be teaching you in ionic part. Basically, simultaneous solubility, I'm going to teach it. This is not now in your syllabus, the simultaneous equilibrium. You can keep it as such. Anyways, I'll be giving you the slight idea in the ionic equilibrium chapter as well about this particular topic. Okay, I hope every single thing is clear. My dear students, with this, the chapter is done and dusted. Every single thing is taught in detail. There's not a single topic that's missed. There is not a single problem pattern which we have missed. Every single thing we have done in detail. Okay? Every single thing we have done in detail. The session PDF of this particular session I'll be sharing on my Telegram. Wassim Bhat Chemistry Official is the name of my Telegram channel. You guys can join in, right? And once I end the session, I would want your honest reviews in the comment section of this particular video. I'll be taking a leave with this. You take care. God bless.